In this course so far, we have discussed converter circuits and their DC equivalent circuits. Beginning this week, we will spend the rest of the course discussing converter control systems. What we're going to do is to extend the DC equivalent circuit models that you've learned to construct so far to include the converter dynamics. And we'll be able to solve these AC models of switching converters then to find the important converter transfer functions. And lastly, we're going to use those transfer functions and models to design the control systems of some switching converters. So this week we're discussing Chapter 7, which is titled AC Equivalent Circuit Modeling. So we will extend our previous equivalent circuits to incorporate now the inductors and capacitors of the converter, and we're going to develop small signal AC equivalent circuit models that can be solved with standard circuit analysis to find things like transfer functions of the switching converters. So here is a sketch of a simple feedback system that controls the output voltage of a buck converter. So what's illustrated on top is the switching converter power stage as we've discussed so far, and the bottom half of this diagram is a feedback or a control circuit that adjusts the duty cycle automatically to regulate the output voltage. So the object in such a control circuit is to regulate a voltage such as the output voltage V of t of the converter so that it is equal to a constant and well controlled value capital V. Now you can't just set the duty cycle to one value and leave the circuit alone running at that value and expect the output voltage to always be the desired capital V. And the reason for this is that there are disturbances in signals, such as in the input voltage Vg. It may be, for example, that we derive Vg by rectifying the AC power line voltage, or perhaps Vg is an input battery voltage or some other voltage that is not well controlled. And so there are variations in Vg of t, and these variations propagate through the switching converter and cause variations in V. There can also be variations in the load. Here we simply have a load resistor R, but in fact the load can be something whose current changes. And we know that the output voltage does depend on the load current. Certainly in continuous mode, if we include losses in the circuit, the output voltage does become a function of the load resistance and or the load current. And in discontinuous mode, the output voltage has an even stronger and larger dependence on the load current. So we have variations in load current and in input voltage, and these lead to variations in the output voltage. In addition, we have uncertainties. All the components and element values have tolerances. So we may have plus or minus 10% tolerances, which could cause some variation in the output voltage just from that. So when we account for all the tolerances of all the elements and for the value of Vg and so on, this also causes variations in the steady state value of the output voltage. So what we do is we build a control system that senses the output voltage through this feedback connection. This voltage is put into a summing node that generates what's called an error signal. We subtract the measured output voltage from a desired reference value called Vref, and the object here is to make the output voltage equal to Vref. The difference is called the error signal, and this signal coming out of the summing node is a measure of how much the output voltage differs from the desired value. That error signal is put through what's called a compensator circuit that typically is realized with an op-amp or a similar circuitry to produce a control signal Vc that controls the duty cycle of the transistor. A pulse width modulator, we're going to talk about it later in this week, is a circuit that takes an analog input voltage, Vc in this case, and produces a switched waveform whose duty cycle is proportional to the control voltage. And this control waveform then goes through the gate driver and controls the MOSFET turning on and off. So this circuit, if properly designed, can automatically adjust the duty cycle to attempt to drive the error signal to 0 and make the output voltage equal to the reference. We're going to talk a lot more about design of this feedback loop in Chapter 9. Some applications of control. We nearly always have a control system in any power converter. So in a DC-DC converter, typical application is to regulate the DC output voltage, as I've just described. So the control system will adjust the duty cycle automatically, again, to make the output voltage accurately follow a reference signal. In a DC to AC inverter, we may want to regulate an AC output voltage. So this is similar to the DC-DC case, except that the desired output voltage now is an AC, typically a sinusoid, and so we want that AC voltage to accurately follow an AC reference signal, but otherwise it's the same. In a grid-tied solar inverter, our inverter may actually produce an output current instead of a voltage, but it's the same idea. We adjust the duty cycle to make the current that we put into the grid follow a reference signal. Another case is an AC to DC rectifier, and we often now have requirements on our rectifiers that draw power out of the AC power line regarding the quality of their AC current waveform. In many locations, we're not allowed to build peak detection diode capacitor circuits that draw spikes of current out of the power line at the top of the sine wave. These pollute the power system with harmonics and disrupt the operation of neighboring devices. And so there often are regulations that limit the kind of waveform we can draw out of the power line, and generally require it to be a sinusoid that is in phase with the voltage. So then we build a control system to regulate the current that our rectifier draws out of the power line, and again we will control the duty cycle to make that current follow a reference. So in order to design these control systems, the first thing we need to know is we need to model the dynamics of the converter. So in order to model those dynamics, we need good AC equivalent circuit models, and then we need to be able to solve and understand what the models are saying to guide us to do a good design of the control system. So some applications then of converter modeling. We want to do worst case analysis is one example, where we need to prove that our circuit will work under worst case conditions. So what are the worst case values of the applied signals and of all the components with their tolerances? So we may need to do this for aerospace, often it's a requirement, or in a commercial high volume production we need to do a similar kind of design to get high reliability and high yield from our production line. So for high quality design, we already know steady state models, and one thing we need to do with our steady state model is to ensure that under steady state conditions with all of these variations and tolerances in steady state, that the circuit will perform acceptably well with a high enough efficiency, low enough losses that the temperature rise is not too high, adequate steady state voltage regulation, and so on. And then for our AC control system design, we need AC models that we can analyze and prove that we have stability and a good transient response, a well-behaved transient response under these worst case conditions. So the way a good design practice goes then is we will simulate our equivalent circuit model during preliminary design to really verify that the design works under these worst case conditions. We'll construct laboratory prototypes and make those prototypes work under nominal conditions or with whatever component values are present in the laboratory prototype. We'll then compare the performance of this prototype to what our AC model predicts, and we will have to refine our model until it predicts the observed behavior adequately well. Once we have such a model, then we use it to predict behavior under worst case conditions and improve the design until we can show that the circuit will always work and meet our goals for reliability and production yield and performance. So the objective here then is to develop the tools that we need for this modeling, analysis, and design of the converter control system. And Chapter 7 is about the modeling, Chapter 8 is about analysis of our models, and Chapter 9 continues analysis for the feedback system and then discusses how to design the feedback system using the models from this chapter. So our models of the power converter need to predict how AC variations in things like the input voltage or the load or the duty cycle affect the output voltage under transient and not DC conditions. And another way to say that is, what are the small signal transfer functions of the converter from these input quantities to the output? So what we're going to do in this chapter then is to extend the steady state converter models that you've already learned to include the dynamic elements such as the inductor and capacitor. In the next chapter, next week, we will talk about how to construct the transfer functions of these converters using the models from this week. And in the final week of the course, we'll discuss design of the converter control systems, or Chapter 9. In fact, we're going to take 4 weeks to cover these chapters 7 through 9. Okay, modeling. So modeling is the representation of the physical behavior of some system by mathematical means. And one thing you have to understand is that models are not exact. They're an approximation of what's going on at some level that is adequate to describe what we need to know, but is no more complex than that, so that we don't get bogged down in unimportant details. So we certainly, for example, don't attempt to model what every electron and every wire is doing. We really want the simplest model we can that describes the important things of interest and ignores everything else. And so we make approximations formally to ignore what's not important. And it's best to start with a simple model. The simplest model is best to begin with. And later we can refine the model and add in things that we find are important if we have the time and if those things are found to be necessary to model. But certainly we don't attempt to model everything. Here's an example. And when we talk about modeling the dynamics of a switching converter, here's exactly what the waveforms actually look like. So on the top plot here is the MOSFET gate drive signal of a switching converter. This is actually a buck boost converter. And this VC of T is the control voltage at the input to the pulse width modulator. So these top two waveforms, if I go back to my diagram, it's the VC of T continuous signal here that looks like this, and then this control signal that switches up and down and looks like this. So there is some AC variation in our control signal, and you can see that that causes some variation in the duty cycle. Now the AC variation is slower than the switching frequency, and we're generally talking about variations that happen much slower than the switching of the converter. So this slow variation in VC causes a slow variation in duty cycle. Okay, the second waveform here is the observed inductor current, and it has some switching ripple, but there's an average that if we were working in steady state, we would have a constant average that is the DC component of the inductor current. In this diagram, though, we have some AC variation, and that's causing an the underlying average to vary. So I've sketched here both what the dark waveform is the actual inductor current, and this lighter, more smooth line is what we call the average of the inductor current. It's a quantity that varies, and basically it's the waveform without its ripple. The bottom waveform is a similar kind of waveform for the output voltage. So this is the output capacitor voltage of our converter. It has some switching ripple, and underneath that is some underlying variation in the low frequency component. So we can think about this as saying our control signal has some DC or constant value, capital VC, here might be some DC value, plus some sinusoidal variation that makes VC vary sinusoidally about this DC value. And in response to that, the pulse width modulator makes the duty cycle vary also. So there's some steady state value of duty cycle plus some slow AC variation in the duty cycle. Here's what a typical waveform, such as the actual output voltage waveform of the converter, looks like when we have this sinusoidal variation in the duty cycle. So what's shown here, first of all, is this is the spectrum. So these are the amplitudes of frequency components of the waveforms versus frequency. And this frequency right here is the switching frequency. So we have switching harmonics in the waveform, and so we see a frequency component at the switching frequency and also at its harmonics. So this is twice the switching frequency, 3 times the switching frequency, and so on. In addition to that, there is a low frequency variation at this low frequency modulation frequency. So when we vary the control input sinusoidally at frequency omega sub m, we observe some output variation at frequency omega sub m. Now, the converter power stage is nonlinear in general, and so it generates harmonics. So we have not only omega sub m, but we also see the harmonics of omega sub m from this nonlinear process. And then finally, modulation causes sidebands. So we see sidebands of the switching frequency. So there's one right here at frequency omega s plus omega m. And there'll be sidebands including the harmonics as well. And they extend on both sides of each of the switching harmonics. So we see them spectrum all the way up here. So it's a pretty complicated waveform that comes out of our converter. And so now it's time to simplify our model. We're not going to try to predict all of this, and frankly, we don't care about it all. Generally, when we're designing a control system, what we care about is this. So if you vary the duty cycle at 100 Hertz, what is the resulting 100 Hertz variation in the output voltage? And so this is what we want to predict. And as we've done so far in this course, we generally don't want to predict the switching harmonics. So we want to remove the switching ripple and just model the underlying low frequency variations in the system. So we're going to throw these out. And we will do that by a process called averaging that is a generalization of the way that we have calculated the DC components so far in the course. And this approach does continue to apply the small ripple approximation, but we need to discuss in more detail exactly how to do that in the AC model. And then we also have these harmonics that are low frequency harmonics that are multiples of the modulation frequency. We are going to ignore these or throw them out also and not model them. The reason for that is that otherwise our differential equations that we get for the converter dynamics are nonlinear, and we can't simply take the Laplace transform and find transfer functions. So what we're going to do is similar to what is done in an electronics class in modeling other nonlinear elements such as transistors and diodes, that we construct a small signal model in which we ignore these low order harmonics and linearize the circuit. So then this is in the end the only thing that we want to model. Okay, so the business of averaging to remove the switching ripple. So far in the course, we found the DC component of a waveform by integrating the waveform really over one switching period and dividing by the period. Although that definition assumes that the circuit is in steady state and that the waveforms are periodic. Here what we're going to do is generalize that and talk about a moving average. So if we go back here and look at, say, the output voltage, we will integrate over one switching period, but then make this period of integration, this one switching period integral, move forward in time along the waveform. And what we'll get by doing that is the underlying variation with the switching ripple smoothed out or removed. So formally, this is how we define the average of an AC signal. So the average value of some signal x of t is found with this moving average, where at time t we integrate over one period that's centered at time t. So it extends from t minus half a switching period to t plus half a switching period. And we define the average of the waveform at time t is found by integrating the waveform over this interval and then dividing by the period. What we're going to find when we do that is, and we're going to show that in the next lecture, is that we can write the equations of the converter like this. So for every inductor we're going to have an equation of L di dt is the average voltage on the inductor, where the waveforms in this equation are the averaged values of the inductor current and voltage. Similar for each capacitor. Now this turns out to be a simple generalization of what you already know how to do in the DC case. In fact, if you look at what happens to these equations in steady state, when the transients have settled down, then the derivatives of the inductor currents and capacitor voltages go to zero. And that's what happens when we reach steady state. So in that case, the left-hand sides of these equations go to zero, and what we're left with is the right-hand side equal to zero. And the right-hand side contains an average inductor voltage or an average capacitor current, and these are in fact the volt-second balance and charge balance equations that we already know how to find. And so in fact, the bottom line is all you have to do is take the equations that you already know from volt-second balance and charge balance, and instead of equating these voltages and currents to zero, we equate them to L di dt or C dV dt. So in fact, averaging is a small step from what you already know. Now, I'm going to give an optional lecture where we're going to talk about this approximation in more detail and give it some mathematical foundation, but you can apply it without even understanding that foundation. The more you know, the better, and I hope many of you will choose to watch that lecture. So here's the equations we get. It turns out that the right-hand side is nonlinear. It involves the products of time-varying quantities, such as duty cycle times output voltage, for example. And these are nonlinear processes, this multiplication of time-varying quantities. So we have to linearize this circuit to get, if we want linear differential equations that we can solve as in basic circuit analysis. So the next step is to construct a small signal converter model that is linearized about a quiescent operating point. And this is something we already do, or already know how to do in undergraduate electronics courses. For example, if we think about the equation of a diode. So the diode, physical diode, has this exponential relationship between current and voltage. And if we operate the diode at some quiescent value of current, meaning a DC current, capital I, which might be, say, right there at 2 amps, then we can find the resulting DC voltage from the IV characteristic. That would be this value. And then on top of that quiescent value, if we add some small AC variation that here is called I hat of t, so we vary the current sinusoidally about this quiescent value like this, then in result of that variation, we will see some AC variation in the voltage. That's illustrated here. And we call that variation V hat. And in the small signal model, what we're trying to do is simply find what V hat is in terms of I hat. So in your electronics classes, I hope that you learned how to do that. We linearize the nonlinear IV characteristic of the diode using its slope at the quiescent operating point, and we define a small signal model using a resistor whose resistance depends on the slope. And we can then, from this model, represent the relationship between the small signal AC current and the resulting small signal AC voltage. Okay, power converter has the same thing going on, really. And here's an example of the buck-boost converter, where we know that the output voltage is the input voltage multiplied by D over 1 minus D, and there's a minus sign there also. So the output voltage is a nonlinear function of D. This curve here of output voltage versus duty cycle is not a straight line. So you might then try to do a similar thing. We could say operate the converter with a quiescent duty cycle or steady state value of 1/2, which from solving this expression tells us that we'll have a resulting quiescent output voltage of minus Vg. And then on top of that, we could say, what if we also added some small variation, d hat variation, in the duty cycle? And from this slope, we could calculate the resulting small AC variation V hat in the output voltage that would result. And so to linearize this about the quiescent operating point, we would find the slope of this curve, and from that slope we would know the gain, the small signal gain, from a duty cycle variation to an output voltage variation. Now it turns out that the buck-boost converter is actually more complicated than that. Linearizing this DC characteristic is not enough. We actually have to get into the details of the model and how the L's and C's interact with each other to correctly do this. And we're going to learn how to do that this week. And what I'll say to that is, here is the answer for the buck-boost converter, and we're going to derive this answer. So this may look similar to the DC model of the buck-boost converter that you've already seen. It has the same transformers, a 1 to D transformer and a D prime to 1 transformer, but it also includes the values of L and C, and it also includes some extra generators. These are D hat sources that model how variations in the duty cycle excite variations in the voltages and currents of the converter power stage. We can add losses into this if we like as well. I haven't added them in this particular example. So in the next several lectures, I'm going to develop this model and teach you how to derive an equivalent circuit model such as this. In this brief lecture, I'm going to explain how to derive the averaged AC equations of a switching converter. And we're going to do this by simple extension of the ideas of volt-second balance and charge balance that you already know how to do. We're going to extend those to write the equations of the average voltages and currents under transient conditions. I'm going to explain just how to do it, but not derive where it comes from. This is what you need to know to do the homework, but in the next lecture, which really is perhaps optional, we're going to discuss where it comes from and give a little more idea of the mathematical foundations. So I'm going to explain with reference to this buck-boost converter. So the usual buck-boost converter with an input voltage Vg of t, an inductor current I of t, and an output voltage V of t. So as usual, we start in the usual way. With a switch in position 1, here is the circuit, and we can write the equations for the inductor voltage and capacitor currents. So the inductor voltage, which is L di dt, in the first position is equal to the input voltage Vg. Likewise, the capacitor current, which is C dV dt, is equal to minus the load current during this first interval. At this point, what we previously did was to replace these quantities on the right-hand side of the equation with their DC components and make the small ripple approximation to ignore their ripples. So what we want to do today is still make the small ripple approximation, but don't assume that the quantities are purely DC. Allow them to vary. And so what we will do is replace the quantities on the right-hand side of the equation with their averaged values, where the angle brackets here denote averaging. And I mentioned that on the previous lecture. So say the average value of v of t, where we average over a period ts, is equal to 1 over the period times the integral over 1 period of v of t dt. And the integrating period, there are different choices we can make for the integrating period. The one that I described in the last lecture was that we integrate over a period that is centered at time t, and we integrate a half a period before and after, like this. And what the point of this is that it removes the switching ripple by averaging over exactly 1 period, and what is left is the underlying low frequency component, including the DC component, but also this average can vary during transients. So Vg of t here is replaced by its average, and V of t is replaced by its average. In fact, what this amounts to is instead of writing the DC component, we write the average value. Okay, same thing for the switch in position 2. Here is our usual circuit with the usual equations for the inductor voltage and capacitor current for this interval. We have V of t, and we also have I of t on the right-hand sides of these equations. So we will replace I with its average and V with its average. So we have equations for what the inductor voltage is during each interval. And from those equations, as usual, we can write the inductor voltage waveform, which is one value during the first interval and a different value during the second. The solid dark line here is the actual waveform, including the ripples, and the dashed lines here have ignored the ripple, making the small ripple approximation. And for example, during the second interval, the dark line, or solid line, is V of t, while the dashed line is the average V. So what we do now is we calculate the average inductor voltage. Previously, the average inductor voltage equaled 0 by volt-second balance, but now we're going to let the average inductor voltage equal L di dt, where here we're taking the derivative of the average inductor current with the ripple removed or ignored. So this average inductor voltage is simply d times the value during the first interval plus d prime times the value during the second interval, here and here. And we equate this then to L times the derivative of the average I, and this is our averaged equation that describes the inductor during transient as well as DC conditions. And what this shows is how the low frequency component of the inductor current with the ripple removed will vary over time. Okay, we can do the same thing for the capacitor. Here is the capacitor current waveform. The solid lines include the ripple, and the dashed lines employ the small ripple approximation. So the average capacitor current, again, can be written as d times the value during the first interval, here, plus d prime times the value during the second interval. We collect terms and equate this to c times the derivative of the average V, and we get this equation that describes how the low frequency components of the capacitor voltage will change with time. Finally, we know that to complete the model of the converter, we may have to write an equation for the average input current. And in the DC case, we found the DC component of Ig, the current coming out of Vg. And so for the AC model, we will need to do the same thing. So we express Ig during each interval and write the Ig of t waveform, and we apply the small ripple approximation to it. So when the switch is in position 1, Ig is equal to the inductor current, which we can write by ignoring the ripple in the inductor current and say Ig is the average I during the first interval, and it's 0 during the second interval when the transistor's off. So the average Ig then, here, which is the average or low frequency component of the switched waveform Ig, that average is equal to d times the average I plus d prime times 0. So here's our equation that we get for the average inductor current. So to summarize, we can generalize the ideas of inductor volt-second balance and capacitor charge balance to write the equations of the averaged or low-frequency components of the waveforms without requiring that they're DC, but rather they can vary with time. We employ the small ripple approximation. The equations look very similar to those you've already been writing, but now we allow the waveforms to have AC variations. Okay, in the next lecture, which is optional, we're going to discuss some of the mathematical details and foundations behind averaging. And then in the following lectures, which aren't optional, we're going to linearize these equations that we derived in this lecture and then construct small signal AC equivalent circuit models. In this optional lecture, I'm going to briefly summarize the math behind averaging. So in the last lecture, we talked about the average equation of the inductor, in which L times the derivative of the average inductor current was taken to be equal to the average inductor voltage. This actually follows directly from the definition of averaging and from the defining equation of the inductor. And we can see that as follows. Here we'll start with the equation of the inductor. By definition, L di dt is the inductor voltage with no averaging applied. And so let's then consider what is the derivative of the average inductor current, where we define the average inductor current as in the previous lecture. So the derivative of the average inductor current can be written like this, where inside the brackets is our definition of how we average. And so let's take the derivative. Now we have the derivative of an integral here. We're allowed to interchange the order of differentiation and integration under a certain set of conditions that the mathematicians tell us. First, the function we're integrating, namely the inductor current, needs to be a continuous function so that we can take its derivative. And second, the derivative of the current is allowed to be discontinuous, but it can only have a finite number of discontinuities over one switching period. Well, the derivative of the current is the inductor voltage over L. This is in general a switched waveform in our converters, so it has discontinuities. But if we don't switch too many times per switching period, then we can certainly, or at least if we switch a finite number of times per switching period, then we satisfy the second requirement, and so we're allowed to reverse the orders of integration and differentiation. So that's what we get in this bottom equation then, where we have the integral of the derivative of the current. Okay, now for the derivative of I, what we will do is take this defining equation of the inductor and divide by L. So di dt is the inductor voltage over L. And we can substitute that in here for the derivative. So that's what I've done here. Okay, now we can just rearrange terms. Actually just take this L and put it over here to get L di dt, and on the right hand side what we have is in fact the average value of the inductor voltage. So we integrate over one period and divide by the period, and we get the average voltage like this. So what we've shown then is that the averages obey the inductor equation as well. Now you might say, well, that's obvious, but in fact it isn't. We have to show it. We don't have any extra terms, and the actual value of L is unchanged by averaging. You can apply the same arguments to capacitors, and so for a capacitor with the same arguments we get a similar kind of equation. Okay, so let's look at the mechanics then of actually computing this average formally. The first thing I should say is that this definition of the average is not synchronized with the beginning of the switching period in general. This moving average is a function of time that doesn't hop from one switching period to the next. So what I've drawn is an inductor voltage waveform, VL of t, where the switching period is starting right here. And then this is drawn at some arbitrary time t that doesn't coincide with the switching period. It's right there. And so our averaging interval then extends 1/2 switching period before and after this time t. Okay, so this is the interval that we have to average over to compute the average value of the inductor voltage at this time t. To compute this average, if we include the ripple, then we have, the computation gets more complex. And so what we do is apply the small ripple approximation. And what that small ripple approximation effectively says, or what we will assume, is that the values of continuous quantities are taken to be constant over this interval. That the change over this small switching period is taken to be small. So the inductor voltage during the first interval is the input voltage Vg. If it has ripple, we're going to ignore it, and we're going to replace this Vg of t with its average, the average Vg. Okay, so the d interval is this one right here. The d prime interval is the rest of the switching period, which there's some of it over on the left side and there's some more on the right. So during the d prime interval, we also assume that the inductor voltage during those two intervals is the same. So during the second interval, the inductor voltage is the output voltage V, and we will take it to be its average, or average V, which is the same value here as it is here. And that's the assumption that is made with the small ripple approximation. Here's the same diagram. With that assumption then, the average inductor voltage is D times this average Vg for the D interval, plus D prime times the average V, both there and there, add up to a total net time of D prime Ts. And so we get D prime times the average V for the second interval, and therefore L times the derivative of the average inductor current is D times the average Vg plus D prime times the average V. A little more about this business of averaging. We can view averaging, or this way that it's been defined here, as an operator. And this is an operator that removes the ripple but preserves the underlying low frequency components of the waveform. And it's an important thing to do because it makes our equations tractable and simple, so that we get a simple set of equations or AC equations for the converters. And it's removing the switching frequency components while preserving the magnitude and phase of the low frequency components of the waveforms. So really we can think of this averaging operation as being a type of low-pass filtering, where we're removing the switching harmonics of the waveform and preserving the low-frequency components. And we can actually take the Laplace transform of this averaging operator to see what it does in the frequency domain. So we'll do that in a second, but first, to just plot it, these are computer-generated plots, which I've shown 2 lectures ago, but they're real simulations of a buck-boost converter. The top waveform or top axes are the gate drive, showing the duty cycle changing from a lower value to a higher value. The middle and lower waveforms are the resulting inductor current and capacitor voltage waveform for the converter. The dark waveforms that have ripple in them are the actual simulated current and voltage, including the ripple. And then the underlying thinner smooth curves are what is calculated by the computer applying this definition of averaging. So what I've done for real actually here is to take the waveforms with ripple, apply the averaging operator to them with the computer simulation, and plot the result. And you can see that the average quantity really does go through right through the middle of the ripple, and it is in fact the correct way to calculate this moving average. One other small point I'll make is that if you change the interval of integration, so instead of say integrating from t minus ts over 2, suppose we just integrate from t to t plus ts. What you're effectively doing is just shifting the answer in time, and it would shift the average forward or backwards in time depending on the interval of integration that you choose. So centering the integral of integration right at time t is the correct one that adds no phase shift to the waveform and gives us a waveform that actually goes through the middle of the ripple. If you're up on your Laplace transforms, you can take the Laplace transform of this averaging function, and actually here's the answer. We have the 1 over ts term out in front that is this. Integration in the Laplace domain is dividing by s, which gives us this s in the denominator. And then the two exponentials in the numerator are what make what take care of the limits of integration and make the integration period go from ts over 2 in the past to ts over 2 in the future. Okay, you can let s equal j omega and turn this into a transfer function and plot it as a bode plot. We're going to talk about bode plots next week, but for now, I guess if you're not familiar with that, you'll have to take my word for it. When we do that, we find that this g-av of s transfer function with s equals j omega turns out to be this. It's a purely real number. There is no imaginary part, so there is zero phase shift in this operator. And it has a magnitude whose plot looks like this. So here I plotted the magnitude in decibels versus frequency on a logarithmic scale, like in a bode plot. And what you can see is that at low frequency, say for example at 1/10 of the switching frequency, the magnitude is 0 dB, or basically 1, and there's zero phase shift, so the signal passes through this averaging operator unchanged. At the switching frequency, the magnitude of this quantity turns out to be 0. So it's like a notch filter that completely removes components at the switching frequency, and therefore it removes the switching ripple. It also removes harmonics of the switching frequency, so at twice and 3 times the switching frequency and so on, the magnitude is 0. So switching harmonics are completely removed. So this is really what we want. And this averaging operator then preserves the low frequency components even at half of the switching frequency here. The magnitude is a little less than 1, so there is some change, but it's not that great. But when we get past half the switching frequency, there's a big change in the waveforms, and in particular the switching harmonics are removed. So you can debate whether we want to say that the operator doesn't change the result at half the switching frequency or not, but certainly at sufficiently lower frequencies, this averaging operator does not change the components of the waveform. Okay, we can apply the same arguments to the capacitor then. What I've drawn here, though, is not the capacitor waveform at some arbitrary time t, but I've simply started at the beginning of one switching period and drawn the waveform over one complete switching period. And this is what was done in the last lecture. So if you like, you can draw the waveforms as I did previously for the inductor at some arbitrary time t in the middle of the switching period, but the answer that you get for the converters and cases that we're considering in this course is unchanged. You get the same answer if you just talk about what is the average over one switching period, and it's simpler to do. And so from now on, that's what we're going to do. What I would caution you is to say that for some cases that are more advanced, but that we're not going to consider in this course, it is important to carefully derive the average as we did for the inductor waveform. And in particular, I'm thinking about current mode control. So for those of you who know what current mode control is, to get an up-to-date and accurate model in current mode control, we do have to carefully draw the waveforms at an arbitrary time t like this. But that's beyond the scope of this course. So the process of averaging is indeed well-founded mathematically, and it works very well for the continuous conduction mode. Here are the equations that we derived previously for the buck-boost converter example. So these are the averaged AC equations of the converter. We call them large signal or nonlinear equations for the reason that the right-hand sides of these equations involve the multiplication of time-varying quantities. For example, here in the inductor equation, we have the duty cycle d of t multiplied by Vg of t. We have d prime of t multiplied by the average V of t. Whenever you multiply time-varying quantities together, you can generate harmonics. So for example, if d of t and V of t are both sinusoids, then when we multiply, we get terms like sine squared that has harmonics, and the components are not simply at the original frequency. So in fact, multiplication is a highly nonlinear function. And so this is a set of nonlinear differential equations. To apply Laplace transforms and talk about transfer functions, we need to linearize them. And so that's what we're going to do in this lecture. Now, how do we linearize a nonlinear equation? The way this is done classically in electronics is to construct a small signal model about a quiescent operating point. Another way to say that in mathematical terms is that we could construct a Taylor series expansion of the nonlinear function and take the linear terms that gives us a linearization of the function about some given operating point. So here's how we do it. Let's consider that we drive the inputs to the converter first with some DC or steady state values. So the duty cycle and Vg are the independent inputs to the converter system. So let's consider first that we apply some steady state or DC value of duty cycle that we'll call capital D. So we let d of t equal capital D. Likewise, we apply a DC or steady state or quiescent value of Vg that we'll call capital Vg. So we let the average Vg equal capital Vg. Incidentally, quiescent means quiet, and when we talk about a quiescent operating point, it's the same thing as saying we're at the steady state or DC values of the converter. So if we apply these DC inputs to the converter, then the converter will go through some transient, like we talked about early in the semester, and eventually the transient will decay, and we'll be left with a converter operating at its steady state operating point. So in that case, the average inductor current and average output voltage and average IG will go to their DC or quiescent values that we already know how to find. We solve the DC equivalent circuit models that we've talked about in previous weeks to solve for the DC values of these quantities. For the buck-boost converter without losses, here is the answer that we had. Okay, so this defines the quiescent values or steady state values of the voltages and currents within the converter in response to these applied constant inputs. Next, what we're going to do is to consider what happens if we add some small AC variation to the inputs. So now suppose we let the average VG equal this quiescent value, capital VG, plus a small AC variation about that quiescent value that we're going to call VG hat of T, like this. Likewise, we could let the duty cycle D of T be equal to the quiescent value capital D plus a perturbation D hat of T, that is a small AC variation as well. So if we apply that to the inputs, what we would expect is that the voltages and currents in the converter would also have some corresponding small AC variations in them, so that we could write, say, the average I, inductor current, as being equal to capital I, the quiescent value, plus I hat of T, the perturbation or AC variation in average I. Likewise for V and IG. Okay, now the small signal assumption that we will make, and what allows us to linearize the equations, is to assume that the perturbations on the left side of these inequalities are very small in magnitude compared to the quiescent values or DC values on the right-hand side. So, provided that all the perturbations are small compared to the quiescent values, then we will be able to linearize the nonlinear equations and construct small signal linear AC models for the converter. Okay, the lecture notes have slides for this next part, but I'm going to actually just work them out by hand. So what we're going to do is for each of these AC quantities, I'm going to plug in the perturbed expressions. So on the left-hand side, we get L times the derivative of the average I, which we're going to let be equal to capital I plus I hat of T. And to keep the equation simple, I'm not going to write the of T part, but it's assumed to be here. Okay, on the right-hand side of the equations, D of T we're going to let be capital D plus D hat of T. And the average VG we're going to let be equal to capital VG plus VG hat. Okay, then we have to add D prime. So what is D prime of T? Well, if D equals capital D plus D hat, that means that D prime, which is 1 minus D, would be equal to 1 minus the quantity capital D plus D hat, which is then 1 minus capital D minus D hat, and we're going to write that as capital D prime minus D hat. So capital D prime is equal to 1 minus capital D. Okay, people often forget the minus sign in front of the D hat. If D hat makes D bigger, then it makes D prime smaller, so D prime becomes capital D prime minus D hat. Okay, so for this second term then, D prime we will write as capital D prime minus D hat, and the average V we will write as capital V plus V hat. Alright, let's multiply this out. On the left-hand side, what is the derivative of capital I? Well, capital I is defined to be DC, so its derivative is 0. So the left-hand side becomes L times DI hat dt. Okay, on the right-hand side, we have a lot of terms to multiply out. But what I will say is that we get three different kinds of term. The first kind of term involves the products of DC quantities. So here we have a capital D times capital VG, and we also have a capital D prime times capital V. So these terms are what we call DC terms. They're all constants. The second kind of term that we have is the product of a hat quantity with a DC quantity. So for example, we have D hat times VG. We have capital D times VG hat. There's a D prime, or capital D prime times V hat. And there's a minus D hat times capital V. So these involve a DC quantity times a small AC quantity. We call these first order or linear AC terms. And then the third kind of term that we have involves the products of two hat quantities. So we have a D hat VG hat term, and we have a minus D hat V hat term. So these involve the products of two time-varying AC quantities. The hat terms are small, or we're taking them to be small, so this is a small number times another small number. We call these second order terms. And they're nonlinear because they involve the products of time-varying quantities. Okay, what do we do with these different kinds of terms? Well, we treat each of them separately. First of all, for the DC terms, what do the DC terms equal in this equation? Well, if you solve the DC model of the converter by applying volt-second balance to the inductor, what you get is that these DC terms are the average voltage applied to the inductor in steady state, and by volt-second balance they equal 0. So the DC terms, in fact, are equal to 0. You could also see that by equating them to the DC terms on the left-hand side of the equation. The derivative of capital I was 0, and we got 0 on the left side of the equation. So the DC terms add up to 0. Now, how about the second order terms? Well, we're going to make the small signal approximation now, which says that the product of two hat quantities is a very small number. This is a small number times a small number, which is a very small number, and the small signal approximation or small signal assumption says that we will throw these terms out. So okay, they're not exactly 0, but they're second order or higher order terms that we will neglect. And so the first order or linear terms are all larger than the second order terms because they involve a hat quantity times a large DC quantity. So for example, here we have D hat times VG hat. That is much smaller than D hat times capital VG. So we will retain only the first order terms, and our equation then becomes L times DI hat dt on the left hand side equals the first order terms on the right hand side, which are capital D times VG hat plus capital D prime times V hat plus D hat times capital VG minus V. And this is the desired result. This is the linearized small signal equation for the inductor. Okay, here is the capacitor equation, and we can do a similar process for it. So we'll write C times the derivative of capital V plus V hat is equal to minus D prime, which is capital D prime minus D hat, times the average I, capital I plus I hat, minus the average V, which is capital V plus V hat, over R. We can simplify this. On the left-hand side, the derivative of the dc, capital V, is 0, so we get c times dv hat dt on the left. And on the right-hand side, we'll get dc terms that are minus d prime capital I minus capital V over R. So these steady-state terms equal 0. Then we get first-order terms, so there'll be a d hat times capital I, and there'll be, let's see, minus d prime times I hat, and then there'll be a minus v hat over R. So these are the first order terms. And then we have, let's see, one second order term that would be d hat times I hat. So we'll throw out the second order terms, making the small signal approximation. The DC terms add to 0. And finally we get c dv hat dt is equal to the first order terms. And this is our small signal equation for the capacitor. Finally, for Ig, we need to linearize this equation as well. So the average current Ig is capital Ig plus Ig hat. This is equal to the duty cycle, capital D plus D hat, times the average I, capital I plus I hat. If we multiply this out, on the left side we have capital Ig plus Ig hat. And on the right-hand side, we have DC terms, that would be capital D times I, plus small signal AC terms, D hat, capital I, plus capital D times I hat. And we have second order terms, which in this case would be just D hat times I hat. For this equation, we don't have a derivative, and there are DC terms on both sides of the equation. So what we can write, in fact, is we can equate the DC terms on both sides and write that capital Ig equals capital D times I. And this is, in fact, what we get out of our DC model for the converter. Then we'll throw out the second order terms, making the small ripple approximation. And the other equation we'll get is equating the first order terms on both sides of the equation, so that Ig hat equals D hat times I plus capital D times I hat. And this is the small signal first order AC equation for the input port of the converter. In the small signal equations, such as this Ig hat equation, we take the capital quantities, or the quiescent terms, capital I and capital D for this example, to be givens. We solve the DC model at a quiescent operating point to find these things like capital I and capital D. And then in the AC small signal model, to solve for the hat quantities, the DC quantities are just constants. We treat them as constants, they're already known. And the variables in the small signal AC equations then are the hat quantities. Okay, so this process of perturbation and linearization allows us to construct small signal AC equations for the converter. The next step that we're going to do is to take these equations and construct a small signal AC equivalent circuit model in the next lecture. In the previous lecture, we perturbed and linearized the converter equations, and we derived this set of three small signal equations for the buck-boost converter. We're now in a position then to construct an equivalent circuit model for the converter. And the process for doing this is very similar to the way we've been constructing the DC equivalent circuit models. We just have some different terms now. But in these equations, we have signals in the converter that are the hat quantities. Again, the capital values are taken as constants or parameters in the model that are known. So they're known given quantities, and it's the hat quantities that are signals in our equivalent circuit. So as in the DC case, what we're going to do is construct an equivalent circuit to go with each of these equations. So the equations are treated as loop or node equations of the converter equivalent circuit model, and we will take then the three circuits that we get and combine them with DC transformers, actually in this case they're AC transformers, to get the final equivalent circuit model for the converter. So again, the lecture slides have the material that I'm about to present, but I'm going to actually draw them by hand on the screen to illustrate the process. So here is the first equation, which we got from the averaged inductor equation that was then perturbed and linearized. So this is in fact the small signal AC equation that describes the loop in the small signal AC model that contains the inductor. So we're going to start on the left side of the equation with an inductor, and we recognize that L times di hat dt is the voltage across the inductor in our small signal model. So I'm going to just put an inductor in the middle of the circuit here, having value L with a current I hat flowing through it. And therefore the voltage across this inductor with this polarity would be L times di hat dt. Okay, and this equation says that inductor voltage, L di hat dt, is equal to a sum of three terms, which we recognize as voltages, and these are the voltages around the loop then, that is the Kirchhoff voltage law or loop equation for this part of the model. D times Vg hat is a dependent source in our model. It depends on the input voltage Vg hat. This is actually the input AC variation in Vg that is applied to our small signal AC model. And so that gets multiplied by the constant or the value D, and we're going to represent this with a dependent source of value D times Vg hat. The next term, d prime times v hat, this is another dependent source that depends on the output voltage, v hat, in our AC model. And so I'll draw a dependent source on the output side here of value d prime v hat. Okay, now going around the loop, this term has the same polarity as the Vg hat term, so as we go around the loop we have to go through plus to minus in the same direction, so this is actually minus on top and plus on the bottom. And finally we have another source, capital Vg minus V, then all times d hat. Now in this equivalent circuit or the AC model, d hat is an independent input to the circuit. It's actually the control input of the system. And so I'm going to draw all the d hat sources as independent sources, so round sources. And this is d hat with a gain of capital Vg minus V. Okay, this one also is a plus sign, and so as we go around the loop it's minus on the left and plus on the right. So this is the equivalent circuit then to go with our inductor equation. Okay, let's do the capacitor. Here's the equation we got from the small signal capacitor equation. C dV hat dt we recognize as the current and the capacitor in our model. So I'm going to draw a capacitor here, a value C with a voltage V hat across it, so that it has a current of C dV hat dt. Okay, this equation says that that current is the sum of three other currents. So this is a node equation, and we'll draw a node here where the capacitor is connected. And we have three currents besides the capacitor current flowing in that node. The first term, minus d prime times I hat, is a current that depends on the inductor current I hat from the previous circuit we just drew. So this is a dependent source, and I'll put a dependent current source of value d prime I hat. Okay, this current, because of the minus sign, goes out of the node, not into the node, and so its current points down. The second term is the load current. We have actually it's the AC variation in the load current, and so we can recognize V hat over R is the current through a resistor of value R having a voltage V hat. And because of the minus sign, this also flows out of the node, so that's consistent with a resistor. And then the last term is another D hat source. This is a current that depends on the control input D hat. So we will draw an independent source for the control input. With the plus sign, this flows into the node, and it's a value capital I times D hat. So here is the equivalent circuit to go with the capacitor equation. Finally, our last equation is for Ig hat. Ig hat we recognize is the current coming out of the Vg hat source at the input of our converter. So I'm going to draw a voltage source of value Vg hat. So this is the independent input to our small signal AC model that has Vg variations. And the current coming out of that source is Ig hat. And this equation says that that current is equal to a sum of two other currents. So this is also a node equation. Here's the node. And we have the current D times I hat. This is a dependent source that depends on the I hat inductor current elsewhere in the model. So we'll draw a dependent source for it. And with a plus sign, it goes out of the node. And then I times D hat. This is another control source, D hat source. So it's an independent input that comes from the control. From the plus sign, it goes out of the node, and its value is capital I times D hat. So here is the model for the input port of the converter that we get from the Ig hat equation. Okay, now we can put all of the circuits together. So here are the three circuits. In the middle is the first inductor loop equation. On the right is the capacitor equation, and on the left is the Ig hat equation that we constructed. And they're placed together. And just like in the DC model now, we can recognize that the dependent sources behave as effective transformers. And so these were DC transformers in our DC model. I'm going to actually represent them as AC transformers here. Put a squiggle little AC symbol through the transformer. This denotes really that it's an ideal transformer model and not a physical transformer. It's really the same as the DC transformer. The little AC squiggle helps us keep track of the fact that this is the small signal AC model, so quantities like capital VG or capital V are simply constants in the model and not actual signals, and it's the hat quantities that are the AC signals in this circuit. Okay, so we have a 1 to D transformer from these two sources that's shown here, and we have a D prime to 1 transformer here from these sources. Because this d prime v hat source is minus on the top, whereas v, the reference polarity of v, is plus on the top. The dots are reversed on this second transformer, as shown here. Okay, so construction of the equivalent circuit model for the small signal AC equations proceeds in a very similar manner to what you've already learned for the DC model. And once we have the small signal AC equations, then I think we can proceed in the usual manner to construct a small signal AC model. Just for reference, here are the results for the three basic converters. The first shown here is the buck converter, and the AC model contains a buck type transformer in the AC equivalent circuit. It's 1 to D. It has some D hat sources and the output LC filter. For the boost converter, we get the inductor on the left side. There's a D prime to 1 boost type transformer in the middle of this AC model, and there are D hat sources around it. And finally, the buck boost converter has both a buck and a boost transformer, very similar to the DC model. We have 3 D hat sources, and this is in fact the model that we just derived. So we can derive the basic models, or the models of all the basic converters. You will do homework where you will derive one of these, and we're in a position now to be able to use these models and solve for things like the small signal transfer functions of the converter. Here is the diagram of a basic control system feedback loop that I introduced at the beginning of this week. So the goal now, or for this week, has been to model the elements around this feedback loop that we can use in our upcoming weeks to design the control system. So what we've done so far this week is derive an AC equivalent circuit for the switching converter that models its dynamics. So now we have that. Let's look at the rest of the loop. The feedback connection, summing node, and compensator are generally built with analog circuits such as op-amp circuits, and I'm going to presume that you already know how to solve those and design them from other classes. But the thing that's missing is the pulse width modulator, and so we need to take a few minutes now and discuss how the pulse width modulator works and how to model it. So the pulse width modulator is a circuit that has an analog control signal at its input, we're calling VC, and some smooth signal, and its output is the gate drive signal that switches high and low. When it's high, the MOSFET is on. When it's low, the MOSFET is off. And the duty cycle of this waveform is supposed to be proportional to the control signal VC. So let's talk about what is that relationship between the duty cycle and the analog input VC. Here is a common way to build a pulse width modulator. We have a sawtooth wave generator, which is an oscillator, and it produces a signal such as this one. It's also sometimes called a ramp generator. So it makes a periodic signal whose period is the switching frequency here. So this is the switching period, T sub S. And in fact, this sawtooth wave generator is what sets the switching frequency of the switching converter. Here I've drawn this sawtooth waveform, V saw of t, as being this function that starts at 0 and it increases linearly with a constant slope up to some maximum value V sub m. At the end of the switching period, then it jumps back down to 0 and starts over again. The sawtooth wave is put into an analog comparator circuit where it is compared with this control input, the analog input VC of t. VC of t is this waveform right here. The function of the analog comparator is that it compares the two analog input signals at its plus and minus input terminals, and it produces an output logic signal that is high when the plus input is greater than the minus input, and otherwise it's low. So this PWM output then will be high here until at this point the sawtooth and the control input are equal. After that point, the sawtooth will be greater than VC, and the logic output will switch low for the rest of the switching period. So the output of the comparator is then this logic signal having a duty cycle of D. What is the equation between the input and output of the pulse width modulator? Well, if the sawtooth waveform is linear, so it has constant slope, then we can write that the duty cycle is actually linearly proportional to the control input VC. And you can compare or look at just a few different cases. Suppose VC is 0, then we'll switch at the very beginning and our duty cycle will be 0. And on the other hand, if VC is equal to the peak value Vm, then we won't switch until the end of the period and our duty cycle will be 1. And with a straight line or linear sawtooth, the duty cycle will vary linearly in between those two extremes. So we can write then that the duty cycle is the control input divided by the peak amplitude of the ramp, V sub m. Sometimes commercial sawtooth or pulse width modulators have sawtooth waves that start at some DC bias or some value greater than 0, and in that case we need to subtract that bias from VC in this formula. So here's that equation again. If you like, we can perturb and linearize this equation. So we let VC equal capital VC plus VC hat. Let D equal capital D plus D hat. If you plug those into here, we get this expression. And from these we can see that the quiescent or steady state value capital D is equal to capital VC over Vm. This is in fact, in practice, how the quiescent duty cycle is set by the DC component of the control voltage VC. And likewise, D hat is equal to VC hat over Vm. So the block diagram of the pulse width modulator then is a gain equal to 1 over Vm. And in a small signal sense then, VC hat goes in and D hat comes out. I should note one other thing. The pulse width modulator effectively samples. It inherently samples, which means that we have one duty cycle per switching period. If we go back and look at these waveforms, the duty cycle is determined only at this point right here. And there is simply one value of duty cycle here over each switching period that is proportional to the voltage VC sampled at that instant. It doesn't matter what VC does at other times. So we can have things going on here at other times and they won't affect the duty cycle. Now you might say, well, suppose we actually had variations that did this and made it switch many times. That's actually an undesirable thing. It causes a lot of switching loss. It can happen when there is noise in our control signal, but we do everything we can to eliminate it. One thing that's often done in commercial pulse width modulator chips is that there's a latch driven by this comparator. The latch gets set by the sawtooth wave generator at the beginning of the switching period, and it gets reset by this comparator signal, and then the output of the latch is this signal that goes to the gate driver. What this does is it sets the latch here to turn the FET on, or MOSFET on, or whatever our switch is. At this point, the transistor's turned off, and once it's off, no amount of noise can turn it back on again. Okay, so we have sampling then. There is one value of duty cycle for every switching period, regardless of VC, and we have a sampler built in. Sampling is actually beyond the scope of what we're going to talk about in this course, But what I'll say is that we must restrict the bandwidth of our control system to be sufficiently less than the Nyquist rate, which is half the switching frequency or half the sampling rate. Models of the modulator that don't account for sampling, therefore, are not going to be accurate except at frequencies that are sufficiently less than this Nyquist rate. One quick summary slide, something sampling does is it repeats the spectrum of the signal at the switching frequency and its multiples, and so we get something that is known as aliasing, where if the original signal has frequency content at DC and low frequencies, that frequency content gets folded by aliasing up to higher frequencies at about the switching frequency and its harmonics. So we're not predicting that in our models, and in fact, when there is aliasing, generally bad things happen to our control system, and so we don't want that to happen. Here is a plot of the effective transfer function of the zero-order hold circuit, which is what the pulse width modulator behaves as, that I've described so far. And so it has behavior at the Nyquist rate and higher, and generally what we want to do is restrict our bandwidth to be sufficiently less than that, and at these lower frequencies the modulator essentially has a constant gain that is the one we've already discussed, the 1 over V sub m. So for frequencies sufficiently less than the Nyquist rate, we can model the pulse width modulator with a simple gain block with a gain of 1 divided by the peak-to-peak amplitude of the sawtooth. And this is the model that we're going to use then in our control system designs that are coming up in the future weeks. In this lecture, we'll discuss what is known as the canonical circuit model. All PWM continuous conduction mode DC-DC converters perform the same basic functions, and as a result, their equivalent circuit models have the same general form. And the canonical circuit model is a way to represent that general form. So basically, you can use the canonical circuit model for any converter, and then we just plug in the specific element values for whichever converter you're using. One of the uses of the canonical model is that we can solve larger system problems in a generic sense for any converter, and then plug in the detailed parameter values for whichever converter we're using to apply it to our particular situation. The canonical circuit model also is actually a way to solve the circuit for the transfer functions through circuit manipulations rather than doing algebra on paper. And so I'm going to illustrate how to do that also. So these basic functions are this. First of all, the DC-DC converter transforms the voltage and current levels, ideally with 100% efficiency, and therefore we expect the model to contain DC transformers that represent that. We have low-pass filtering of the waveforms from the inductors and capacitors that are really there to filter the ripple, but they also filter signals at other frequencies as well. So the V hat and D hat variations get filtered by the L's and C's in the converter also. We can control the circuit by variation of the duty cycle, and so the canonical model has sources that depend on the duty cycle variations, D hat. So we have these independent sources in the model of any converter, and therefore all of these elements should be present in any of our converter equivalent circuits. So here is a development of the canonical model based on simple physical principles. So again, we said this first order property that we're trying to obtain is the conversion ratio M of D with this effective DC transformer function. And so we will start our converter model by building it up beginning with this DC transformer. So the effective turns ratio is the converter conversion ratio M of D. This conversion ratio is a function of the quiescent duty cycle capital D, so that it will vary if the steady state duty cycle varies. Here I've also illustrated the DC input voltage, capital VG, and the DC output voltage, capital V. So solution of this model at this point says that capital V equals M of capital D times capital VG. The next thing we will do is introduce variations in VG. So our power input source now we will write as capital VG plus VG hat. So we can have variations in VG, and to first order what happens is that we would expect those variations to pass through the same conversion ratio and cause V hat variations in the output. At this point what I'm doing is drawing the ideal transformer symbol containing both a DC line so that it passes DC and an AC line in it, so that we are now modeling how it passes the AC variations as well. So effectively what we've done here is combine both the DC and AC quantities into a single equivalent circuit model, which really combines the DC models we talked about in previous weeks with this week's AC models. The third step is introduction of an effective low-pass filter. So the inductors and capacitors that filter the ripple also filter the variations that come from VG hat. In the canonical model, what we do is we push all the inductors and capacitors to the output side of the equivalent circuit, and so we have some effective low-pass filter there. It may turn out that the element values in this low-pass filter are not the same as the actual values in the converter. We're going to see in the example in a couple of minutes that we push an inductor through the transformer turns ratio, and the inductor then becomes a function of D in this effective low-pass filter. So it is an effective low-pass filter that does depend on the values of L and C, but it's not, the values may not be exactly L and C. The next step is to introduce variations in the duty cycle, or the control input. So now we will represent the duty cycle as capital D plus D hat. Capital D affects the conversion ratio, or transformer turns ratio, whereas the D hat causes introduction of control sources. So we have some independent sources, D hat sources. In the canonical model there are two sources. One is a voltage source of value E of SD hat, and the other is a current source of value J of SD hat. In the canonical model we push all of the independent sources to the left side of the model, so we have both the VG sources and the duty cycle sources on the left. Okay, we can talk about transfer functions that are predicted by the canonical model. If we look at this circuit as it's drawn right now, we have an output voltage, the AC output V hat, and it is a function of the two independent inputs, the VG hat input and the D hat input. So in general we can express the output as a superposition of terms that come from the two different inputs. So there are some coefficients when we apply superposition. The coefficient of VG hat we call the transfer function GVG of S, and the coefficient of D hat we're going to call the transfer function GVD of S. And to find one of these transfer functions, you set the opposite source to 0. So for example, to find GVG, what we do is, this is the transfer function from VG hat to V hat, and it's found under the conditions that the other input, or D hat, is set to 0. Okay. So in order to calculate that, we can just look at the circuit and see what the canonical model predicts. If we set d hat to 0, that will make this d hat voltage source into a short. Setting d hat to 0 makes the current source into an open. And then we have the VG hat source connected up to the primary of the transformer. I would also note that to find AC transfer functions, we set DC quantities to 0, or DC biases. So the capital VG will be 0, capital V will therefore be 0 also. This doesn't mean that the DC component of VG is 0 in the actual converter. It simply means that in order to solve for this transfer function, we set the DC quantities in our model to 0. Okay, so with VG hat applied across the primary of the transformer, the voltage at the secondary side will be VG hat multiplied by the turns ratio M. That voltage gets multiplied by the transfer function of our low-pass filter, so that the voltage at the output will be M times that transfer function times VG hat. So then this transfer function from VG hat to V hat is M times HE of S, like this. Likewise, to find the control to output transfer function, GVD of S, this is found as the transfer function from D hat to V hat under the conditions that we set the other source, VG hat, to 0. So let's set VG hat to 0 here, and capital VG is 0. VG hat is set to 0, so we get a short circuit at the input of our converter. That shorts out the current source, and therefore the voltage across the input of the transformer is E of S times D hat. The voltage coming out of the transformer then will be the turns ratio M times ED hat. And the voltage at the output of our converter then would be this quantity multiplied by the effective low-pass filter transfer function. So we get M, or HE of S times M of D times E of S times D hat. So this is the control to output transfer function GVD, as shown here. We can solve other quantities here if we want as well. For example, we could find the input impedance or the output impedance, and we'll be talking about those later. Okay, here is the buck boost small signal model that we previously derived. Let's try to manipulate this into canonical form. So in order to do that, we need to push all the D hat sources or independent sources to the left, to the input side of our model. And we need to push the L's and C's to the right. And then finally in the middle we need to combine the transformers. So let's do that. I'm going to do it one step at a time. And what we'll do is we'll take this current source and push it through the transformer. When we do that, since the dots are reversed on this transformer, it reverses the polarity, so it will point down. And then we also have to divide by D prime, this turns ratio, so that on the primary side of this transformer, we get I D hat over D prime. I'm also going to push this voltage source through to here. Okay, the voltage source is in series with the inductor. We can write them in any order, so we can just push this straight through the inductor. And then when we push it through the turns ratio of this transformer, we'll have to divide by D. So this voltage source would be VG minus V over D times D hat. Okay, that's shown on this slide. Here's the current source and here's the voltage source. The next thing to do is we need to push this current source past this inductor. Now that's maybe not so obvious how to do it, but here's the trick. What we do is we break this path and connect the current source there. Now, you can't just do that. In order to compensate for connecting the current there instead of here, we need to put another current to compensate. And basically, we're taking this current and putting it into this node where it doesn't belong. So we need to take the current back out of the node and put it where it does belong. And this current source then is the same value as that one. It's capital I d hat over d prime. So I've shown that right here. My claim then is that we're allowed to do this because the loop and node equations of this circuit are unchanged. Since we put the current into the node and then take it back out again, we effectively don't change the node equation there. Now, what do we do with this? We can take this second current source and push it through the transformer to here. And in the process of doing that, we would multiply by d, the turns ratio. So this becomes d over d prime times capital I times d hat. Okay, so that takes care of that one. What do we do with this current source? Well, there's a trick for that also. What we have to do is make a Thevenin equivalent of this inductor in parallel with this current. So we have basically this between these terminals here. And let's see, we have an impedance of SL and we have a current going that way of I d hat over d prime. So this is we can view this as a Norton equivalent type circuit. We need to turn it into a Thevenin equivalent circuit. So it would be an impedance in series with a voltage source. And the voltage source would be the open circuit voltage between these terminals. So it will be plus on the left and minus on the right. And it will have a value equal to the current times the impedance. So SL times capital I over d prime times d hat. So this is a Thevenin equivalent model for this network, and we can put that in place of this. So that's what we have here. Here's the Thevenin equivalent voltage and inductance, and looks like I haven't pushed the current source through the transformer yet. Next step, we'll push this current source through the transformer as I described previously. And once we get it here, we will further simplify by trying to push it past this voltage source. So that's on the next slide. Here is the current source written there, and to push it past the voltage source, we do the same trick that we did with the inductor. We're going to break this connection, put the current source into this node, and then take it right back out again and put the current into the node where it belongs. Okay, so this further simplifies the circuit. We now have two current sources in parallel that we can add. So they make a composite source that would be I d hat times 1 plus d over d prime. And then as for these, we have a voltage source in parallel with a current source between these terminals. Okay, what is the IV characteristic between these terminals of the voltage source in parallel with the current source? Well, in this case, the voltage source wins and the current source makes no difference. The independent voltage source holds the voltage between these terminals to be the given value regardless of the current. So in fact, you can just ignore the current source. Okay, last step, we will push the inductor through the transformer. We'll push this voltage source through this transformer. When the inductor gets pushed through the transformer, we have to divide by the turns ratio squared, or d prime squared. So we get this. Here is the effective low-pass filter has the inductance over d prime squared plus the capacitor. The two transformers are now combined, and the sources are combined as well. So we got two voltage sources that I then combined, and we have the current source. Okay, an interesting thing happened when we combined the two voltage sources. One of the voltage sources depended on the inductor impedance, and it picks up an S times L factor inside it. So the coefficient of d hat is now frequency dependent, and it has terms that depend on S. In general, the E of S and J of S coefficients of the d hat sources can be functions of S. And in this case, we picked up the factor of S by pushing a current source past the inductor. Here is that E of S coefficient for the E of S d hat voltage source. We can actually use the steady state relationships for this converter. For example, V is the output voltage as a function of the input voltage Vg in duty cycle, and our expression for the inductor current, capital I, can be simplified from the steady state model. And when we do that, we can then express E of S in this form. Okay, this frequency dependence is actually causes control problems, and we're going to talk about those in the next chapter. So here then is the canonical model. For the basic buck, boost, and buck boost converters, the effective low-pass filter contains an inductor and capacitor, although the value of inductance can be a function of duty cycle. And we get the d hat sources and the M of D transformer. And here's a handy table that gives the results. So the element values in the canonical model are listed here. And if you want to apply or find the AC model for one of these converters, you can, the work is done for you. You can just simply plug into this table to get your model. In the field of control theory, the state space description is a formal way to write the dynamic equations of a linear system. State space averaging is an early and well accepted way to derive the model of a switching converter that employs the state space description of the converter network. In your travels, you may hear people talk about state space averaging, or if you read papers, it may be referenced. And I want you to know that what I've been teaching you in this class is in fact state space averaging, except without the formality of writing the circuit equations in vector and matrix form. State space averaging does have some additional advantages. It provides a formal way to write the equations correctly, where we identify what are the independent sources, the state variables, and the other dependent or output quantities of the network, and write them in a very specific matrix or vector form. And what we know from state space averaging is that if we can write our converter equations in state space form, then we can plug the result directly into the state space averaging method and always get a correct and valid model of our switching converter. I think that we don't have time in this 9-week class to spend the hour or two of lecture that it would take to cover all of this, but I do want you to know that it exists and that what you have learned in this class is in fact the same thing. So what I'm going to do is append the full set of slides to this video, which covers an introduction to how to write state equations for an electric circuit, a derivation of the state space averaging method and a statement of the results, and then an example of applying state space averaging to derive the AC model of a flyback converter. So for those of you who are interested or have the time, I'd suggest you can look through those slides. Having developed AC models of switching converters, we're now in a position to use the results of these models to draw their transfer functions and bode plots, and then to design their control systems. So in Chapter 8, which we'll cover this week and part of next week, we're going to discuss the transfer functions that are predicted by the small signal models of our power converters. So we begin with a review of bode plots. Now, in my experience, usually our electrical engineering undergraduates have seen bode plots in their beginning circuits classes. However, the depth at which it's covered and the abilities to construct bode plots are highly variable. And we really need to be good at these in order to use them and actually design the control systems. So what I'm going to do is start at the beginning but cover bode plots fairly quickly. Those of you who feel that you are good at these can skip the first several lectures. However, often people comment that they learned something from watching them. So I would suggest that if you have time, you take a look. We'll also talk about second order systems. We're going to concentrate as well on constructing phase asymptotes, not just the magnitude asymptotes. And we'll talk about some approximations that can be made that help us develop analytical expressions for fairly complicated transfer functions and let us control the algebra. After that, we're going to talk about converter transfer functions, and so we'll apply the bode plots to construct the transfer functions of some switching converters and discuss their important features. Next, we're going to talk about a graphical construction technique to construct bode plots. And this is an approximate method that actually lets us construct transfer functions nearly by inspection. So we can take a circuit that can be fairly complex and develop, without doing a lot of algebra, the bode plot of its frequency response. This gives a lot of physical insight into what's going on, and it actually allows us to function as engineers on a higher level, to know what we're doing and get nice quantitative results without getting bogged down in the algebra. So I think this is a fun section to discuss, and we'll do that third. Finally, I'm going to talk about a couple of practical issues regarding measurements of transfer functions in the lab. As an example, here's the buck-boost converter model that we developed in Chapter 7. And so we identified a number of quantities of interest, some transfer functions, such as GVG, which is the transfer function from VG hat variations to V hat, or output variations. We also identified GVD of S, which is the control to output transfer function from D hat to V hat. We may be interested in the output impedance of our converter to see how load current variations affect the output voltage. And we may also be interested even in the input impedance in a larger system application. So these are examples of transfer functions that we want to construct. Okay, this is a fairly complex circuit. It's actually not that bad, but if we start refining it with resistor, loss elements, and other things, it can grow very quickly. Now, in teaching undergraduate circuits, we faculty often have a rule that if you give a problem with more than 3 elements, most of the class gets it wrong. Certainly, it gets difficult to handle circuits that have a lot of complexity and many elements. And yet interesting circuits that do important things do have many elements, hundreds or thousands or more. And so how do you handle that? We need to be able to work out the transfer functions of interest, gain an understanding of what's going on in them, and yet gain that understanding without getting bogged down in algebra. And if you have very many elements, then the algebra can get long and fill many pages, and it's unlikely that the average engineer will get through that algebra without making algebra mistakes. So we have to manage and handle the complexity of real systems. And how do we deal with that? In the electrical engineering field, there is a movement among certain faculty to adopt what is known as design-oriented analysis. We power electronics faculty at the University of Colorado are among those faculty. What we are trying to do is to teach our students how to handle this complexity in the systems and be able to function as engineers. There's an old story that really about a situation that has been going on for decades in which the typical electrical engineering graduate will get a new job at a company and be given a task involving, say, the current design of some system, and they'll be given a set of schematics with many components and fairly complex system. Classically, the new graduate will start writing loop and node equations to try to analyze this system, if it's an analog system, and they'll make a giant mess. They'll get equations that are pages long and get nowhere. And then you start hearing comments like, everything I learned in college was useless. And to the student at that point in their career, they're right. Even worse, they then walk down the hall and ask the technician, say the engineering technician, what's happening, and the technician can explain it. Even though the technician didn't take college, perhaps, and can't write all the equations, the technician could explain in paragraph and with physical explanations how the circuit works, which is even more frustrating to the new graduate. The seasoned, experienced engineer, though, can write those equations, know what they're doing, and function to design a new system that works well. So how does the experienced engineer do it, and what have they learned that the new graduate doesn't know? Well, what we're trying to do with design-oriented analysis is teach some of those things. This week we're going to talk about a few of those things. There are many components of design-oriented analysis, but this is at least a good start. So we want to teach how to approach a real and complicated system, here in the context of transfer functions and solving the AC models of power converters and then using those models to design control systems. So what invariably happens is we have complicated derivations, long equations, and a multitude of algebra mistakes. We want to avoid those things or conquer them. And what we would like to do in our design process is to obtain physical insight that leads the engineer to synthesize a good design, which might mean choosing element values, or it might mean gaining insight to change the circuit in some way to make it better. As far as choosing element values go, we want to obtain simple equations that can be inverted. So with these simple equations, we can solve for the element values that are needed to get the circuit to behave the way we want. If we have a long, complicated equation that you can't invert to solve for the element values, then it's really pretty useless. So design-oriented analysis is a structured approach to analysis that attempts to avoid these problems. Another major component of design-oriented analysis is learning how to make engineering approximations. Unwittingly, in academia, we train students to prefer exact solutions, and the students have some kind of feeling that an approximation is a failure. The opposite is in fact the case. You have to realize that the exact solution is in fact the exact equation that describes the approximate model that the professor gave you in class, that has neglected all kinds of things. The model in the first place is approximate. So the best equation to begin with is a simple one that gives insight and makes all kinds of approximations. And you have to realize that a simple approximation is really painless. If you can figure out how to make a simple approximation, it saves you doing all that work, and so you can get one quickly. And if that approximation gains some insight, then it was worthwhile. And you have nothing to lose, because you can still do the algebra later if you really want to, and in the meantime you've gained insight with a small amount of work. In fact, the way the process goes is we refine our approximation to make our model or our equations somewhat more complex to account for whatever is significant, but we will never go all the way and exactly solve everything. That's an impossible task, and the result is worthless anyway because it's a big mess. So we will keep refining our equations and our approximations until at some point we decide that's enough and it's not worth expending any more effort to further improve the accuracy of the result. Specifically, here are some of the things we're going to talk about in this chapter. We're going to write transfer functions in normalized form, and what this does is it directly exposes the salient or important features of our frequency response. This is also a way to manufacture multiple constraints out of one equation. So for example, we may have several specifications for our system, but we may have hundreds of components. So how do we get hundreds of equations to solve for those components out of a small number of specifications? The salient features, in fact, are sub-equations that come out of, say, a larger transfer function that give us equations for each of the important features of the circuit and how those features depend on individual element values. We'll talk about how to find simple analytical expressions for the asymptotes and corner frequencies and similar kinds of salient features then that let us choose the element values. I'm going to introduce the ideas of frequency inversion, which we'll also call inverted poles and zeros, that let us mold our expressions into ones that are the most meaningful and are written in terms of the important features of what we want. We're going to talk about analytical approximation when we have higher order polynomials, and then we're going to generalize that into graphical construction of bode plots that actually lets us construct bode plots nearly by inspection directly on the plot without doing algebra. And if you can do that, then you know what you're doing, you have a lot more physical insight into what's going on, and it saves a lot of time. This graphical construction is actually equivalent to this analytical approximation of the roots. Here's an example of what we want to get at the end of this chapter. This is the control to output transfer function of that buck boost converter example. And this is a bode plot of its magnitude and phase versus frequency. So we're going to talk about what the bode plot is. Hopefully some of you know what it is, but I'm not assuming everybody does. This also has analytical expressions for the salient features. So there is a DC gain that is written here in terms of the duty cycle and the output voltage. There is a Q factor and a resonance with some complex poles. There is a right half plane zero or non-minimum phase zero. And we have analytical expressions for the corner frequencies and the asymptotes that are the kinds of things we need to do to design the control system. We also have asymptotes for the phase response. So we have 0 degrees of phase shift in this control to output transfer function at low frequency. There are break frequencies that depend on things like the resonant frequency. And there are phase asymptotes. Here a high frequency phase asymptote of minus 270 degrees for the buck boost converter. So again, we need to know this in order to determine the stability of our feedback loop that we will use to control this converter example. We want to use the AC models of switching converters that we derived last week to design the control systems of power converter systems. To do this, we need to plot the frequency responses that are predicted by the AC models. And in other words, we need to construct bode plots of the circuit responses. Now, this is something that is traditionally covered in the undergraduate circuits curriculum for electrical engineers, and many of you may already be good at that, and in that case, you can skip this in the next lecture or two. However, I'm going to review bode plots here so that everybody is up to speed on them, and also I will probably teach you some things that weren't covered in the circuits classes and that go beyond them. So I'm going to go through this material quickly, but I'm going to, I think, cover all the bases. So a bode plot is a log frequency response plot of a transfer function. So if we have a transfer function, like for example, we talked last week about the control to output transfer function, GVD of S, which was the transfer function from D hat of S to the output voltage, V hat of S. This is a transfer function that is frequency dependent, and to plot it and find the what is called the sinusoidal steady state, we let s equal j omega, where j is the square root of -1 and omega is angular frequency, so that we get a complex valued function, gvd of j omega. We can then find the magnitude of that complex function and its phase, and plot those as a function of frequency omega. When we do that plot, that is the frequency response plot. When it's on a log-log scale, it's called a bode plot. So for a bode plot, the frequency axis or horizontal axis is drawn on a logarithmic scale, usually versus the frequency in hertz. And the vertical axis is effectively logarithmic, but it is plotted in units of what are called decibels, where actually a magnitude expressed in decibels is given by 20 times the base 10 log of the magnitude function. Okay, so if we have, say, a gain of 1, so g equals 1, the base 10 log of 1 is 0, and we get 0 decibels. If the function is 10, the base 10 log of 10 is 1, and we get 20 decibels. And in fact, increasing the function by a factor of 10 adds 20 decibels to the function expressed in dB. So we'll plot the function in decibels on the vertical axis. Here's some common numbers and their values in decibels. A factor of 2 turns out to be 6 decibels. A factor of 10 to some power is 20 times the power in decibels. So 1,000, which is 10 to the third power, would be 3 times 20, or 60 decibels. If we want to plot a function that has units, such as an impedance or a voltage or a current, formally we should divide the quantity inside the log to make it unitless. And so one formal way to say that is that say we want to plot impedance, we need to divide by some constant impedance that we call the base impedance to get a dimensionless number and then express that number in decibels. Of course, you have to tell everybody what number you decided to use as the base impedance. A very common choice is a base impedance of 1 ohm. So then we would take our impedance, divide by 1 ohm, and then express that number in decibels. If we do that, it's the tradition to call that Z expressed in dB ohms, like this. So 5 ohms, if we have it with a base impedance of 1 ohm, 5 is 14 dB, right here on this plot or chart. And so 5 ohms would correspond to 14 dB ohms. You often see currents for electromagnetic interference specifications. You see currents expressed in dB microamps, and what they're doing there is they're choosing 1 microamp as the base current. So 60 dB microamps is 60 dB, or a factor of 1,000 with respect to 1 microamp, which means it's a current of 1 milliamp. The usefulness of the log-log plot for bode plots is that functions that go like frequency to some power are effectively straight lines when we use this log-log scale. So for example, if we have a transfer function g whose magnitude is frequency divided by some constant f0 to the nth power, then when we express that in decibels, we take 20 times the base 10 log. The power can be taken outside, and we get 20 in times the log of f over f0. So this turns out to be a straight line in log f. So here effectively you can think of the horizontal axis as going like the log of frequency, and we have a function here that varies as the log of frequency. And in fact, if you increase the log of the frequency by 1, then we'll increase the magnitude by 20 times in decibels. So we say that we have a slope of 20 in decibels per decade, where a decade is a factor of 10 in frequency that increases the log of f by 1. So here is a plot for several different values of n. So here for n is 2, our function is f over f naught squared. We have a straight line with a slope of n times 20 or 40 dB per decade. And the function actually goes through 0 dB right here at f equals f naught. When if you plug in f equals f naught, you get 1, and the base 10 log of 1 is 0, so we're at 0 dB when f equals f naught. So what we can do then is just take one point that is 0 dB at f equals f naught, and then draw a line with the correct slope through that point. The big use of bode plots is to approximate our magnitude function over different frequency ranges by functions of this form. So we may have a function that goes like frequency squared over, say, frequency range from here to here, and will follow this curve. And then over the next frequency range, maybe it goes like frequency to the first power, and so from there we'll go with a lower slope, and so on. And so we divide our frequency response plot into different regimes or different frequency ranges where we have different slopes. Okay, let's do an example. Here's a simple RC low-pass filter circuit. So our output voltage, V2 of S, is equal to the input, V1 of S, multiplied by the circuit transfer function. And the transfer function of this circuit is a voltage divider equal to the impedance of the capacitor, which is 1 over SC, divided by the sum of the impedances, R plus 1 over SC. Okay, so that's what we have here. We're going to write our transfer functions from now on in a normalized form as a rational fraction that's in normalized form. What I mean by a rational fraction is that it's a ratio of polynomials. So there's a numerator polynomial divided by a denominator polynomial. And what I mean by normalized form is that the coefficient of s to the 0 power is 1 in both the numerator and denominator. So here if you multiply top and bottom by SC, then what we get is 1 in the numerator, and in the denominator we get 1 plus SRC. So this is a nice normalized form rational fraction. Okay. This term coincides with a standard form that we're going to use for a first-order polynomial in the denominator. This is called a pole, in which there's a root of the denominator. And the normalized form that we will use has, again, the coefficient of s to the 0 power is 1. And here we have a constant omega naught that tells us the coefficient of s to the first power. Okay, by equating our standard form to the original function, we can find that 1 over omega naught is equal to RC, and so this gives us an equation for the coefficient omega naught in our standard form, and its relationship to the elements of the original circuit. Okay, so we have our G of S then is of, for the simple pole, is of this form. To find the magnitude of this transfer function, we let S equal j omega, which gives us this, and then we find the magnitude of the resulting complex function. So the complex function g of j omega at any given value of omega is some complex number that has a magnitude and it has a phase. So we can find the magnitude by the magnitude would be the square root of the sum of the squares of the real part plus imaginary part each squared. If you multiply top and bottom of our function by the complex conjugate, 1 minus j omega over omega naught, you can express g like this, and this part here is the real part, whereas this part here is the imaginary part. Okay, so to find the magnitude then, we find the square root of the real part squared plus the imaginary part squared. If you plug those real and imaginary parts in and do some algebra, you can show that the magnitude works out to be this function. There's actually an easier way than that. If we have, say, g is some numerator polynomial divided by a denominator polynomial, the magnitude of g turns out to be the magnitude of the numerator divided by the magnitude of the denominator. So the magnitude of the ratio of the polynomials is equal to the ratio of the magnitudes. So all you really have to do, since the numerator is 1, its magnitude is 1, all you really have to do is find the magnitude of the denominator, which has this real part and this imaginary part. So what we would get then would be 1 over the square root of the real part squared plus the imaginary part squared, omega over omega naught, quantity squared, as the magnitude of g. I would also note that you don't include the j when you square the imaginary part. If you did, that would give you an extra minus sign, which is not correct. Okay, so here is our magnitude function. We now express that in decibels. So 20 times the base 10 log of this. Is that. We can use the property that the log of 1 over x is equal to minus the log of x. So we can actually flip over the quantity inside the log and pull a minus sign out instead. So this is up to the minus 1 power. And we can get this expression for the magnitude in dB. Okay, here is our function that we found for the magnitude. What we're going to do next is draw the bode plot by approximating it over different frequency ranges by functions that go like frequency to some power. And in the case of this simple form of the single pole, we find the asymptotic behavior at low frequency and high frequency. So at low frequency, which means in particular for frequencies where omega is very small, what does this function tend to? Well, if you look at the denominator, we have 1 plus a function of omega, and when omega is small, this function of omega becomes small. And in particular, when omega over omega naught squared is a lot less than 1, we can just throw out this term. So another way to say that is for omega much less than omega naught, the function we just ignore this term, and we get 1 over root 1. So magnitude of g goes to 1. And that's the asymptotic behavior. So our low frequency asymptote we're going to draw as just a straight line equal to 1 or 0 dB. How about the other case? What happens at high frequency? So if we reverse the inequality, where omega is much greater than omega naught, in that case, the omega term becomes large compared to 1, and we can throw out the 1. So then we get 1 over omega naught squared, which goes to 1 over omega naught. Or this is a function that goes like omega over omega naught to the minus 1 power. If we want to express this in frequency f, omega is 2 pi f, so we could write this as 2 pi f over 2 pi f naught, all to the minus 1 power, which is just f over f naught to the minus 1. Okay, this is a term that we've already seen. If we go back a few slides, here is our plot for functions that go like f to some power, Here the power is minus 1. So we'll have this curve right here. The n is minus 1 curve. And it's actually a line that has a slope of minus 20 dB per decade, and it goes through 0 dB at f equals f naught. So here is that line for f much greater than f naught. We have the minus 20 dB per decade slope, and it passes through 0 dB at f equals f naught, which in fact intersects the other asymptote. So we have two different asymptotes, one for f much less than f naught and the other for f much greater than f naught. The only thing left is to say, well, okay, what does the exact curve do in the vicinity of f equals f naught? And to find that, we can just plug in some values. So for example, if we when f equals f naught, what do we get? Our magnitude of g then becomes 1 over root 1 plus f over f naught quantity squared with f equals f naught, and the whole thing will go to what? 1 over root 2. Okay, 1 over root 2 expressed in decibels works out to be minus 3 dB approximately. So at the corner frequency, the function we say is 3 dB below the 0 dB asymptote, or we say the function is 3 dB down at the corner frequency. You can do a similar calculation at f is 1/2 f naught or f is 2 f naught, so a factor of 2 on either side in frequency, and find that the exact curve is 1 dB below the asymptotes there. So we can plug in then those values. You just draw the asymptotes and then plug in the values for these 3 points and draw a smooth curve through them, and that is the plot of the single pole response. So anytime we get a term that can be written in this form, then this is what its magnitude looks like. Okay, we should also talk about the phase. The phase is very important in design of the control system, so we need to similarly understand the phase. So here is, again, our g of j omega is this. To find the phase, this phase angle, we know from geometry the phase is the arctangent of the, in this case, the imaginary part, or this opposite side divided by the real part, which is this side. So from trigonometry, we get that the phase is the arctangent of the imaginary over the real part. When we take this imaginary part and this real part and divide, including the minus sign, we get that the phase is the arctangent of omega over omega naught, which is the same as minus the arctangent of f over f naught. Here's a plot of that with frequency again varying on a log scale. This is a computer-generated plot. We can plug in some values. So as in the magnitude, we might look at the asymptotic behavior. What happens to this function for omega much less than omega naught? Well, we find that the function tends towards a 0 degree asymptote at low frequency. And likewise at high frequency with omega much greater than omega naught, the function tends towards a constant asymptote of minus 90 degrees. At the corner frequency omega equals omega naught, you get minus the arctangent of 1, which is minus 45 degrees. So right here at the corner we're at minus 45. So we have asymptotes for low frequency and high frequency, but unlike the magnitude case, the asymptotes don't intersect. And we need some kind of other asymptote to draw for mid frequencies that tells us how the phase changes between the high and low frequency asymptotes. Now there's more than one way to do this, and in fact in different textbooks or different papers and things you'll see different choices for that asymptote. One way to do it is to find the slope of this function right at the corner. So right here at minus 45 degrees, we could differentiate the arctangent function and find its slope. It's actually a little tricky because you have to vary frequency on this in this logarithmic form and then take the derivative of that. But we can do it, and if you do that, it turns out that if we draw a function with that slope and extend it up to the high and low frequency asymptotes, then this break frequency where the asymptotes intersect turns out to be equal to e to the pi over 2 times f naught. And this one here turns out to be e to the minus pi over 2 times f naught. Okay, get out your calculators. E to the pi over 2 is 4.81. So if we know f naught, we can multiply by 4.81 and find this break frequency where the asymptotes change. So you'll see in some books that's what people use. In some other books, most notably the Shams outline on bode plots, they round 4.81 up to 5. And so this is 5 times f naught, and this is f naught divided by 5. Yet another choice that is popular is instead of 5 to use 10. So here's that choice. There is in fact no such thing as an exact approximation. 10 is easy to do in your head, and in fact the choice of 10 is perhaps not quite as good in the vicinity of f naught, but it's maybe a better average approximation of the curve over the whole range. So again, it's a matter of taste, but what we're going to use in here is 10, and it does have the nice interpretation that the phase changes over 2 orders of magnitude about the corner frequency. So it'll change from 0 to minus 90 degrees over 2 orders of magnitude in frequency. And that's a good approximation of how the phase works. So the slope of this phase asymptote then is minus 45 degrees per decade, where a decade is a factor of 10 in frequency. So in this factor of 10 in frequency from here to here, we change by minus 45 degrees. Okay. The actual function deviates from the asymptote by 1/10 of a radian, or 5.7 degrees, at these break frequencies. So here's a summary of the rules for constructing the magnitude and phase bode plot asymptotes for the case of the simple real pole. So the magnitude asymptotes are 0 dB at low frequency and a minus 20 dB per decade slope at high frequency, with a deviation of minus 3 dB at the corner frequency. The phase asymptotes have a minus 45 degree per decade slope asymptote, going from 1/10 of the corner to 10 times the corner frequency. The low frequency asymptote is 0 degrees, and the high frequency asymptote is minus 90. Continuing our review of bode plots, here are some more standard terms that often come up. First one we'll look at is the single zero. This is a polynomial that has a root that we can view as a root of the numerator of the transfer function. So this term actually is 1 over the term for the pole that we discussed in the last lecture. So we can go through the same arguments as for the simple pole to find which term dominates at high or low frequency and derive the asymptotes. But another way to see it is simply to consider what happens to the magnitude and phase of a complex number when we invert it, or take 1 over the number. So suppose we have some complex number, g of j omega, that at some given value of omega has a magnitude and a phase, which we can actually express in polar form as some magnitude I'm going to call r times e to the j theta, where theta is the phase. Then what happens to 1 over g of j omega? Well, 1 over g will be 1 over r e to the j theta, and this has a magnitude of 1 over r, and it has a phase, so phase term we can write e to the minus j theta, so the phase of this term is minus theta, or minus the phase of the original g. So 1 over the complex number gives us a phase with a minus sign, and for the magnitude, when the magnitude is expressed in decibels using the log, this can be written as r to the minus 1 power, so we get minus the number of dB. So 1 over g, to do that, we end up putting a minus sign on both the dB magnitude and on the phase in degrees. So as a result, then, here are the asymptotes for the 0, with the magnitude asymptotes and the phase asymptotes. They look just like the pole asymptotes, but with a minus sign. So at high frequency, the magnitude asymptote has a plus 20 dB per decade slope rather than minus. And for the phase at high frequency, the phase asymptote is plus 90 degrees rather than minus. And the intermediate frequency asymptote has a slope of plus 45 degrees per decade. But otherwise, we have all of the same rules for constructing the asymptotes as we had for the pole. Here's another term that is important in power converters. We're going to see that in some upcoming lectures that this kind of term comes up in boost and buck boost converters, as well as some others, and that it causes some major problems and headaches in our control loops. It's called the right half plane zero. It looks just like the zero except for this minus sign here. We call it a right half plane zero because the root occurs where s is a positive real number or has a positive real part because of this minus sign. Now, what does this do to our bode plot? First of all, what does it do to the magnitude? If we let s equal j omega and take the magnitude, or find the sum of the squares of the real and imaginary parts, we find that the minus sign doesn't affect anything, and we end up with the same expression for the magnitude as in the more conventional left half plane or real zero. However, the minus sign does change the phase. When we take the arctangent of the imaginary over the real part, the minus sign comes into play, and so we get a minus sign here in the expression for the phase. So the right half plane zero has a magnitude like any other zero, but its phase is not like a zero. It has another minus sign and looks like a pole. So here are the asymptotes for the right half plane zero, with magnitude like any other zero, but phase that looks like the phase of a pole. The next two terms are ones that we don't have to use, but they can be useful, and in many applications give us a more physical way to write the transfer functions of some kinds of systems. And this trick is called frequency inversion. It's well known in the classical filter design field, where we invert the frequency axis. So wherever we had a term that was like, say, s over omega naught, we turn it into a term that goes like omega naught over s. On our logarithmic frequency axis, what this does is it makes the frequency axis operate in the opposite direction. It's like a minus sign on the log. So this is a well-known transformation in filter design that can turn a low-pass filter, for example, into a high-pass filter. Okay, in the case then of, say, this term illustrated here, which is an inverted pole, the regular pole will look like this. And what frequency inversion does is it flips the frequency axis around so that our term looks like this. So we have a flat gain of 0 dB at high frequency, And then as we decrease in frequency below omega naught, the gain reduces or rolls off. Now, you don't ever have to use these kinds of terms. For example, you could multiply top and bottom here by s over omega naught. And if we do that, we'll get s over omega naught in the numerator, and the denominator will give us s over omega naught plus 1, which we can write like this. So this alternate form has no inverted terms and is completely equivalent to the frequency inverted term. But the nice thing about the frequency inversion term is that it gives us this interpretation that we have a high frequency gain of 1 or 0 dB, and then we roll off at low frequency. And in combination with other terms, this can be a nice, useful thing. And we'll talk about that in the next lecture of some examples. So here are the asymptotes in summary form for the inverted pole. Likewise, we can invert any of our other terms. So for example, an inverted zero is found by applying the same transformation. So if our regular zero has asymptotes in magnitude that look like this, then frequency inversion will turn them into a high frequency flat asymptote and a low frequency asymptote that increases as we reduce frequency. And again, we can write this in an algebraically equivalent form like this that does not use inverted terms. But where we're interested in emphasizing what the high frequency asymptote is, this is a good way to write the expression. Then here is a summary of the asymptotes for the inverted zero. Okay, so we've gone through all of the basic real pole and real zero type terms that we're going to use. In the next lecture, we're going to put them together and construct the larger transfer functions and their frequency responses. In this continuing review lecture, we'll talk about combining the forms that we've discussed in the previous two reviews to construct the bode plots of more complicated transfer functions. So the basic idea here is that we can combine terms such as poles and zeros that we know how to draw the asymptotes for according to some simple rules. And the simple rules can be seen or derived really by writing the expression for a complex number in polar form. So suppose we have a transfer function g1 and another one g2 and g3, and we express each of these in the polar form as some magnitude that's called r here times e to the j times theta, the phase. So if we call g3 is the product of g1 and g2, we can find the magnitude and phase of g3 by multiplying the terms for g1 and g2 together. So we'll get r1 times r2 times e to the j theta 1 times e to the j theta 2. And the product then we can write as r1 r2 in magnitude, which is the magnitude of g3, times e to the j theta 1 plus theta 2, so the phase adds. Okay, when r1 and r2 are expressed in decibels, then their product is found by adding the dB values. So r3 is the sum of the dB magnitudes of r1 and r2, and theta 3, the phase, is the sum of the phases. So in general then, to find the composite phase, when we multiply terms, we simply add the individual phases. And to find the composite magnitude in decibels, we add the composite dB individual magnitudes. So here's an example. Suppose we have a more complex transfer function that has a constant term, g0, that we'll take to be a real positive number, and then it has two poles. So there are two denominator terms that look like the poles that we previously discussed. And here are some numbers plugged in. So g0 is 40. If you express that in decibels, 20 times the base 10 log of 40 turns out to be 32 dB. F1, the corner frequency omega 1 over 2 pi, let's suppose is 100 hertz. Let's suppose F2 associated with omega 2 is 2 kilohertz. So here's a plot of that. And to construct the magnitude, we construct the magnitudes of the individual terms and then add their dB together. So G0 is 40 dB. I'm sorry, it's 40 or 32 dB, which is up here. So that's the G0. The first pole is 0 dB for frequencies below F1. F1 is 100 hertz right there, so here's F1. So we'll be 0 dB until we get to F1, and after F1 we have an asymptote that has a slope of minus 20 dB per decade. That was supposed to be a straight line. Okay, then our second pole at frequency F2 of 2 kilohertz, let's see, there's F2. This one has 0 dB asymptote until we get up to F2, and then it has a minus 20 dB per decade slope after that. So to get the composite, we have to add the blue, the red, and the green lines, and at any one frequency, the composite magnitude will be the sum of the individual magnitudes. So, for example, down here at low frequency, we have 32 dB plus 0 dB plus 0 dB is a total of 32 dB. And we continue like that until we get to the first corner frequency at 100 hertz. After 100 hertz, the first pole adds a minus 20 dB per decade slope. So the composite will decrease with that slope because the first pole is decreasing. And so we'll follow this minus 20 dB per decade slope until we get to the second corner at F2. At that point, we have another minus 20 dB per decade slope, and the composite will go down with a minus 40 dB per decade slope. So the yellow asymptotes are the total asymptotes for G of S. Likewise, to construct the phase asymptotes, we construct the individual phases of the different terms, and then we add them together. So the G0 term is a real positive number. Its phase is 0. The first pole at F1 gives us 0 degrees phase until we get to 1/10 of the corner frequency F1. So F1 is 100 hertz. 1/10 of that is 10 hertz. So here's F1 over 10, or 10 hertz. Beyond that corner, this first term has an asymptote with a slope of minus 45 degrees per decade, and we continue at that asymptote, or that slope, until we get to the next break frequency, which is at 10 times our corner. 10F1 is 1,000, so we're at 1,000 hertz, and at that point we flatten out and have a constant minus 90 degree asymptote. Finally, our last pole has a similar shape, except its corner is at 2 kilohertz. So let's see, here's 2 kilohertz up here. 1/10 of that is 200 hertz. So we'll follow a 0 degree asymptote until we get to 200 hertz. Then we'll go down at minus 45 degrees per decade until we get to 10 times 2 kilohertz, or 20 kilohertz. After that, we have a minus 90 slope, or minus 90 degree flat asymptote after that. So the composite phase asymptotes for this transfer function are found by just adding the individual phase asymptotes. So at low frequency we have 0 degrees. When we get past 10 hertz, the first pole makes our phase start to decrease. When we get to the second pole, or when we get to 200 kilohertz, 1/10 of the second pole, we get another break, and the second pole starts contributing negative phase as well. So the composite will have two phase asymptotes that are decreasing, and our total will go down with twice the slope, or minus 90 degrees per decade. So that's supposed to be a straight line there. When we get to 10 F1 or 1 kilohertz, the first asymptote flattens out, but the second keeps going, so we continue with a slope of minus 45 degrees per decade until we get to 10 times the second corner at 20 kilohertz, and after that all of our individual asymptotes are flat, and so the composite has a flat asymptote also of minus 90 plus minus 90, which is minus 180 degrees. So there, the yellow is the composite phase asymptotes for this transfer function. Let's do a second example. Here is a set of asymptotes that we're given, and the object here is to write the transfer function. So this is a transfer function A of S, and we're supposed to write what is the expression for A of S. Well, there's more than one way to do this, but one way is to say, okay, we're given what this low frequency asymptote is. It's A0. Here the asymptote is actually expressed in dB. We have to, when we write the transfer function, we have to write A0 that's not in dB, but just as a regular number. At frequency F1, the asymptotes change, and we have a plus 20 dB per decade slope. What kind of term does that? Well, a zero would do that. So we could have a zero function term in the numerator with a corner frequency F1, or in our transfer function we express this in the corner in radians per second, so omega 1, where omega 1 is 2 pi F1. We continue until we get to F2, and after F2 the slope decreases by 20 dB per decade, and it goes back to a flat slope. Well, the kind of term that decreases the slope by 20 dB per decade is a pole. And so the transfer function A of S can be written in this way. Okay, we can also write expressions for the asymptotes, and I'm going to illustrate how to do that here. In order to write the equation of an asymptote, what we do is wherever we have a sum, we take the term that is largest, and this is in fact how we derive the asymptotes in previous lectures. So for example, what is the equation of the mid-frequency asymptote here between F1 and F2? So for F between F1 and F2, we can write A of S as follows. If we're at frequency higher than F1, so you can think of S as being j omega, and what is the magnitude of the j omega over omega 1 term relative to 1? Well, if omega is greater than omega 1, then this term has larger magnitude than the 1, and to write the equation of the asymptote, we throw out the 1. Okay. Likewise, for the denominator, what do we do? Well, over this frequency range, we're at a frequency less than F2, so we let S equal j omega, and omega is less than omega 2. That means that this second denominator term will be smaller in magnitude than 1, so we throw that term out. And what we get then is A of S is A0 times the numerator, S over omega 1. Then for the denominator, we just have 1. And that's our function. Now if we want to take the magnitude will be the magnitude of A0, which is a real number, times the magnitude of this numerator with s equals j omega. It gets us omega over omega 1, and then the denominator is 1. Okay, or in terms of f, we could also write this as A0 times f over f1. So that's the equation of the mid-frequency asymptote. Okay, it's very useful to be able to write the equations of asymptotes. When we design our feedback loops, we're going to need to do this to calculate things like the crossover frequency and other quantities that we need to know. Okay, I'm going to write our A of s again. Let's write the equation of the high frequency asymptote for f greater than f2, which is in turn greater than f1. What can we say about this high frequency asymptote? Well, again, when we have a sum, we take the largest term and throw out the smallest. So here, s is larger, omega is larger than both omega 1 and omega 2, so the terms on the right are the largest, and we can throw out the 1 in both cases. So A of s then will have an asymptote, or we can say A of s is approximately equal to A naught times the s over omega 1 in the numerator, and the s over omega 2 in the denominator. Let's see, the s's cancel out, and we get A0 times omega 2 over omega 1, or in terms of f, A0 times f2 over f1. So that's the equation of this high frequency asymptote. Now here the high frequency asymptote is labeled A infinity. It's just the value of the asymptote. So A infinity apparently is given by that expression. So we have a straightforward way to easily write the equations of the asymptotes by simply taking the largest term wherever we have a sum of terms. And here this also gives us an easy way to find, say, the high frequency gain in terms of the low frequency gain. Okay, these slides 35 and 36 document what I just said. Now there's one other way to write the transfer function that can be very useful. Suppose we're not interested in A0, or it's not so important in our application. Suppose instead we're more interested in the high frequency gain. We could express A in terms of the high frequency gain instead of the low frequency gain. And what we do is we use inverted forms. So if we use inverted poles and zeros, each of those kind of terms has a high frequency gain of 1 or 0 dB. So if we express our transfer function in terms of inverted forms only, then we know that each of these forms will be 1 at high frequency, and then any multiplying constant out in front is in fact the high frequency gain of the transfer function. So if we take that viewpoint, we start with a high frequency gain of A infinity, and if we decrease frequency below f2, the gain decreases. So that is in fact what a pole does, and this is an inverted form. So 1 plus omega 2 over s would cause our transfer function to decrease. And then when we get to f1, the slope increases again as we decrease frequency. So this is an inverted 0. So we can put an inverted form 0 in our expression as well. This happens at f1. So this is another completely equivalent way to write the transfer function. This way of writing the transfer function emphasizes the high frequency gain rather than the low frequency gain. And if that is what is important in our application, then that's a good way to write the term. I'll leave it to you to verify by algebra that this form is in fact equivalent to the original form with non-inverted poles and zeros. One last application of inverted poles and zeros. Suppose we're interested in a transfer function that is a bandpass filter. So let's suppose we want, say, a transfer function like this, where this slope is plus 40 dB per decade. This is plus 20. This is a flat slope at this mid-band gain. This slope is minus 20, and this slope is minus 40. How should we write the transfer function of this? Well, what I would suggest is the easiest way is to reference our transfer function to the mid-band gain. In a bandpass filter, that's usually what we're interested in. So we will write A of S is equal to the mid-band gain A sub m multiplied by some poles and zeros. And these poles in zero terms have to be chosen such that each of them gives a gain of 1 or 0 dB over this mid-band range of frequencies. And then these terms can make the gain roll off at higher frequency or lower frequency. Well, so what we can do is first we can have regular poles at omega 3 and omega 4, like this. Okay, these poles give 0 dB gains at frequencies below omega 3 and omega 4, but over the important mid-band range of frequencies, their gains asymptotes are 1. Then for the omega 2 and omega 1 corner frequencies, we use inverted forms. The inverted forms will cause the transfer function to roll off at low frequency, but they will have 0 dB asymptotes over the mid-band and higher frequencies. So we can have an inverted pole at omega 2 and an inverted pole at omega 1. And the numerator apparently is just 1. So this is a valid way to write this transfer function. It mixes both regular and inverted forms, but it's written directly in terms of the things that are important. So it expresses the mid-band gain directly here, and then it gives each of the corner frequencies with an appropriate term. So this is another example of how to use inverted form terms to make the transfer function be meaningful and straightforward. We have one more important standard form to consider in construction of bode plots, and that is the second order system that may contain a resonance. Here's an example of a two-pole low-pass filter that contains an inductor and capacitor. And these LC type filter circuits commonly appear in our converter models, and in fact we've seen them already in the canonical model last week. So if we solve this circuit to find the transfer function from input to output, we're going to call it G of S in this lecture. We can do the analysis and find that G of S is given by this expression, which has a quadratic form polynomial in the denominator. So this quadratic or second order polynomial we can write in general like this, where a1 and a2 are the coefficients of s to the first power and s to the second power. And by equating a1 and a2 to the coefficients L over R and LC in the original transfer function, we find that a1 is L over R and a2 is LC. So in a case like this, how should we draw the bode diagram? Well, one approach, I think the most straightforward way, is to factor the denominator. We already know how to draw the bode plot of a single pole, and so if we could factor the denominator, the second order system, into two single poles, then we might perhaps apply the methods we've already talked about in the preceding lectures. So here is our polynomial in the denominator. We could factor it with two roots, and here I've denoted the roots as S1 and S2, and using the quadratic formula, here are the solutions for S1 and S2. So as usual, it contains a radical, and the quantity inside the radical is the discriminant, and so we have the case where it's possible for the discriminant to be negative and we can get complex roots. So this indeed can happen. So in the case then where the discriminant is positive and we have real roots, then we can go ahead and factor it this way and then construct the bode plot as two real poles in the way that we've already been talking about. Although I'm going to talk a little more about that in the next lecture, and there are some perhaps even easier ways to do it than that. But in the other case where the discriminant is negative and we have complex roots, then we really can't use what we've already talked about in the case of the single pole. It doesn't apply. Here, going back to the slide from the previous lectures for the single pole, what we did was we let S equal j omega and found what g of j omega was for the single pole case. We got this expression, and then to write the equation for the magnitude, we found the square root of the sum of the squares of the real and imaginary parts, and while I didn't point it out at the time, there was an implicit assumption there that omega naught is a real number. If omega naught is complex, which happens in the complex roots case, then we're not correctly finding the real and imaginary parts. So the single pole derivation from the earlier lecture assumes that we have real poles, and it's not valid in the case where we have complex roots. So in the complex case, what we're going to do instead is define a new standard normalized form for the second order type polynomial, and then derive the magnitude and phase asymptotes without assuming that we have real roots. There are two forms that are in common use in the control business for the second order case. The first one uses a damping factor called zeta here, this quantity, and the second uses a Q factor here. And you can use either form. In fact, just from equating the coefficient of s to the first power, apparently 2 zeta is the same as 1 over q. In the case of the Q factor, this is in fact not the most general way to define Q, and in the RF business, the Q is defined in a more general way, so we can talk about the Q factor of a single component, such as an inductor. And the Q factor is a measure of how ideal the inductor is and how large the loss is. So Q actually comes from quality factor, and it's most generally defined in this way as 2 pi times the peak stored energy in the element divided by the energy dissipated per cycle. So we can talk about the Q of an inductor, whereas with a damping factor, this is really defined in the context of a second order system. Now, this definition of Q is actually consistent with this one in the second order system, but the second order system definition is perhaps more restrictive. This is a nice form to use though with Q, because we're going to see in a minute that it has a very nice interpretation on the bode plot. Okay, so here was our original transfer function for the two-pole case. We can equate the denominator polynomial to the denominator polynomial in our standard form, and get analytical expressions then for the omega naught and the Q. in terms of the original component elements. So by equating the coefficient of s squared, we have s squared, for the s squared terms, LC in this form is equal to 1 over omega naught squared in this form. So we can solve for omega naught. And what? Omega naught will be 1 over root LC. Or F naught, which is omega naught over 2 pi, then is 1 over 2 pi root LC. Knowing that, we can also solve for the Q. So in our standard form, 1 over Q omega naught is equal to this term L over R. So we can substitute in our omega naught into there and then solve for Q. And if we do that, here's what we get as the expression for the Q for this circuit. Okay, given the standard form, let's work out what the magnitude and phase asymptotes do. So we can take the same approach as in the real pole case, let S equal j omega and work out the magnitude. And if you do that, here's what we find is the magnitude. This term on the left here, it comes from the real part squared, and this term comes from the imaginary part squared. So we can find the asymptotes. What happens for omega much less than omega naught at low frequency? Well, when omega is much less than omega naught, then this term here is small compared to 1. And this term is also small compared to 1 if we let omega be low enough. And the whole thing just goes to 1. So our low frequency asymptote, as in the case of the real pole, is 0 dB or 1 for frequencies sufficiently less than the corner frequency F naught. In the high frequency case, where omega is much greater than omega naught, then which term dominates? Well, this term here goes like omega over omega naught squared and then squared again, so to the 4th power. And if omega is much greater than omega naught, then this term will be large compared to the 1, so we can throw that out. This term here goes like omega over omega naught squared. It doesn't get large as fast as the omega over omega naught to the 4th power term, though, so this one doesn't dominate. It's this one that dominates at high frequency. So the magnitude of G then will go to 1 over the square root of just this term, omega over omega naught to the 4th power, which is omega over omega naught to the minus 2 power. Or in terms of F, we can write it as F over F naught to the minus 2 power. So this is an asymptote with a slope of the minus 2 power times 20 dB per decade, or minus 40 dB per decade. It intersects the low frequency asymptote at the corner. So I think this is a nice set of asymptotes. It is in fact consistent with what you would expect from two poles if they were real and were both at F naught. What remains is to investigate what happens in the vicinity of the corner frequency and see the deviation from the curve. So as in the real pole case, what we can do is evaluate the exact transfer function or the exact formula at the corner frequency omega equals omega naught. So at omega equals omega naught, what we get, if we just put omega naughts in for the omegas, omega naught over omega naught is 1. So we'll get 1 minus 1 squared, which actually cancels out. And the real term that came from both of these adds up to 0. And we're left with the term that came from the complex part, and omega naught over omega naught quantity squared is 1. So the whole thing goes then to 1 over root 1 over q squared, which is just q. Okay, so that's an interesting answer. It says that the value of the exact function at the corner frequency is equal to q. Well, how large is q? The fact is that q can be absolutely anything. And it's interesting that the quantities that determine the asymptotes, say the low frequency asymptote is determined by this term, high frequency asymptote is determined by this term, and the exact value at the corner frequency is determined by this term. So Q doesn't matter anywhere except at near the corner frequency. And Q can in fact be absolutely anything. In a passive circuit it's a positive number, but that's all we can say about it. So in fact, if we go back here, Q appears only in this term, and it's equal to R root C over L. And we can make R be anything we want, from 0 to infinity, which means Q can be anything. So what determines the actual function at the corner frequency has nothing to do with the terms that determine the asymptotes away from the corner. If Q is large, then say Q is 1,000,000, the function will go up here to 1,000,000, and it'll look like this. If Q is a small number, 0.01 down here, then the function will go down there. So we can get an exact function that deviates wildly from the asymptotes at the corner frequency. And this behavior is in fact characteristic of a resonant circuit, where at this resonant frequency f0 we get solutions that deviate substantially from what happens at other frequencies. Okay, how about the phase asymptotes? Well, we can find the phase of G by finding the arctangent of the imaginary over real part, as we did in the real case, real pole case. So if we do that, here is what we get. We can plot this function as usual, and with a computer drawn plot, here's what it looks like. The curves tend to a low frequency asymptote of 0 degrees and a high frequency asymptote of minus 180 degrees, as you would expect two poles to do. And then in the vicinity of the corner frequency, the change from 0 degrees to minus 180 degrees becomes more sharp as you increase the Q factor. So we can think about some mid-frequency asymptote, say that does this to change from 0 to minus 180, and how steep this asymptote is, or how steep the change is, depends on Q. All of the functions go through minus 90 degrees at the corner frequency, but then the slope here depends on the Q factor. As in the real pole case, we can try to derive an asymptote for the mid-frequency phase. We might take the same approach as in the real pole case, where we could at first try to find what is the slope of the actual phase function at the corner frequency f0. And if you do that and draw an asymptote like this that has the same slope, then what you find is that the break frequencies here and here have this e to the pi over 2 factor, like in the real pole case. Recall e to the pi over 2 is approximately 4.81. But then it's raised to the 1 over 2q power. So this break frequency right here is f0 times 4.81 to the 1 over 2q power. Likewise, this break frequency is f0 divided by that quantity. So we have the same choices as in the real pole case. We can use 4.81, or we could round it up to 5, or we could round it up to 10. And what I would say here is that to keep our asymptotes consistent in the real and complex pole case, and in fact to get the same answer at q of a half, which is the boundary between real and complex poles, we should use the same factor here. And so what we're going to do is shown here. We're not going to quite do this. We're going to use the approach shown here, where this break frequency right there is 10 to the 1 over 2q power times f0. And this one is at f0 divided by 10 to the 1 over 2q power. Here's a sketch of what that asymptote looks like compared to the real curve, and you can see that the actual curve crosses this asymptote at 3 places. And so this approach, or this way to draw the asymptote, is not a bad approximation. Incidentally, what this choice implies then is that the slope of the asymptote turns out to be minus 180 times q degrees per decade. So if we have a q of 2, then we'll have a slope of what? Minus 360 degrees per decade. The larger q is, the more negative this slope is, and the closer we get to just a step change from 0 to minus 180 in the vicinity of f naught. To summarize, here is a plot then of what the actual curves look like. These are nice computer-generated plots of the magnitude and the phase response for different values of q, and they're drawn in the vicinity of the corner frequency. So again, as q gets larger and larger, we get a response that has more peaking in it, which is called a resonant response. The phase changes more abruptly from 0 to minus 180 degrees in the vicinity of resonance, again as q is increased. In the previous lecture, we saw how to handle the case of complex poles. So we can use this standard form for the quadratic case, and how we approach plotting it then is to first work out what q is, and if q is greater than 1/2, then we have complex poles, and we can plot the magnitude and phase responses as described in the previous lecture. However, in the case where q is less than 1/2, then we have real poles, and what we would still like to do is to factor the denominator into 2 real poles like this, and then plot it using the rules for real poles. So we're going to consider today, or in this lecture, the details and mechanics of how to factor this and plot as 2 real poles. So here's an example back to our RLC network where this was the transfer function. This was the example in the previous lecture. Let's factor the 2 roots, and what we find is omega 1 and omega 2 are given by this expression using the quadratic formula with the radical and the plus and minus sign. Now, I think that this expression for the 2 corner frequencies is not very illuminating. It's pretty hard to just look at this expression and tell how the corner frequencies depend on the different element values. If you change, say, L, what does that do to the 2 corner frequencies? It's actually interesting to know that, in fact, when the Q factor is much less than 1/2, that the 2 corner frequencies can be approximated like this, where omega 1 is R over L and omega 2 is 1 over RC. So, for example, omega 1 doesn't even depend on C, and omega 2 doesn't depend on L. But you'd never know that from looking at this formula. So the simpler and approximate equations are actually more useful. They gain more insight as to how the corner frequencies depend on the element values, and they're easy to solve. You can see how to change an element value if you want to adjust the value of the frequency, which you would never get out of this formula. Okay, we're going to define omega 1 as the low frequency pole, which is found by taking the minus sign, and omega 2 is the high frequency pole, found by taking the plus sign. And what we're going to do is derive a simple approximation to get expressions like this without having to use the ugly quadratic formula. So the way I'm going to state it is, if we start with this standard function, the first thing we will do is find q, and in the case where q is less than 1/2, then we know we have real poles and we will factor them. Whereas if q is greater than 1/2, then we will use the quadratic form as in the previous lecture. So when q is less than a half, we factor the poles, and the quadratic formula tells us that these are the expressions then for the two poles. And you can note that when q is less than a half, then 1 minus 4q squared is positive, so we get a real result for the roots. Okay, let's look at whether we can approximate these functions in a much simpler way. So I'm going to look first at omega 2, the high frequency pole. So here was the expression we had for omega 2, and it has a term out in front that is omega naught over q, and then it has this more complicated term that has the radical in it, and I'm going to call this more complicated term f of q. If we look at what f of q does as a function of q, first of all, when q is small, so much less than a half, then 4q squared is much less than 1, and what we could do to approximate f of q is just throw out the 4q squared term, and we get 1 plus root 1 over 2, which is just 1. And so for low q, f of q actually goes to 1, which is what's plotted here. As q approaches a half, then this function approaches just 1 over 2, and the discriminant goes to 0. So the f of q goes to a half at q of a half. And in fact, it changes very quickly for q in the vicinity of a half. If you, in fact, look at the function for q less than 0.3, f of q is between 0.9 and 1. So if we just called f of q equal to 1, we'd be within 10% of the right answer for q less than 0.3. And it's only this last little part here for q between 0.3 and 0.5 where f of q changes much at all. So the low q approximation says then for omega 2, let's just take the f of q function and call it equal to 1 and approximate omega 2 as being omega naught over q, this part of the expression. Okay, how about the omega 1 term? Here's omega 1, it has the minus sign. So if you try the same thing, say, okay, let's let 4q squared be much less than 1 and ignore it, what you get then is 1 minus 1 over 2, or 0. So then we're approximating omega 1 as 0, which is not a very useful approximation. So we need to do a little more work. And here's a trick, a way to do it. What we do is you can think of this as rationalizing the numerator. We're going to multiply by 1 plus the radical in the numerator and the denominator. And if you multiply this term by this term, it removes the radical from the numerator. You can do the algebra. I'll let you do that on your own. And what you can show then is that omega 1 is given by q omega naught over f of q, where f of q is the same function we defined on the last slide, which we've already plotted. So for omega 1 then, we get q times omega naught divided by the f of q, and again f of q is close to 1, particularly when q is less than 0.3. So the low q approximation then approximates the low frequency pole as omega 1 is q omega naught. So then here's a summary. For the two-pole case, when we have low q, the two poles split into a low frequency pole omega 1 and a high frequency pole omega 2, and they're in fact spaced evenly about this resonant frequency f naught. It's no longer resonant, but so f1 is f naught times q, where q is a small number, and f2 is f naught divided by q. If we increase q, the two poles move together towards f naught, and then in fact when q is greater than a half, they turn into a resonant response with a resonance at f naught. So what we do then is we calculate q. If we find q is less than a half, then we can use the low q approximation and quickly get the real poles from these expressions. Back to our RLC example. Here was our original transfer function, and here are the expressions that we had for f naught and q. So f1, we said, would be q times f naught. So Q is R root C over L, and F naught is 1 over 2 pi root LC. So the root C's cancel, and what we get is R over 2 pi L. It's a nice simple expression. For F2, we said that was F naught divided by Q, with F naught again is 1 over 2 pi root LC, and 1 over Q is 1 over R times root L over C. So let's see, the root L's in this case cancel, and we get 1 over 2 pi R times C. So again, nice simple expression. So the low Q approximation gives us a nice way to keep control of the algebra and get simpler expressions that are easy to use in design. In this lecture, we will generalize the low Q approximation to the case of a higher order polynomial. So what we're going to do is use numerical values to justify making approximations, but those approximations then can be expressed as analytical functions of the component values, and these analytical functions can be very simple. So we have an nth order polynomial here, P of S, with coefficients a1 through an, and what we would like to do is to factor it into roots in this form. So the taus essentially are the roots, and under the case that the roots are real and well separated in value, then we're going to find that some simple ways to do this. We'll also look at some special cases, for example, when we have two roots that are nearby or near each other, and where we need to leave the roots in complex form. Here's how it works. What we do is we take the factored form and we multiply it out, and then equate like powers of s to the original polynomial. So if you do that, here's what we find. That the coefficient of s to the first power, or a1, is the sum of the taus. a2 is the sum of the taus that are products taken two at a time. a3 is involves the sums of products taken three at a time, and so on. And an is the product of all the taus, tau 1 through tau n. Now, so far we haven't really accomplished anything. We haven't solved the problem because we can't solve this in general. And in fact, it's not known in general how to factor exactly a higher order polynomial. However, this does give us a way to make approximations. And what we're going to do is first assume that the taus are written in order. So tau 1 is bigger than tau 2 is bigger than tau 3, and so on. And we can make that assumption without loss of generality. There is an order for the taus. Okay, and in that case, if you look at these expressions, the first expression that's written is in fact the largest. So if tau 1 is bigger than tau 2, which is bigger than the rest of the taus, then an approximation we can make is to simply take the largest in the sum and throw out the remainder. So a1 is tau 1. Likewise, for a2, tau 1 times tau 2 is the largest of all of these terms. That's bigger than tau 2, tau 3, and so on. So we'll take the tau 1, tau 2 term and throw out the rest of those. And likewise, we keep doing this. Then in the case where the taus are written in this order, which means they're real and well separated in value, then we can take the largest, or the first term in each of these expressions, so that we're left with this system of equations. And this system is in fact easy to solve. Tau 1 is a1. Tau 2 can be found by dividing the second equation by the first, which would give us that tau 2 is a2 over a1. Tau 3 can be found by dividing the third equation by the second, which means that tau 3 is a3 over a2, and so on. So we have an approximate factorization, and then here is the answer. So these are this is tau 1, this is tau 2, tau 3, and so on. And here is our factorization. So we have a set of inequalities that has to be satisfied. We can easily check these inequalities if we know the element values and see if they're satisfied, and if they are, then this is the factorization. It's also very easy to evaluate these. If we simply have the ratio of terms, it's pretty easy, given expressions for the coefficients, to find their ratios. We'll do an example in a few minutes, but this form is one that lends itself well to getting simple analytical expressions for the roots. Another thing about this is we can plug in numerical values to check this set of inequalities, but having plugged the numerical values in and found that the inequalities are satisfied, we don't have to plug numerical values into this equation. We can instead plug in analytical values, so analytical expressions. So for example, A1 is something like RC, A2 might be L over R, or L times C, and so on. So we can plug or obtain analytical expressions for the roots in this second form. Okay, well, we just need to worry next about special cases. So suppose some inequality is not satisfied. Let's say this inequality out here in the middle of this string of inequalities. In that case, what we have to do is take the two roots that are on each side of this inequality and leave them in a quadratic form, like this. So this means we have two roots that are not well separated, and we can treat them in a quadratic form to get a more accurate expression for the corresponding terms. Here is then the way to do it. So this term here is ak over ak minus 1, which is what it would have been in the original approach, and the second term is ak plus 1 divided by ak minus 1. So this is a different term. One can multiply this out and show that this is the set of inequalities that are required for this approximation to be accurate. So this is in fact what happens when we have two roots that are close to each other. We have another special case where the first inequality is not satisfied. And in that case, we leave the first two roots in their original form, which is a quadratic form, like this, and then we continue as usual for the remaining roots. One can multiply this out and find the inequalities that need to be satisfied, and here's what they turn out to be. So the first two inequalities are different. Other cases, if we have several isolated inequalities that are violated, then we just have to leave the corresponding roots in quadratic form, so that we may have more than one quadratic form in our factorization. We'll do some examples of that. And then if we have several inequalities in a row that are violated, then that means we have more than two roots that are close together. So then we have to use cubic or higher order roots, and then you're on your own. You know, that's a higher order case, and we have to handle it with other means. Here is an example. This is one that we actually, a circuit that we build in our second power electronics course at Colorado. It is a damped input filter. So we have a switching converter here, like for example a buck converter, whose input current is a pulsating current. There are regulations typically that limit the amount of high frequency current harmonics we're allowed to inject back into the power source, and so we have to build LC filters. And in the process of adding an LC filter, what one finds is that this LC filter can disrupt the feedback loop of this converter and actually cause instabilities. So we have to damp the filter. And here's one way to do it. We add an RL network in parallel with our inductor, which adds some damping to the resonant filter here and makes it easier to stabilize and control the converter. So this is an example of a third order input filter circuit. Now you can do the analysis of this circuit and find that its transfer function from converter current to current going into IG is this expression. Well, I'm not going to take the time to do the algebra. You'll have to take my word for it. But we get a third order denominator because there are two inductors and one capacitor in our circuit. So what we would like to do is to factor the denominator into a simpler form with factored roots. So if we apply our approximate factorization method, we identify that this is A1, this here is A2, and this is A3, which is noted here. And with that, we can now apply the factorization method. If the roots are real and well separated, then here is what the factorization will be. We said it would be 1 plus A1s times 1 plus A2 over A1s times 1 plus A3 over A2s. This is the A1. This right here is A2 over A1, and this is A3 over A2. So simple enough to apply. Here are the inequalities that are required. Basically, the first root is much greater than the second root, which is much greater than the third root. Okay, we could leave it in this form, but in fact, this result can be further simplified. And if you look at these inequalities for a minute, you'll see, first of all, how can it be that L1 plus L2 over R is much greater than L2 over R? One thing I would caution you is that you have to be careful with these much greater than symbols. We can't just do normal algebra like to subtract L2 over R from each side of the equation. If we do, we'll get L1 over R is much greater than 0, which is not a very useful inequality. In fact, what this inequality means, the only way it can be obeyed, is if L1 is much bigger than L2, which then means that we can ignore the L2 here, we can ignore it there also, and then we get L1 over L1, which is just 1. And so the whole thing simplifies then to this. So this is our inequality, or set of inequalities, and in fact these are simpler expressions for the three roots. So we can actually take the factored form and simplify it in the same way to this. So this is a nice form, I think. It's an easy way to see how each of the three roots relates to one of the L's or C's. Okay, that was the real root case. Now let's suppose that the second inequality is violated. So in that case, we have to leave the second and third roots in quadratic form. And so here is the correct form from this second case. 1 plus A2 over A1s plus A3 over A1s squared. Here is our A1, which is this term. Here is A2 over A1. And this is what A3 over A1 works out to be. Okay, we can go back and plug in for this case what inequalities are required. We still have three inequalities required, but they're different than before, and in particular the third one is different. Now if you look at this set of inequalities, how is it that the second term can be much greater than the third? Both terms have RC multiplying factors, but the first one has L1 over L1 plus L2. The second one has L1 in parallel with L2 over L1 plus L2. So basically it means that L1 is much greater than L1 in parallel with L2. And again, the only way that can happen is if L2 is much smaller than L1. We still have this inequality, which we had before. And having made that inequality, we can now go and throw out the L2 here, throw out this L2, and this is just RC. And then this one gives us really L2 over L1 plus L2. So the second inequality is really saying L1 is much greater than L2. So what we get then from these is really these two inequalities are required, but we no longer require this third inequality. So when this inequality is not satisfied, we can leave the second and third roots in a quadratic form like this. And in fact, you can see that this expression then simplifies down to this. We have one more case where it's the first inequality that is not satisfied. So in that case, we have to leave the first and second roots in quadratic form like this. Basically, we leave them alone. And then the third root is a well-separated root that is a3 over a2. Okay, so again, plugging in a1, a2, and a3 into that, here is the factorization that we get for this case. And by plugging into this third special case, here are the inequalities that are required here. In this case, we require L1 much greater than L2, and also we require RC much greater than L2 over R, but the in-between or second inequality is no longer required. So with these, we can again simplify these expressions and write the polynomial like this. So this method of approximate factorization can lead to very simple expressions that are simple functions of the element values. So this is a very nice design-oriented way to conquer the algebra and simplify the factorization process and really get expressions that give a lot more insight into how the circuit works. The other thing I would add is that in the case where none of the inequalities are satisfied, then basically we're designing a system that has three roots all close to each other, so you have a cubic type system, and we can't approximately factor it. You're going to have to deal with all of the roots being close together. Okay, we're going to generalize this even further in a couple of lectures, where we're going to talk about how to draw bode plots by inspection. And it is, in fact, one more small step beyond this approach, where we'll be able to just look at a circuit, draw some asymptotes, and get very simple bode plots that are equivalent to doing this kind of factorization. This week we will continue our discussion of frequency response and bode plots, and we will apply the material to power converter transfer functions. So in this lecture I want to work through construction of the transfer functions of the buck-boost converter that we modeled in Chapter 7. So again, here is that equivalent circuit model that we found. And what I want to do now is work out the asymptotes of the magnitude and phase of the control to output and line to output transfer functions. So we've discussed this before as well. If we view the output voltage V hat as the output of our circuit, and we have the control input D hat and the power input VG hat, then we can express the output V hat through superposition as a linear combination of terms that arise from each of the two inputs. And we've already talked then about how to find those transfer functions. The control to output transfer function GVD is found by first setting the other input VG hat to 0, like shown here, and then find the ratio of V hat over D hat, and that ratio then we define as the control to output transfer function GVD. Likewise, to find the line to output transfer function GVG of S, we set D hat to 0, and we find the ratio of V hat over VG hat. So let's work through the solution of each of those and then construct the transfer functions. So first, to find GVG of S. So we'll set D hat to 0. What that does to the D hat voltage source here is to turn it into a short circuit. And to the two current sources that depend on D hat, when we set D hat to 0, they become open circuits with 0 current. So then the circuit reduces down to this one. Okay, next we can push all of the elements to the right through the transformers. So if we push the inductor through this transformer, we'll have to divide by d prime squared, as shown here. And when we push the VG hat source through both transformers, we will, let's see, multiply by d, divide by d prime, and then we have to reverse the direction because the dots are reversed. So we get VG hat times minus d over d prime for that source. So now we have this circuit, and finally we can solve this using the voltage divider formula. So if we view this impedance as the parallel combination, R in parallel with 1 over SC, and then we have this impedance as SL over d prime squared, then using the voltage divider formula, we can write the transfer function this way. So we have the coefficient minus d over d prime out in front, and then multiplied by the voltage divider formula. Okay, at this point I would say R in parallel with 1 over SC is a term that comes up an awful lot, and it's worth working it out and writing it down and memorizing what it is. R in parallel with 1 over SC is R times 1 over SC over R plus 1 over SC. If you multiply top and bottom by SC, you get R over 1 plus SRC. So we can plug that in, so it's shown here and here. And next we can multiply top and bottom by 1 over SRC to turn this into a rational fraction. So if you do that, you get this expression. Now what I would say at this point is we still aren't quite done, because we need to write the poles and zeros in normalized form, where the coefficient of s to the 0 power is 1. So we should divide the top and bottom by r to get that to happen. If we do that, then we'll get 1 in the numerator, and this coefficient of s to the 0 power in the denominator will become 1 as well. So that's shown on the next slide right here. And finally, here's the answer that we get. Okay, we recognize this form now as having a gain out in front that we're going to call GG0. And then it has a quadratic denominator. So we'll write the denominator in the standard quadratic form, which we discussed last week, like this. Okay, by equating like terms in the expression that we have and the standard form, we can get equations for the salient features. So GG0 is apparently equal to minus d over d prime for this converter. The coefficient of s squared in our normalized form is 1 over omega naught squared, and that should be the same then as this coefficient LC over d prime squared. So you can solve for omega naught, and we'll get what? D prime over root LC. And then finally, the coefficient of s to the first power would be 1 over q omega naught in our standard form. That should be equal to L over d prime squared r. So you can plug this expression for omega naught in here and then solve for for q and get an equation for q. Then here is the result. Here's a summary of our salient feature expressions. So we have GG0, omega naught, and q written as nice simple formulas. Okay, now let's work out the control to output transfer function. So this is v hat over d hat, again with vg hat equal to 0. So if we let vg hat be 0, that shorts out this vg hat source. Shorting the source shorts out the current source on the input side as well, which shorts the primary of the transformer. So effectively in our model, the secondary just looks like a short circuit. So then the circuit reduces down to this. We can continue. We can push this voltage source through the transformer. We'll have to divide by the d prime turns ratio and reverse the polarity because the dots are reversed. So that gives us this source. We can also push the inductor through the transformer. We'll have to divide by d prime squared in that case, and we get this. And so the circuit now reduces to this. Well, we still have two d hat sources, so we have quite a bit of work still to solve for the output voltage. Here we can view v hat as actually being a superposition of terms coming from the two sources. Even though the two sources are both d hat sources, we can still write v hat is equal to one transfer function times the first source plus a second transfer function times the second source. So then here is that. Here's the for the first transfer function times the voltage source, with the current source that would have been here set to 0. And here's the second case where we've set the voltage source to 0, and then we get the current source driving these impedances. So for the first case, we can again use the voltage divider formula. The output voltage is this coefficient multiplied by the divider ratio, and it's the same divider ratio as in the GVG transfer function. In the second case, we have the current source driving the parallel combination of impedances, so we can write that the transfer function here is the coefficient I multiplied by the parallel combination of all three elements. By use of superposition, then, we can add these two together to get the total transfer function GVD, and here it is. Now this is still a pretty big, long expression, and it will take quite a bit of algebra and work to simplify it and write it in a standard form. Frankly, I think that it's easier actually to manipulate the model into canonical form and then solve it that way, but this is still a valid way to do it, and if you are able to do the algebra, this is maybe the most straightforward way. So what I will say, I'm not going to do all of this algebra here, but if you simplify this expression, you can get it down to this one, in which we have a DC gain, we have a right half plane 0 in the numerator, and we have a quadratic denominator that is in fact the same denominator as in GVG. So this transfer function then can be written in this standard form, where the coefficient GD0 is this term here. The right half plane 0 frequency, omega z, would be 1 over this quantity. And the denominator q and omega naught are the same as before. So then here is a summary of the equations for the salient features in this case. One other thing I would note is that to simplify the expression for omega z, the 0, from this form into this form, we use the DC relationships that come from solving the DC model. Okay, so we have a nice analytical result where we have equations for the salient features. At this point, if we like, we can plug in numerical values and construct a bode plot. So I've done that here for this example using these values for the element values and the duty cycle. So if you plug those into our expressions, you get these quantities. So the DC gain of GVG is 3.5 dB or 1.5. The DC gain of the control to output transfer function is 187.5 volts. It has dimensions of volts because the duty cycle is dimensionless while the output is voltage. Expressed as dB, this corresponds to 45.5 dB volts. Then we have our quadratic poles at 400 Hertz with a Q of 4, which is 12 dB. And our right half plane 0 turns out to be at 2.65 kilohertz. So then here's a plot of that. So this is the control to output transfer function. We have our DC gain of 45.5 dB volts. We have two poles at 400 Hertz. After 400 Hertz, the function starts to decrease with a minus 40 dB per decade slope. And we have a Q of 4, which is 12 dB at F0. So there's a resonance here, and this value of the function at 400 Hertz would be 12 dB plus 45.5 dB. That's actually dB volts. At the right half plane zero frequency of 2.6 kilohertz, the zero adds plus 20 dB per decade slope, so the composite slope of the entire transfer function then will be minus 40 plus 20, which gives us minus 20 dB per decade slope beyond 2.6 kilohertz. Here are the phase asymptotes. We start at 0 degrees. I actually haven't included the minus sign in the transfer function here, although since we have a negative output voltage, there is actually a minus sign, which would be another 180 degrees of phase, and that's not included in this plot. If we work out the phase asymptotes, the right half plane 0 will have a break frequency at 1/10 of 2.6 kilohertz, which is 260 hertz, and it's shown right there. And that's the first break frequency that we get to. And beyond this 260 hertz, the right half plane 0 will contribute a minus 45 degree per decade slope all the way up to 10 times 2.6 kilohertz, which would be 26 kilohertz. So we have minus 45 degrees per decade there over that range. And then in addition, the complex zeros contribute a slope here that's very large. The slope, recall the formula, is minus 180 Q degrees per decade, with Q is 4, so that would be 4 times 180 negative degrees per decade. So we get a very large slope over this range of frequencies extending from 10 to the minus 1 over 2Q times 400 Hertz, that works out to be 300, up to 533 Hertz, which is 10 to the plus 1 over 2Q times 400 Hertz. So here are the composite phase asymptotes, and at high frequency we finally end up above 26 kilohertz with a constant phase asymptote of minus 270 degrees. Here are the asymptotes for the line-to-output transfer function of the buck-boost converter, and again they don't include the minus sign from the polarity inversion. This transfer function looks similar to the control-to-output transfer function, except it has a different DC gain, 3.5 dB in this case, and it doesn't have the right half plane 0. So the high frequency asymptote is minus 180 degrees rather than minus 270. But otherwise it's similar. Okay, so we've constructed the control-to-output and line-to-output transfer function of the buck-boost converter. I went through really the direct algebraic solution of the model and developed the expressions for the salient features, which we then used to construct the asymptotes. Here is a handy table that lists the salient features of the transfer functions of the three basic converters. So if you have an ideal converter, or if the losses are not significant, you can use this table to quickly get the transfer functions of the basic converters. So what I would say here is that in each case the GVG, or line-to-output transfer function, can be written in this form with two poles and a DC gain. GVD, the control-to-output transfer function, will have the same two poles, it'll have a different DC gain, and it may have a right half plane 0. In the case of the boost and the buck boost converters, we have a right half plane 0, and in the buck converter we don't. This table can also be used for isolated converters containing transformers that are based or derived from these buck-boost or buck-boost converters. So for example, if we have a forward converter, we can use the buck transfer functions, and all we need to do though is include a turns ratio in GVG, which is the transformer turns ratio. And as far as GVD is concerned, the gain is actually written in terms of the output voltage V rather than the input voltage VG. And so the effect of the turns ratio cancels out, and you can apply this GVD transfer function with these coefficients directly. If the converter has inductors on the primary side, then you would have to reflect the inductors through the turns ratio of the transformer. This is the physical turns ratio in before applying these formulas. Now, we've seen right half plane zeros arise in the buck and the buck-boost converters, and they arise in other converters as well. And what I'd like to do now is briefly discuss where the right half plane zero comes from and what its nature is. It actually causes some serious problems in the dynamics of the converter that make it difficult to control. So one way to view the right half plane zero is this, that at low frequency the 1 dominates over the s over omega naught term, and so the transfer function is 1, which is positive. On the other hand, at high frequency, where s over omega 0 has magnitude substantially greater than 1, then this term dominates, and there's a minus sign involved. So at high frequency, we have a phase reversal from the minus sign. In a block diagram form, one way to view this transfer function is that we have a low frequency path this way that has a gain of +1, whereas at high frequency this path dominates, and it has the s over omega z term, and it has the minus sign right there. So one interpretation of this from the frequency domain is that initially for high frequencies the transient response goes the wrong direction because of the minus sign. And then later, when the low frequency gain becomes significant, the phase becomes correct with the plus sign, and the output will follow the input. So one way to think about this then is, suppose that our input signal to our converter is some kind of step. Say we start at a low value and we step up to a larger value. So that's our input. And we would hope that the output would follow the input. Perhaps there's some transient response that has some lag and takes some time to get there, but we would like the output to eventually rise and follow the input. But the right half plane zero response, the characteristic is that the output goes initially the wrong direction. So the output goes down instead of up. And then eventually, after some substantial time, it catches up and goes the right way and follows the input. So why do the boost converter and the buck-boost converter exhibit this kind of behavior? Well, it really comes out of how the switching occurs to connect the inductor to the output. In each of these converters, the current that drives the output coming out of the converter is a diode current. And the diode conducts when the transistor is off. In fact, we can write the equation for the average value of the diode current, and it is d prime times the inductor current. So the inductor current flows through the switch to the output during the d prime interval. And this is true in both the buck and the buck-boost converters. So let's consider a transient where we turn up the duty cycle. Here are some waveforms. So this is our inductor current, including its ripple. It's operating here initially with D of 0.4. And we're switching, so we get some switching ripple like you see here. The diode current is equal to the inductor current when the diode is on, and it's equal to 0 when the diode is off. So here's a sketch of that, the diode current waveform. And its average, which is d prime times IL, is also illustrated here. Finally, I've illustrated the output voltage as well. So at this point right here, we turn the duty cycle up from 0.4 to 0.6. And we would expect the boost converter, with a larger duty cycle would make a larger output voltage, and so the output voltage should rise. But what happens to the average diode current? It takes time for the inductor current to change, and right after we change to D equals 0.6, the inductor current hasn't had time to change much. It's a continuous waveform. So the inductor current goes through some transient, and eventually it builds up to a large value, but initially it hasn't had time to do that. On the other hand, when we change the duty cycle from 0.4 to 0.6 at this instant, the duty cycle immediately goes down. So see what happens to the diode current. The width of the D prime interval is less, and the average diode current immediately jumps down. Well, if you drive the output with less current, then the load can discharge the output capacitor and make the output voltage go down. So you'll see the output voltage initially dip. After some time, the inductor current builds up to a big value. In fact, in steady state, the inductor current goes like Vg over d prime squared r. So with a square, the inductor current will build up to a much larger value. And we see eventually that the average diode current builds up to a value where the average is greater than it was before, even though the d prime interval is shorter. And so with this larger current, we have more current coming out of the converter that can charge the output capacitor up to a higher voltage, and eventually we come into steady state with a higher output voltage. But initially the voltage goes down instead of up. And so this part of the response is indicative of a right half plane zero. Now imagine the effect of this on a feedback loop. We build a control system for our converter that is trying to regulate the output voltage to follow some reference. When the feedback loop sees the output voltage go down, or if the output voltage is less than the reference, then the feedback loop will turn up the duty cycle. So what do you suppose will happen? If we have a wide bandwidth or fast feedback loop, it will see the voltage sag and it will say, uh-oh, the voltage is going down, I need to turn up the duty cycle even more. So it'll turn up the duty cycle again to a larger value, which will make the output sag even more. And in fact, this can be unstable, where the converter will just hit the stops at D equals 1, and the output voltage will go to a low value. It can also cause the feedback loop to oscillate. One way to avoid this is to make our feedback loop slow so that it never even sees the sag. We make the feedback loop change the duty cycle only very slowly, and so it may not even notice the output voltage has gone down or even see anything until we get out here at a later time where the effect of the right half plane zero is gone. So boost converters, buck boost converters, and other converters that have right half plane zeros are notoriously difficult to control. And in fact, before these average models were developed, people didn't understand why, but they did know that boost converters and buck boost converters tended to oscillate, and they were difficult to control. And it was one of the early, I think, victories of averaged converter modeling to be able to predict the right half plane zero and show why these things were happening. In this lecture, we're going to talk about graphical construction of the bode plots of impedances. We will directly construct the asymptotes of impedances on the bode plot, doing a minimum or no amount of algebra beforehand. Effectively, what we're going to do is do the algebra on the plot itself by combining asymptotes. This way, I think, gives a great deal of insight into what's going on. And if you can construct the asymptotes by just looking at the circuit, then you have a lot more understanding of how the circuit works. This method also naturally gives approximations. It is in fact an approximate method, and it provides a framework for coming up with good approximations. Yet another advantage of it is that we can see which impedances don't matter. And so the ones that don't matter we can leave out and not bother with. And it gives a formal way to do that as well. So basically we're going to construct the asymptotes essentially by inspection, and I'm going to illustrate this with several examples. So we're going to start with a simple example of a series combination of an R and a C. So here Z of S is the resistor impedance in series or plus the capacitor impedance. And what we're going to do is construct the asymptotes of each of these individual elements first, and then we'll combine them in the series combination. So first let's do the resistor. That one's pretty easy. It's at 10 ohms and it's independent of frequency. In decibels, 10 ohms is 20 dB ohms, so we're right here. And we'll have this impedance for all frequencies. That line is supposed to be at 10 ohms. So I'm going to label that R equals 10 ohms. Okay, the second impedance, the capacitor, we know the capacitor impedance is 1 over omega C. And this is a function that goes like frequency to the minus 1 power. So we can draw an asymptote that has a minus 20 dB per decade slope. And the only other thing we need to do is to find one point on this curve to draw our line through. So one way to do it is to find the frequency where this impedance equals 1 ohm. Okay, so 1 over omega C equals 1 ohm at what? Omega equals 1 over 1 ohm times C, or F, which is 2 pi omega, would be 1 over 2 pi times 1 times C, which is 1 microfarad, or 10 to the minus 6th farads. So we get 10 to the 6th over 2 pi. 1 over 2 pi is 0.159, so this is 0.159 times 10 to the 6th hertz, or 159 kilohertz. Okay, let's see, 159 kilohertz is right about there. 1 ohm would put us right about there. So we'll draw a line that goes through that point with a slope of minus 20 dB per decade. So if I go down a decade in frequency, we would go up 20 dB. So we'll go through these points, and I'll draw a line through those. So that's 1 over omega C with a slope of minus 20 dB per decade. So these are the asymptotes of the individual impedances. Now next, how do we combine them? We have two quantities that are in series, or actually mathematically we add them. And what are the asymptotes of the sum? Well, let's look at what happens at high frequency and at low frequency. Let's take maybe high frequency first. At high frequency, the capacitor impedance is tending towards 0. And if you go to infinite frequency, the capacitor becomes a short circuit, and the function then goes to just the resistor. In fact, the resistor asymptote is the asymptote of the function, the series combination, at high frequency. Likewise, at low frequency, what happens is that the capacitor tends towards an open circuit. And at DC, the capacitor impedance goes to infinity, so it dominates the series combination, or the sum. So at low frequency, we follow the capacitor asymptote, like that. In fact, all we do then for a series combination is we take the larger asymptote and use that as the asymptote for the series combination, or the sum. In this particular example, this actually gives the exact asymptotes of Z. In other more complicated cases, it won't be the exact asymptotes. This will give an approximation, but nonetheless, taking the largest asymptote is a good approximation for the sum of quantities. So we have a minus 20 dB per decade slope at low frequency and a constant asymptote at high frequency, and we know in fact what they are. They're the resistor or the capacitor impedances. We can also find the corner frequency right here. Let's call that F1. What is F1? Well, F1 is the frequency where the two asymptotes intersect. So we can write at F1, that's where the resistor asymptote, or R, is equal to the capacitor asymptote, 1 over omega C, with omega equal to omega 1. So we can solve then for omega 1. Omega 1 would be, what, 1 over RC. And you can plug in numbers if you like, or you can just read the value off the plot. This turns out to be at 15.9 kilohertz. F1 is 1 over 2 pi RC, and that works out to be 15.9 kilohertz. So we have everything we need. We have the asymptotes, we have the corner frequency. Admittedly, this was a simple case, but this approach generalizes to much more complicated cases. Let's do one that's slightly harder. Here's an RLC network with three impedances in series. So in this case, Z of S is the resistor impedance R plus the inductor impedance SL plus the capacitor impedance 1 over SC. So again, we will construct the individual asymptotes first. The resistor is 1K in this case, so 1 K ohm is 60 dB ohms, and we get this value right up here. The inductor is 1 millihenry. Let's find where 1 millihenry times omega equals 1 ohm. So omega L equals 1 ohm at omega equals, let's see, 1 ohm over L, and F will be omega over 2 pi, so that's 1 ohm over 2 pi times L, with L is 1 millihenry, or 10 to the minus 3 henries. So let's see, that's 10 to the 3 over 2 pi, which is 0.159 times 10 to the 3, or 159 hertz. So let's see, there's 159 hertz. We're at 1 ohm, or 0 dB ohms for the inductor. So we'll draw a line with a slope of 20 dB per decade through that. Next, let's do the capacitor impedance. So we have a 0.1 microfarad capacitor in this example. That impedance equals 1 ohm at what? Omega would be 1 ohm over C. So F would be 1 ohm over 2 pi times C, which is 10 to the minus 7th. So we'll get 10 to the 7th over 2 pi, which is 1.6 megahertz. So we're right about there. We can draw some points for that. Now, to construct the series combination, just as in the last example, we take the largest asymptote at any given frequency, and that is the asymptote of the series combination. So you can see that at low frequency, the capacitor dominates, and we'll follow the capacitor asymptote. At mid frequency, the resistor dominates, so we'll follow this resistor asymptote. And then at high frequency, the inductor dominates, and we follow it. And so those are the composite asymptotes of the magnitude of Z. It looks now like we have two corner frequencies, one here and one here. And again, we can work out what those are. At F1, that's where the resistor crosses the capacitor asymptote. So we have R equals capacitor 1 over omega C with omega equals omega 1. So that omega 1 is 1 over RC. At F2, that's where the inductor asymptote equals the resistor asymptote, so R equals omega L with omega equal omega 2. So we can solve for omega 2 and get omega 2 is R over L. Again, we have analytical expressions for the corner frequencies, and we know what each asymptote is, and so that's everything we need. All right, let's do another example. Let's suppose that we change the value of R so that it's now 10 ohms instead of 1,000 ohms. We'll leave the values of L and C the same. So R is now 10 ohms, which puts it down here at 20 dB ohms. The inductor asymptote is the same. It was 1 ohm at 159 hertz. So I'll draw it again in the same place like that. And the capacitor asymptote is also the same, and I'll draw it in the same place as well. Like this. So using our procedure in the same way, we take the largest asymptote at any one frequency. At low frequency, that's the capacitor. Looks like this. At high frequency, that's the inductor. So we follow this one. And you can see that there's no mid-frequency resistor asymptote for this case because R is too small. So we have a minus 20 dB per decade slope at low frequency and a plus 20 dB per decade slope at high frequency. Right here at this corner, we'll call it omega naught, we switch from minus 20 to plus 20. So let's see, let's first calculate omega naught. At omega naught, that's where the inductor asymptote, omega L, equals the capacitor asymptote, 1 over omega C, with omega equals omega naught. So you can solve for omega naught then. Omega naught squared is 1 over LC, so we get that omega naught is 1 over root LC. Okay, again we get a simple analytical expression for the corner frequency right off the asymptotes. Now one other thing about this is that you can see that at omega naught the slope changes by 40 dB per decade. So that sounds like we have two zeros. It may also be that the zeros are complex, and we should suspect that. So we need to do a little work here beyond this to figure out what is the Q factor of Z. And do we have complex roots here, really complex zeros or not? Well, the way we found the Q factor in previous lectures was we evaluated the exact function and its exact value at the corner frequency. So let's work out what the exact value of Z is at the corner frequency omega naught and see what it does. So at omega equals omega naught, Z of S with S equals J omega, let omega equal omega naught, this would be equal to the sum of the three impedances. So the resistor is R, the inductor is SL with S is J omega naught, so we get J omega naught L. And the capacitor is 1 over SC with S is J omega naught, so we'll get 1 over J omega naught C. And we need to simplify this. Well, we can simplify it by looking at these omega naught L and omega naught C quantities. And if you look at omega naught, that is in fact where omega naught L equals 1 over omega naught C. This is in fact the value of the asymptotes at the corner frequency omega naught. That value we classically call the characteristic impedance, R naught. R naught is defined as the value of the asymptotes, which we could write as either omega naught L or 1 over omega naught C. So at the corner frequency, the inductor has impedance J R naught. Likewise, the capacitor has a magnitude of R naught, and then it's divided by J because it's a capacitor. So we get plus R naught divided by J. Now you can simplify the 1 over J factor again by multiplying top and bottom by J, the square root of minus 1. In the denominator you get J squared, which is minus 1. And so the whole thing goes to R plus J R naught minus J R naught. So the inductor and capacitor impedances cancel out. At the corner frequency omega naught, they have the same magnitude of R naught, but they have opposite phase. The inductor has a phase of plus 90 degrees, and the capacitor impedance has a phase of minus 90 degrees. And when you add them together, they cancel. And so the whole thing just goes to R. Now, to me, this is very interesting that the quantities that depend or that determine the asymptotes are exactly canceling out at omega naught, and then the function goes to whatever is left, which in this case is R. So the actual function goes there and touches the R asymptote right at omega naught, and in the vicinity we get this resonance curve where the function deviates from the asymptotes as necessary to go and become equal to R. Well, R could be anything. It could be absolutely anything, but at omega naught the function goes to R. So this is another way to explain a resonance, that the function will deviate wildly from the asymptotes because the components that determine the asymptotes cancel out, and we go to whatever is left over. The Q factor we defined as the deviation of the actual curve from the asymptotes at omega naught. So this distance here is Q in decibels. If it's not in decibels, it's the ratio. So Q here is equal to R naught, this value, divided by this value, which is R. So we can get an expression for what the Q is also. So far we've talked just about series impedances. Let's talk next about parallel impedances. So here's an RLC example where we have a parallel network, and we want to compute the composite Z of S for this. So we're going to start out in the same way by constructing the individual impedance asymptotes. And here I've used the same values as in the last example. So R is 10 ohms. L is 1 millihenry, which we drew asymptotes like this for L. And C is again 0.1 microfarad, which we drew with asymptotes right here. With a parallel combination, which component dominates? Well, let's write the equation of Z. So Z of S is found by the parallel impedance formula, which is inverse addition. So R in parallel with SL in parallel with 1 over SC. This notation means that we add the impedances using inverse addition. So this is 1 over R plus 1 over SL plus 1 over the capacitor impedance 1 over SC. At any given frequency, which impedance will dominate the inverse sum? Well, the smallest impedance will have the largest inverse, so it will dominate the inverse sum, and then when we take 1 over that, we get that impedance back. So at low frequency, the inductor is smallest, and we'll follow the inductor impedance. Here at mid frequency, the resistor is smallest, so we follow it until we get to high frequency where the capacitor impedance is smallest. And then those are the asymptotes of the composite Z of S. Looks like we again have two corner frequencies, back in F1 and in F2. Again, F1 is where the inductor asymptote intersects the resistor asymptote. We've already done that one. We found that F1 was R over 2 pi L. Likewise at F2, that's where the capacitor asymptote intersects the resistor asymptote. That happens at 1 over 2 pi RC. So looks like we have two real poles in this case. The asymptotes are changing from a plus 20 slope to a 0 slope to a minus 20 slope. Right, let's change the value of R back to 1K for this parallel resonance circuit. Let's see, at 1K, R ends up being up here again. Let's draw our L and our C. There's omega L and omega C. We'll go there. So who dominates the parallel combination now? Well, at low frequency, the inductor is smallest, so it will dominate. At high frequency, the capacitor is smallest, so it dominates. The resistor is never smallest, so it doesn't determine the asymptotes anymore. We have a plus 20 dB per decade asymptote at low frequency and minus 20 at high frequency. Right here, where the inductor asymptote and the capacitor asymptote are equal, which is at F naught, the inductor and capacitor asymptotes become equal, and we get a corner frequency. Again, since we change from plus 20 to minus 20 slope at this corner frequency, we should suspect that there's a resonance. This looks like there could be complex poles in this case, and so we again need to work out what is the exact value of Z at this corner. Well, let's use the inverse impedance or inverse sum formula. Z is 1 over R plus 1 over j omega L plus j omega C. We'll let omega be omega naught. At omega naught, both the inductor and capacitor asymptotes have the same magnitude, again R naught, or the characteristic impedance. And so Z we can write as 1 over R plus 1 over JR naught for the inductor, plus, in this case, J over R naught for the capacitor. If you multiply top and bottom of the inductor impedance by J, we get minus J over R naught for the inductor and plus J over R naught for the capacitor. So the inductor and capacitor terms again cancel out, and Z goes exactly to R. So we peak up and touch the R asymptote right at the resonant frequency. So again, we get a curve with a resonance that goes up and touches R. In the parallel combination, the inductor and capacitor again cancel out in the inverse sum, just as they did in the sum. So with this parallel resonance circuit, then the impedance goes to what's left, which is the resistor. We again have a Q factor. Then, in this case, Q would be this value in dB minus the characteristic impedance in dB, or if it's not in dB, it would be R divided by R naught. So we have an expression for the Q factor in this case as well. In the parallel resonance circuit, Q is R over R naught, whereas in the series resonance circuit, it was R naught over R. So again, with a resonance circuit, we can work out the individual asymptotes, find the composite, and get everything that we need. Okay, I want to do one last example. Here's a somewhat more complex circuit. You can do the same tricks with more complex circuits. We just keep applying the series and parallel formulas, taking the larger or smaller asymptotes, to build up the composite asymptote of Z. A good way to start here is to break this down into smaller sections. So maybe we'll call this parallel R1 and C1, I'll call that Z1. So that's R1 in parallel with 1 over SC1. And we'll call this lower network Z2, which would be R2 in parallel with 1 over SC2 in parallel with SL2. So what we'll do is construct those and then finally put them in series to get Z, so that Z is Z1 plus Z2. So let's start. Z1 is R1, which is 100 ohms or 40 dB ohms. So there's R1. C1 is 16 microfarads. We can work out the frequency where 1 over omega C1 is 1 ohm, and that turns out to be at 10 kilohertz. So here's the 1 over omega C1 asymptote. The parallel combination of R1 and C1 then, we'll take the smallest, which is this, and that's Z1. It has a corner frequency right there. Frequency we'll call F1. F1 is where R1 equals 1 over omega C1, and that works out to be 100 hertz. For Z2, let's construct those asymptotes. R2 is 10 ohms, so that's 20 dB ohms, and it's right there. C2 is 1.6 microfarads. It goes through 1 ohm at 100 kilohertz, which is right there. So here's our C2 asymptote. And then L2 is 16 millihenries. We can work out where omega L2 equals 1 ohm, and that turns out to be at 10 hertz, right here. So we can draw a plus 20 dB per decade slope for L2, like that. So let's put all the red asymptotes in parallel, R2, C2, and L2. So we'll follow L2 at low frequency, then R2 at mid frequency, and then C2 at high frequency. And that would be the magnitude of Z2. We get a corner in it right here at 100 Hertz and another corner here at 10 kilohertz. I'm going to call the 10 kilohertz corner F2, which is 1 over 2 pi, let's see, R2 times C2. To construct the composite asymptote now, we simply take the larger of Z1 and Z2. So take the larger of this blue cross-hatched line with the red cross-hatched line. You can see that Z1 dominates at low frequency. Until we get right here at 1 kilohertz, we'll call that F3, where the C1 asymptote crosses the R2 asymptote. So F3 is at 1 over 2 pi times C1 times R2. After that, we follow the Z2, or red cross-hatched asymptote. We get to F2, and then we follow the capacitor C2. And the green asymptotes then are the composite asymptotes for Z. So we can build up the impedance of a fairly complicated circuit and easily construct the approximate asymptotes of the composite impedance Z. One thing I'll say here is that unlike maybe the very first example, these are not exact asymptotes. They're approximate. And one way you can see that is, for example, at high frequency, where the two capacitors dominate. And at high frequency here, we're taking C2 as being the dominant impedance. If you look at the circuit, at high frequency, really we have C2 in series with C1, which is, in fact, slightly less than C2 in value. We're making an approximation here, and it's a pretty good approximation, but it's an approximation nonetheless. You can't expect to be able to simply draw straight line asymptotes and get exact factorizations of higher order polynomials. So this is, in fact, an approximate solution with an approximate factorization. I would suggest that it is really the graphical equivalent of the analytical factorization method that we talked about last week. Another interesting thing that comes out of this is that the L2 asymptote doesn't play a role in the final composite impedance asymptotes. Omega L2 is actually too large in value to come into play where it would have a significant effect. And so it may not be obvious from looking at the original circuit that that's the case, but you can see from looking at the asymptotes here and the way we constructed them as to why that happens. It's actually just as important to be able to make approximations to see which components don't have an impact as it is to see which ones do. And so if in fact you simply threw out L2, approximated it as an open circuit, and just drew the asymptotes of these components, the resistors and capacitors, you would get a good approximation of the final result. So being able to simplify the circuit and construct the asymptotes that depend only on the dominant impedances and nothing else is a very valuable thing to be able to do. And this is a structured way that leads to approximations such as that as well. In the radio frequency business, this kind of approximation was widely used, but generally in an earlier day than today. Something called reactance paper, or also here called impedance graph paper, was widely distributed among RF engineers. And this is basically a bode plot, but it has inductor and capacitor impedance asymptotes already plotted for you. So this slide has something like that in PDF form. So if we have a, say, combination of maybe a 1 millihenry inductor in series with a, say, a 1 ohm resistor, and then that's maybe in parallel with maybe 10 microfarads, then we can easily plot the composite impedance by just following the 1 millihenry line until we get to 1 ohm, and that's the series combination of 1 millihenry and 1 ohm. And then we put the 10 microfarads in parallel, which is this impedance, and there you go. There's your bode plot. So this is a very easy and quick way to construct pretty complex impedances right on the plot. In the last several lectures, we've discussed how to use graphical construction directly on the bode plot to construct the asymptotes of series, parallel, and more complex impedances. In this lecture, I want to extend these ideas now to talk about constructing transfer functions. And in an upcoming lecture, we're going to further extend this to talk about constructing the closed-loop transfer functions of feedback systems. So to construct a transfer function using these graphical techniques, what we do is to express the transfer function as a ratio of impedances. We then construct the impedances graphically and then divide to get the transfer function. So here's a very common example where we have an RLC filter network, such as the one in our canonical model, and we want to find the transfer function h of s from the input voltage to the output voltage. So we can do this using the familiar voltage divider formula. If we call this element Z1 and these collection of elements here is Z2, then we can express the transfer function as Z2 divided by Z1 plus Z2 according to the voltage divider formula. Now Z1 plus Z2 is in fact the input impedance looking in here from the input source. We'll have Z1 in series with Z2. So we can also write this simply as a ratio of impedances as Z2 divided by that input impedance. So one way to construct the transfer function is to construct the bode plots of Z2 and of the input impedance and then divide. We'll talk in a minute about how to divide graphically. Another way to do it is to express the transfer function in this way. You could, for example, multiply by Z1 and then divide by Z1 and write the transfer function like this, and you recognize that this Z1, Z2 over Z1 plus Z2 is the parallel combination of the two impedances. Yet another way to look at that is to take the input source and Z1 and construct a Norton equivalent circuit. So the input source and Z1 can be written as an effective current source in parallel with an impedance, and the Norton equivalent is found in which the current source is the short circuit current between these terminals, or the voltage divided by Z1. So V1 over Z1. And the Norton equivalent impedance here is in fact Z1, or the impedance between the terminals when the voltage is set to 0. So we could apply this transformation, and we have to connect Z2 in parallel. And you can see then that the output V2 is equal to the current V1 over Z1 times this parallel combination of these impedances, Z1 in parallel with Z2. The parallel combination is in fact the output impedance of the network. If you short the input voltage source and find the impedance seen from the output terminals, you get Z1 in parallel with Z2. So this alternate method then is to write the transfer function as z out divided by z1, according to this formula. And again, we've expressed the transfer function as a ratio of impedances. So you can use either way, either the first one or the second one, and I would suggest that you use whichever one is easiest to construct. It turns out that the second one for this particular circuit I think is easier, although you could do it either way. In the second case, the output impedance is just the parallel combination of the three elements, and we've already constructed that. And Z1 is simply the inductor impedance. So let's construct then this transfer function h of s as the ratio of the output impedance divided by Z1. Okay, I'm going to do an example of that here on some semi-log axes, although the next slide contains the results. So let's suppose that we've constructed, or we have some values for R, L, and C. I'm going to just choose some arbitrary numbers. So let's suppose the inductor has some omega L asymptote that looks like that. The capacitor has a 1 over omega C asymptote, perhaps looking like this. The resistor maybe is here, just for some arbitrary choice. And so to construct the output impedance or parallel combination, as usual, we take the lowest asymptote. So we get asymptotes like this in red for Z out. We have a corner frequency right here at F naught, which is 1 over 2 pi root LC, as we've discussed previously. There's a characteristic impedance R naught that is omega naught L, or 1 over omega naught C, or simply root L over C if you eliminate omega naught. And we have a Q factor where the inductor and capacitor cancel out at the corner frequency, and the output impedance rises up to be what's left, which is the load resistance. So we get a Q factor that would be R divided by R naught. So that is our Z out asymptote, our set of asymptotes. We have to divide that by Z1, which is the inductor asymptote. So Z1 I'll draw as simply following omega L. I'll draw that one in green. And finally we'll construct the ratio. So to divide asymptotes, or to divide impedances, we simply divide the expressions for the asymptotes. So over some given range of frequencies, we express each impedance by its asymptote and divide to find the asymptote of the transfer function. Once again, I'll remind us what h of s is. It's Z out divided by Z1. So at low frequency, below F naught, Z out and Z1 are both omega L, or they follow the omega L asymptote. So the asymptote for H is omega L divided by omega L, or 1. My axes are labeled in dB ohms, but I'm going to draw H in just dB on the same axes. So we'll draw H at 0 dB all the way up to F naught. So I'm going to label the magnitude of H, which is the magnitude of Z out, divided by the magnitude of Z1. And for these low frequencies below F naught, we get omega L divided by omega L, or 1. Okay, above F naught, Z1 remains omega L, but Z out becomes 1 over omega C. So what we have for Z out divided by Z1 will be 1 over omega C divided by omega L. And the slope will have Z out will have a slope of minus 20 dB per decade. When we divide by Z1, we subtract its slope, which is 20 dB per decade. So we get a composite slope of minus 40 dB per decade. So I need to draw a minus 40 dB per decade slope there, like this. And the equation of this asymptote here then, H is again Z out over Z1, but Z out, as I mentioned, what now becomes 1 over omega C, and then we divide by omega L, and so the expression of this asymptote is 1 over omega squared LC. So we have two poles at F naught. Now one last question is, what is the Q factor? Well, to find the Q factor for H, we find the exact value of H at the corner frequency, and the exact value of H is the exact value of Z out divided by the exact value of Z1. So what will that be? Well, Z out, the exact value is R, and Z1 has an exact value of R naught at F naught. So the ratio will be R over R naught, which is Q. Therefore, H has the same Q factor that Z out had. So if Q is that distance, then we'll get the same distance here, and the actual function will have a resonance curve as well. So I'll label that distance. So Q is Z out of j omega naught divided by Z1 of j omega naught, which is, again, R over R naught. So graphically we can get everything we need simply by taking the ratios of the impedances. Okay, again, all of those quantities are listed here on the next slide. Let's apply this then to the canonical model. Our canonical model of power converters contains exactly the filter that we just solved with a transfer function that we've been calling HE of S. So we can construct HE of S by the method I just described. The only slight complication is that we have an effective inductance LE that might depend on duty cycle. However, we can handle that. The asymptotes for the inductor impedance, again, follow as usual. So here's our output impedance, as we just discussed. Here's the graphical construction of the output impedance with our capacitor, resistor, and our LE asymptotes. And we can identify the Q factor. So we get a transfer function then with asymptotes like we just constructed, with an F naught corner frequency given by the point where the capacitor and LE asymptotes intersect, and with a Q factor defined by R divided by that characteristic impedance. In the boost and the buck boost converters, LE is given by L over D prime squared. That's what we found in an earlier lecture. So what happens to the inductor asymptote then when we change the duty cycle? Well, let's see. If you increase the duty cycle, that will make D prime decrease, and so 1 over D prime squared will increase. So increasing the duty cycle makes L over D prime squared increase, and the asymptote then will go up like this as you increase the duty cycle. Well, you can see what that does to the corner frequency. If we have a larger effective inductor asymptote, then that will move the corner frequency down to a lower frequency. And you can also see what that does to the Q factor. When we increase our inductance, we increase R naught. So a new R naught will shift from here to here, and then the Q factor, which is this distance, will become smaller. So we get a lower Q when we increase the duty cycle. So it's a fairly simple matter from constructing the asymptotes to see what happens when things like the operating point change. What does this do then to the corner frequency, or the transfer function? So we previously had a transfer function that had a low frequency asymptote of 0 dB, and we get a corner frequency here at f0 with some Q factor, and when we increase the duty cycle, the low frequency 0 dB asymptote doesn't change, but the high frequency asymptote, corner frequency, and Q factor all change. So this will move down to this frequency with this smaller Q, and then we'll have our minus 40 dB per decade slope then. So the graphical construction method then can give us everything we need. We can just construct all of the impedances, transfer functions, asymptotes, corner frequencies, and Q factors directly, and in the process get a great deal of, I think, physical insight as to how changing things change the results of our converter circuit. We'll now begin the last chapter of the course, Chapter 9 on controller design. We're going to apply the models developed in Chapter 7 and the transfer functions analysis developed in Chapter 8 to the problem of designing power converter control systems in this chapter. So what I want to discuss in this lecture is the object of our feedback control systems, and we're going to introduce these then around these switching converters. And then in upcoming lectures, we're going to talk about the design of the control system. So to introduce the topic, we have then our switching converter with an output voltage that for now we're going to treat as the output, although we have other examples where we're controlling other things like currents. But let's take the example of an output voltage controller. So the output voltage then is a function of the different independent inputs to the converter. We have the power input VG, we have the duty cycle input D, and we may have other variations such as load current variations that also affect the output voltage. So just as a functional block, we can view the switching converter for this example as having an output that we identify as the output voltage, and we have inputs that affect the output voltage from VG, from the load current, from the duty cycle, and possibly other quantities. In the DC voltage regulator application then, the object is to make the output voltage be a fixed and well-controlled value. However, the output voltage is a function of all of these quantities such as VG and the load current. So you can't expect to just set the duty cycle to one value and always get the desired output voltage. So if there are variations, for example, in VG, they will affect the output voltage, or variations in the load current can affect the output voltage. And so what we want to do is adjust the duty cycle automatically to regulate the output voltage. And we view then VG and the load current as being disturbances. What we'd really like to do is make the transfer functions from these disturbances to the output voltage be as small as possible, and we would like the output voltage to follow some controlled reference and not be a function of VG or the load current. Some typical examples. If VG comes from the rectified AC power line, then that rectified voltage has second harmonics of the power line. So in a 50 or 60 hertz AC system, the second harmonic will be 100 hertz or 120 hertz. And so VG may have some VG hat variations at 100 or 120 hertz. And those will propagate through the switching converter according to the line to output transfer function at 100 or 120 hertz to produce variations in V. So one of the classic things we want to do with feedback then is to build a feedback loop that adjusts the duty cycle to remove these variations in V. Or another way to look at that is to make the transfer function from Vg to V at 100 and 120 Hertz be as small as possible. Likewise, if there are load variations, they affect the output voltage through the converter output impedance, and what we would like to do then is make the output impedance of the converter be as small as possible. Load current variations may also have step changes that can be very significant, and our feedback loop can affect the output voltage response to, say, a step change in current. Circuit elements may have tolerances, there may be variations in component values, and we would like the output voltage to stay regulated and not be a function of those variations or tolerances. So all of these are reasons to add feedback to a power converter system, and we invariably have feedback in practically every power converter. Here's a classic feedback system then, a simple negative feedback controller where we sense the output voltage through some sensor gain. Often this sensor is just a voltage divider that may divide down the output voltage to a value that is more convenient to work with in our control circuitry. But we get a voltage signal here, H times V then, that is proportional to the output voltage. With a negative feedback system, we compare that sensed output voltage to a reference. And this reference voltage is well controlled. We will go to some lengths to build an accurate reference voltage that doesn't have variations due to temperatures or initial tolerances or aging. So we have a well-known reference signal. We compare the feedback output to that reference and find what's called an error signal that tells us how much the output voltage differs from the error. The object here is to make the error signal equal to 0. If we do that, that means the feedback output voltage exactly equals the reference. So we can say that the object of feedback is to make the H times the output voltage equals the reference. Now, a feedback loop is not perfect, but we can approach this value and have the difference between these two quantities be very small. The error signal goes into what's called a compensator. Typically, the compensator is simply an op-amp circuit in an analog feedback loop. If we're building a digital controller, then we may have an A to D converter or analog to digital converter and then some digital controller. The output of the compensator is a control signal that goes into the pulse width modulator, which we've already discussed, and causes a duty cycle or controls the duty cycle that the power transistor operates at. Okay, what can you do to make the error signal small? Well, some students initially think that there's something wrong here, because if we have an error signal of 0, doesn't that mean that the compensator output is 0? And doesn't that mean the duty cycle is 0, which means we don't get any output voltage? So how can that work? Well, that's the wrong way to think about it. Here's a better way to think about it. Let's suppose we want an output voltage of whatever, say 5 volts. What duty cycle does it take to get 5 volts? Well, that depends on Vg, but there's some value we can find. And so we need a certain duty cycle coming out of our pulse width modulator, which means we need a certain voltage going into the pulse width modulator. I'll call capital Vc, which maybe is a couple of volts, whatever the number works out to be. So given that voltage, how can we make the error signal small? Well, the error signal, VE, is actually Vc divided by the compensator gain, G sub C. If you want to make the error small, what we need to do is make the compensator gain big. So if Vc is, say, 2 volts, that's what it needs to be. If we can build a compensator that has a gain of 1,000,000, then the error signal will be 2 microvolts. which means that the reference and the feedback error, or the feedback output voltage, differ by only 2 millivolts. So that's pretty good regulation. If you can make the compensator gain arbitrarily large, then we can make the error signal arbitrarily small. And then that is really the thinking behind this negative feedback system. We'll refine the block diagram now of the negative feedback system. So we have blocks for the sensor, which I said had a gain that we called h of s. We have our reference input and our error signal. The compensator gain we call g sub c. The pulse width modulator we've already modeled in previous lectures and previous homework. So it has a gain that was 1 over v sub m, the height of the ramp. And that produces a duty cycle that drives the switching converter block. So there is a feedback loop then through the duty cycle to the output going around this loop. Then we also have these disturbance signals. So VG hat and I load hat are variations that propagate through the converter to the output, and these disturbance transfer functions are things that we want to minimize to make V not depend on these disturbances. To refine the model of the converter block, we use our canonical model for the converter, which we previously solved. So we represented the output voltage V hat as a linear combination of terms coming from the different independent inputs to the converter. And here I've represented VG hat, D hat, and also the load current variation I load hat as independent sources in this model. We can find transfer functions from each of those disturbances to V hat by solving the canonical model. So we previously solved GVD and GVG. We can also find the output impedance. We've actually worked that out graphically already and include it as well. So here is our converter equivalent circuit model with those disturbances included. And here is our block diagram of the feedback network. We can perturb and linearize the elements in the feedback loop as well, and so I've explicitly written these feedback elements and block diagrams in terms of hat quantities. So the output of the sensor is h of s times v hat now, and we've removed the DC components, or quiescent values, of the signals in the feedback loop. The reference, then we have v ref hat. In some converters there is no variation in the reference, although many times in DC regulators nowadays we do have variations in the reference as well. So I'm going to leave it in as v ref hat. We have an error signal VE hat then, that is the AC variation in the error signal, and so on. Then here is our block diagram including the transfer functions of the converter power stage, with the small signal variations VG hat and I load hat driving their respective transfer functions. So this is a block diagram now that we can solve. Okay, the solution is given on this slide, where we've actually gone through and solved the block diagram to find this. I'm not going to do the details of this manipulation, but I am going to outline them. What we can do is write an equation for the error signal. VE hat is given by V ref hat minus H times the feedback output voltage, V hat. And we also have an equation for V hat. V hat is what? GVG times VG hat minus Z out times I load hat plus GVD times D hat, which is in turn the error signal VE hat times these gains GC and 1 over VM. So what you do is you take this VE hat expression and you plug it in over here to eliminate VE hat, and then you solve for the output voltage. So if you do the algebra for that, here is the result. This looks fairly intimidating, but in fact it can be written in a simpler form. If you recognize that all of these terms have the same denominator, and this quantity right here is called the loop gain, and we're going to call the loop gain T of S in this course. So the loop gain appears there, it appears here, and it appears here. And actually you can multiply this top by H and then divide by H, and then the loop gain appears there also. The loop gain is actually the gain around the feedback loop. You start at the error signal and follow all of the gains around the loop. We get G sub C times 1 over Vm times GVD, and then times H. And we stop right there. We don't include the minus sign of the summing node. So those quantities, by convention, are defined as the loop gain. In a negative feedback system, we leave the minus sign out of our definition of T, and it was assumed in solving the loop that it was there. So that is, in general, how we find this quantity in the denominator. So written in terms of the loop gain T, this expression can be simplified into this form. Okay, this is the expression for what we call the closed loop transfer functions of the converter. So this expresses V as a function of the Vref variations times this transfer function, plus Vg hat variations times this transfer function, and then we have the I load variations times this transfer function. So this is what we need to know about what happens after we close a feedback loop. Now, what are the effects of the feedback loop on the transfer functions? The key result here is that feedback reduces the transfer functions from disturbances to the output. So the transfer function that we found for the Vg hat term was this. GVG is the original line to output transfer function of the open loop power stage, and that gets divided by 1 plus the loop gain after we close the feedback loop. So what happens to that transfer function? Well, if you make the loop gain big, for example, if we put this compensator in our feedback loop that has a gain of 1,000,000, which will make T bigger by a factor of 1,000,000, then that reduces this transfer function. So in fact, this disturbance gets reduced through feedback by this factor of 1 over 1 plus T. So if we can make T equal to 1,000,000, then this factor will be 1 over 1,000,001, and the variations in the output caused by Vg hat variations will be reduced by that factor. The same arguments apply to the output impedance, and really the output current variations, I load hat, is just another disturbance. So here is our open loop output impedance, which was this parallel RLC circuit that we have previously constructed. That transfer function, basically output impedance, gets divided by 1 plus the loop gain also. And so the output impedance is effectively reduced by feedback by this factor of 1 plus T. So again, if T is 1,000,000, then the output impedance is reduced by a factor of 1,000,001, and we can get a very low output impedance so that load current variations have very small effect on the output voltage. Now, this business of T being 1,000,001 is actually true only at low frequency. All amplifiers have to roll off, and at high frequency their gains are much smaller. So we'll find that we can reduce the output impedance by a lot at low frequencies, but at high enough frequency that doesn't work anymore. So we're going to have to work out exactly what the transfer function of T does and what the effect is at all the frequencies of interest on these closed-loop disturbance transfer functions. Okay, we had one other term in our equation, which came from vref. And this transfer function from vref hat to the output voltage turned out to be this. And it has a different dependence on t than the other transfer functions. What happens to this transfer function if t is big? Say, take our example where t is 1,000,000. Then t over 1 plus t will be 1,000,000 divided by 1,000,001, and basically it's equal to 1. So this term goes essentially to 1, and the overall transfer function from the reference to output then becomes 1 over h, like this. This is a really nice result because it means that the output voltage follows the reference very well, and the gain is just 1 over h. And it's very interesting that it doesn't depend on anything else in the system besides h. The dependence on t cancels out. So for example, if our compensator changes, or if our control to output transfer function GVD changes, it has little effect on this gain because those variations will cancel out. So we say that feedback makes the transfer function from the reference to the output be insensitive to tolerances and variations in the components in the forward path of the feedback loop, things like GC, VM, and GVD. So to accurately control the output voltage, all we need to do is accurately control the reference and accurately control H. Well, if H is some voltage divider with some resistors, that means we buy some accurate resistors, say 0.1% tolerance resistors for our voltage divider that becomes H. And we also have to build a good reference to supply the reference voltage accurately. But you can buy integrated circuits that have accurate references. So we do that, and then we're in business. The output can be well controlled, and it will depend only on the reference and H and not on anything else. Okay, that's the basic idea of feedback, and these are the important transfer functions. In the next lecture, we're going to construct the bode plots of the different transfer functions. In the last lecture, we found that the quantities t over 1 plus t and 1 over 1 plus t are important functions that we need to find to compute the closed-loop transfer functions. In this lecture, we're going to talk about how to construct those quantities in a very easy and simple way with no algebra, but rather by using the algebra on the graph or graphical construction approach, which is really a generalization of a lot of these graphical construction techniques we talked about in the last chapter. So I'm going to illustrate this with respect to an example. And so here is a loop gain, T of S, and just an arbitrary one that I've chosen. It has a DC gain, T0, which here is some fairly large value, 50-something dB. It's got two poles with a Q factor, then there's a 0 and another pole, and so it looks like this. This is a fairly complex function with a fair number of poles and zeros, and so if you tried to add 1 to it and then refactor and compute 1 over 1 plus t or t over 1 plus t, it's a pretty tedious chore. You'll get cubic type denominator polynomials that will be hard to factor. And so it's not a very good candidate for algebra. And here's the approach. To approximate 1 over 1 plus t or t over 1 plus t, we use some of the same tricks for approximations that we used in Chapter 8. Namely, whenever we have a sum of terms, we approximate this using the largest. So here in the denominator we have 1 plus t. If you look back at this typical t, I've identified what's called a crossover frequency here, where t passes through 0 dB. And so above the crossover frequency, the magnitude of t is less than 1, and in fact the farther up in frequency you go, the smaller t gets, and so it quickly becomes much less than 1. Likewise, at low frequencies, the magnitude of t is bigger than 1, and if you get very far down in frequency below the crossover frequency, this magnitude gets very large. 60 dB is a gain of 1,000, 40 is a gain of 100, so we're talking 2 orders of magnitude or more. So the quantity t over 1 plus t, we can approximate then for low frequency where t is large in magnitude, we can approximate the denominator by ignoring the 1 and just taking the t. And in that case we get t over t, which is 1. On the other hand, at high frequency where t is small in magnitude, we'll approximate the denominator by throwing out the t and just use the 1. And so t over 1 then leads to t. So this is what we get at high frequency or above the crossover. Similar process for 1 over 1 plus t. At low frequency where t is large, we throw out the 1 and we get 1 over t. Or at high frequency, we have the opposite case, so we throw out the t and we get 1 over 1, which is just 1. Okay, these are very easy to construct. Here I've drawn the asymptotes of t again, and to find t over 1 plus t, we have then our two cases bounded by the crossover frequency. At low frequency where t is large, this just becomes 1, and at high frequency where t is small, this becomes t. So here's our low frequency asymptote, and here are our high frequency asymptotes. So you can see that compared to t, the quantity t over 1 plus t doesn't have the low frequency poles and zeros. These go away, and in fact what happens is they get moved up in frequency effectively, and we get instead a pole, or perhaps more things, at the crossover frequency. Okay, the quantity t over 1 plus t is important in the transfer function from the reference to the output. And what we found previously was that the output over the reference transfer function was 1 over h times t over 1 plus t. What we would like is for this to simply be 1 over h so that the output follows the reference with a simple gain of 1 over h. So that's indeed what happens where t over 1 plus t is 1. So here v over v ref is just approximately 1 over h. But at high frequency that's not the case. So really within the bandwidth of the feedback loop, which means below the crossover frequency where we have large loop gain, then the feedback loop works well and makes the output follow the reference. But at higher frequencies the feedback loop runs out of gain, it no longer works, and then what actually happens is the gain reduces back to the open loop case. So in this case, where t over 1 plus t goes to t, the overall transfer function, v over v ref, becomes t over h, which is in fact just the gains in the forward path of the loop. For the same example, let's construct now 1 over 1 plus t. This is the quantity that multiplies the transfer functions from disturbances to the output. Here's our same t again, and to construct 1 over 1 plus t, we again have two cases. Above the crossover frequency where t is small, this quantity just goes to 1, And below the crossover frequency where t is large, this quantity goes to 1 over t. Okay, so 1 is easy enough to draw. It's up here at high frequency. And then at low frequency, 1 over t is found by finding the mirror image, or flipping this t upside down. Basically, we reflect t about the 0 dB axis. The zeros of t become poles in 1 over t. The poles of t become zeros in 1 over t. And this DC gain becomes a DC gain of 1 over the DC gain, or in decibels minus the dB. So then here is what our 1 over 1 plus t quantity looks like. What is the interpretation of this? Well, a transfer function from a disturbance to output, say from Vg to the output, is equal to the original open loop transfer function, GVG, divided by 1 plus t. So we take the original transfer function with no feedback loop and we multiply it by this quantity. So what happens is that, first of all, at high frequency where we don't have much loop gain, the feedback loop doesn't change the disturbance transfer function. So it has no effect, and you get the same thing that you get in the open loop case. So that's what happens here. But at low frequency, where we have a lot of loop gain, then our transfer function from the disturbance to the output is reduced by the amount of the loop gain. So V over Vg then becomes the open loop gain divided by t. So if we have a loop gain, say, of 60 dB at some frequency, then this transfer function from Vg to the output is reduced by 60 dB by the feedback loop, which is, therefore, we'll have minus 60 dB of gain relative to the open loop case, or 1/1000th of the output variation that we would have if there was no loop. So this is a measure then of how much loop gain we need to make the loop reduce the disturbances. We'll do several examples next week using these criteria. So we will construct these t over 1 plus t and 1 over 1 plus t asymptotes, and we will use them then to shape our loop gain to design the system to meet requirements regarding rejection of disturbances such as load current variations and Vg variations. One last short note about terminology here. Sometimes students are confused by this. We call things open loop or closed loop. So when we talk about an open loop transfer function, what we mean is the transfer function of the original power stage before introducing a feedback loop. On the other hand, the closed loop transfer functions are what we get with the feedback loop present, so they're the transfer functions like these. And then finally, we have a quantity just called the loop gain, neither open loop gain or closed loop gain, but just the loop gain, which is the T of S, gain around the loop. In this lecture, we will discuss stability. In the previous lectures, we found how to construct the loop gain and the important quantities t over 1 plus t and 1 over 1 plus t. These important quantities govern the closed loop transfer functions of the control system. For example, to construct t over 1 plus t, we found that this had an asymptote of 1 or 0 dB, where the loop gain t is large in magnitude, and where it's small in magnitude, it follows t. So for this example, we get asymptotes that look like this. Now let's take a look at these asymptotes. They don't include the poles right here at FP1 that were present in t, nor do they seem to include this 0. And instead, we have a new corner frequency at the crossover frequency f sub c. So it would appear that these corners have moved up to f sub c. In fact, what happens is that the poles do indeed move. One of the poles may cancel this 0, and the other will move up here to f sub c. So what is apparent is that the act of closing a feedback loop can move the poles around. Now, that's both good news and bad news. The good news is you can move the poles to other places. And in this example, we end up increasing the bandwidth of our system so that these low frequency poles down at about 30 hertz get moved up to the crossover frequency of greater than a kilohertz. But the fact that the poles can move is also bad news because the feedback loop can move the poles anywhere. And sometimes they get moved to bad places, such as in the right half of the complex plane, where we get unstable responses, or where we may have undamped or lightly damped type resonant responses, such as this. Here's an example of a response where, for example, the input or the reference perhaps took a step change. So maybe we could think of our reference as doing this. And then here's the response of the output voltage, V hat, which is trying to follow the reference. And it eventually does follow the reference, but there's a transient response that may include things like overshoot and ringing. Oftentimes in a power system, we don't like this kind of overshoot and ringing, and it's not allowed. For example, if this was a computer power supply where we were trying to feed 3.3 volts, say, to a processor, maybe this is the turn-on transient, we don't want to overshoot to twice that, or 6.6 volts. We'll blow up all of the chips, the processor chips. Another example where this might be undesirable is if we have, say, a robot arm and we're trying to control the position of the robot. And we're commanding the robot position to change from, say, this value to that value. But instead, first it swings past the value and comes back. And maybe going past that value makes your robot arm go through the wall or something. So we very often can't allow this kind of response. So we get new poles at the crossover frequency, and those poles can be resonant. They can be associated with a Q factor right here. So we may have a closed loop response that includes some Q factor. And that resonant response leads to overshoot and ringing like this. So this is something that we generally have to control, and the control of exactly where these closed loop poles are, what their Q factor is, whether they're stable or unstable, is the stability problem. Here's another way to look at it, just the algebraic approach. Suppose that our loop gain T has some numerator polynomial, I'll call n of s, and a denominator polynomial, we'll call d of s. We can simply plug that in for t and see what we get. So t over 1 plus t, if we plug this expression in, we can do the algebra, and we find that the denominator polynomial becomes n of s plus d of s. So it's a different polynomial than the original d of s. To find the poles of this denominator, we have to do quite a bit of work. We'll have to add the two polynomials together and refactor them. It actually turns out to be not so simple to do in the general case. And that algebra and refactorization often is not very illuminating. So one of the key topics of the classical control field is finding simpler ways to understand the nature of these new poles at the crossover frequency without having to do this refactorization. Here's an example of how the poles can move. So let's say we have some original open loop system with a transfer function g of s. We close a feedback loop around it with some feedback gain h of s, so that we get a loop gain then that's g times h. And we'll do an example where G is this fairly simple looking expression. It has a DC gain of 100, and then it has 3 poles. So there's 3 roots of the denominator, each at s equals -1. And in the complex S-plane then, we have 3 poles here at -1. Okay, we'll add a simple feedback loop now. So this is our G of S, and we're going to add a feedback loop having a gain of 1, or H of S equals 1, and let's calculate what the closed loop poles are from V in to V out. So we have already found that V out over V in is 1 over H times T over 1 plus T. H is 1 and T is G, so we get this. We can plug in our transfer function for G. We can do the algebra and multiply out the transfer function to find the denominator. We find that there's a cubic polynomial in the denominator, which we have to refactor. Well, it's not so easy to refactor this by hand. This is done here numerically with a root finding program, and we find that this is the denominator. So this cubic polynomial has 3 roots. One of them is at s equals -5.64, which is right there. So one of the roots at s was -1 gets moved out to there. The other 2 roots are complex, and they in fact have positive real parts. So these roots are at s equals plus 1.32 plus or minus j4.07. So the other 2 roots moved to here and to here. Now these 2 roots are in the right half of the complex plane, and they have positive real parts. They indicate an unstable response. The reason for this is that if you take the inverse Laplace transform of this transfer function for some given input, you find that the output contains terms that go like e to the pole times t. So with the inverse Laplace transform, we'll get a term that is some constant times e to the -5.64t, which is okay. That's a decaying exponential that decays to 0 and indicates a stable response. But the other 2 are e to the plus 1.32t and times e to the minus j4.07t. So these indicate a growing oscillation. They're a response whose amplitude grows, or the envelope here grows, like e to the 1.32t. And the complex part is the oscillatory part. So, by having poles in the right half of the complex plane, we get solutions that have positive real exponents and are growing exponential or growing oscillations, and therefore we get an unstable response. So this is maybe fairly innocent looking at first. We don't have any minus signs in the denominator or anything, but nonetheless it turns out that this has poles in the right half plane and constitutes an unstable feedback loop. Okay, the refactorization of the denominator, again, is not so easy to do in practice. And so in the classical control business, there are quite a few different techniques to get around the problem of having to refactor the denominator. What we would really like to do is to see how we should shape the bode plot of t to make the closed loop response, including these new poles, be well behaved and do what we want. So we have these tests on the loop gain t that determine what the closed loop poles do. One of the general tests from classical control theory is called the Nyquist stability theorem. We don't have time to explain this. If you want to learn this, it's worth learning, and you should take a control class. But what we're going to use is a special case of this that is called the phase margin test, which is a test that we can apply to the bode plot of t and deduce what these closed loop poles do. this is a nice design tool because it lets us change or work with the bode plot of t and change our loop gain, shape it to give the kind of response that we need. So it's a nice design-oriented tool. I'll state, though, that this phase margin test is not the most general. There are some cases where it doesn't work, and we'll discuss those as well. So here is a statement of the phase margin test. So again, this is a test on t, the loop gain, and this test determines whether 1 over 1 plus t and t over 1 plus t have right half-plane poles. So what we do is we first find the crossover frequency. We've already talked about the crossover frequency, but to state it correctly, the crossover frequency is the frequency where the magnitude of t is 1 or 0 dB. Once we find that frequency, then we find the phase of t at the crossover. So this is the phase of t at the crossover frequency. What you do is you add that phase to 180 degrees. The result is called the phase margin. And if the phase margin is positive, then we have a stable feedback system. Okay, now there are special cases. You can build loop gains that have more than one crossover frequency, and some of those might have positive phase margins and some might have negative. And in that case, really, we need to revert to the more general Nyquist criterion. But I'll say that in those cases, usually the loop is unstable. This test also applies really only if the original loop gain, or t, has no right half-plane poles to begin with. So we have to have a system that is open loop stable. Generally in power electronics we have that, but if it's unstable to start with, it's possible to apply feedback to stabilize the system, but we can't apply the phase margin test. We need to use some more complex classical control theory to do this. So having said all of that, the bottom line is that we find the phase of the loop gain at the crossover frequency at 180 degrees. That's our phase margin. We want a positive phase margin for stability. Here's an example. So here is some given loop gain. It has a DC gain here that's, say, 40 dB or a gain of 100. It has two poles with some Q factor at some low frequency. So after that we roll off with minus 40 dB per decade, and those two poles cause the phase to change from 0 down to close to minus 180 degrees. We also have a higher frequency 0, which changes the slope so that we go to a minus 20 dB per decade slope after that, and this 0 gives some positive phase, so that at high frequency the phase of t is minus 90 degrees. Okay, just from looking at the plot, you can see the crossover frequency is right there. Here's the phase of t at the crossover frequency. This says the phase of t. If you work out what that value is, this says it's minus 112 degrees for this example. So if we add 180 to minus 112, we get plus 68, and that is the phase margin. It turns out to be this distance is the phase margin. The phase margin is positive, and so this is stable. Here's a few more details on exactly how we calculate that in practice. A good way first to find the crossover frequency is to write the equation of this asymptote. You have to estimate over which range of frequencies the crossover frequency occurs, and then write the equation of that asymptote. So here's our expression for t that has a DC gain, the 0, and the two poles. The equation of this asymptote at high frequency, if you recall, is found by taking the largest term everywhere we have a sum. So in the numerator, we're at frequency above omega z. S over omega z will dominate over the 1, and we throw out the 1. We're also at frequency well above omega p1 or fp1, so this term will dominate the other two denominator terms, and we throw them out. When we do that, we get this expression, And you can simplify it and write it this way. And finally, if that's the equation of the asymptote, what we do is we equate that to 1 to find the frequency where the asymptote is equal to 1, and we get this equation for the crossover frequency. Of course, there may be some small deviation from the asymptotes. It looks like that deviation will not be very large, but this is an approximate solution. It's a lot easier to use this approximate solution, though, than it is to work with the exact equation with radicals for the magnitude. Once we know this crossover frequency, now we can evaluate the phase right here. So we need the phase of t. There's really two ways to do that. One way is to work with the exact equations for the phase of each of these terms. So that's shown here. This is the expression that we had for the phase of a 0. And this is the expression we had for the phase of complex poles. And so what we can do is add the two expressions and get the total phase. The expressions are somewhat complex, but you can, if you have a calculator or a spreadsheet or MATLAB or something, it's not hard to evaluate. The other way to do this is to use the phase asymptotes. So we could write the equation of this asymptote over this frequency range, which appears to be the correct frequency range that includes the crossover frequency Fc. So for this, to write the equation for this asymptote, what we do is we add the equations for each of the asymptotes of each of these corners. So we're at frequency much greater than the resonant pole corner frequency, and the poles will give a phase asymptote of minus 180 degrees, which is this term. Then the 0 right here is near the crossover, and we're on the part of its asymptote that has a plus 45 degrees per decade slope. So we need to write the equation of that, and this is the equation for a phase asymptote. It has the slope plus 45 degrees per decade. And then we're on a log scale, so this asymptote is a function of the log of frequency, and what you have to do is take the base 10 log of frequency divided by the break frequency for that asymptote. So the break frequency for this asymptote would be at 1/10 of the corner frequency, or Fz over 10. And we have a plus 45 degree per decade slope starting there. So the correct expression then is the base 10 log of frequency divided by the corner frequency over 10. So here is an equation of the phase asymptote. You can decide which one of these is easier to use. The asymptote is quite a bit of an approximation. This one is, of course, the more accurate one. Neither one is easy to do in your head. So we use one or the other of these to evaluate the phase of t at the crossover. Plug that in here, add that to 180 to get the phase margin. Here's a second example. This is a case where the 0 is turned into a pole. So we have our same DC gain of 40 dB, or 100. We have our same two poles with a Q factor, but then this next corner is also a pole, so that we have a total of 3 poles. The high frequency phase asymptotes then go to minus 270 degrees, and if you work out what the phase is at the crossover frequency, it says here that it turns out to be minus 230 degrees. So the phase margin then is minus 230 plus 180, which gives us minus 50 degrees. This is less than 0, and therefore this is an unstable system. You might go back to the previous example that had 3 poles at s equals 1 and work out the phase margin if you want an exercise. Okay, so we have the phase margin test that tells us stability. The next question we'll ask in the next lecture is how big does the phase margin need to be? In the last lecture, we found that the phase margin test is a way to determine the stability of the closed-loop transfer functions based on the loop gain t and its phase at the crossover frequency. In this lecture, we're going to ask how much phase margin is enough. Is 1 degree of phase margin sufficient? Certainly what we found in the last lecture is that if we had a phase margin of plus 1 degree, then our phase margin test would say that the closed loop system is stable. Now, of course, perhaps we want more margin than that in a good, robust design, and so we need some amount of additional phase margin to make sure we have a sufficient cushion for reliability and accounting for variations in components. But there's actually more to it than that. The phase margin also determines the closed loop response. At least it's a measure of the closed loop transient response in some sense. And so in this lecture we're going to discuss the relationship between the phase margin and the Q factor of the closed loop poles of t over 1 plus t that occur at the crossover frequency. And what we're going to find is that the larger the phase margin, then the better the response is as far as having less overshoot and ringing and having a lower Q factor for these poles that are near the crossover frequency. We're going to actually make a dominant pole approximation and characterize the closed loop response of t over 1 plus t and 1 over 1 plus t as having two poles near the crossover frequency that have some Q factor. And we'll find a relationship between that Q factor and the phase margin of t. So this is a nice design tool that really tells us how much phase margin we need and then provides a design criterion for how to shape the loop gain to give us a good closed loop response. I'm going to explain this relationship using a simple second order system in which we assume that the loop gain t has this form. So there is a low frequency pole that we're going to approximate for simplicity as a pole at the origin. So this 1 over s over omega naught term is a term that goes to infinity magnitude at dc, and then it rolls off with a minus 20 dB per decade slope, and it has a magnitude of 1 or 0 dB at omega equals omega naught. So it has this characteristic, or this asymptote, and it goes through 0 dB at f equals f naught or omega equals omega naught. And then we'll have a second pole at high frequency, at frequency omega equals omega 2 or f equals f2, that will cause the slope to change to minus 40 dB per decade after that. Now the real loop gain may be more complex, but if we can approximate the loop gain t in the vicinity of the crossover frequency like this, then this should be a good approximation of what happens in t over 1 plus t in the vicinity of the crossover frequency. So perhaps the real t actually has multiple poles and zeros that are happening at very low frequency with all kinds of things going on. But when we get near, say, within a decade or so of the crossover frequency, we can approximate t like this. So this, in fact, is a good approximation for many of the systems that we want to design, and in fact the results will apply to even more cases simply than this. How does this behave as far as phase is concerned? Well, this s over omega naught term in the denominator gives us a phase of minus 90 degrees, and then the second pole at omega 2 gives us a phase asymptote that decreases towards minus 180 degrees at high frequency. And so the phase margin then will lie somewhere between 0 and 90 degrees. depending on exactly where the crossover frequency is relative to f2. Let's use this approximation for t and calculate the closed loop response. So we can work out what t over 1 plus t is when we plug this in for t. And in fact, the easy way to do that is to first divide the numerator and denominator by t. And what we get is 1 over 1 plus 1 over t. And 1 over t is really easy to calculate if we plug this in. So what we find is that t over 1 plus t becomes this expression that has two poles. All right, we can write these two poles, or this denominator, in our standard form to identify a corner frequency omega c and a Q factor. What we find when we do that is that omega naught omega 2, this coefficient of s squared, is equal to this coefficient omega c squared. So we get that omega c is root omega naught omega 2. We'll find that when we plot omega, or frequency, on a log scale, that this square root of the product is the geometric mean, which on the log scale lies halfway between. So omega c is halfway between omega naught and omega 2. So if we go back to this plot, here's f naught and f2, and fc is halfway in between. Okay, we can also work out what q is. So by equating q omega c to omega naught here, we can find that OQ is omega naught divided by omega c, or alternatively we can write this as square root of omega naught over omega 2. So then here is the t over 1 plus t transfer function. What we have is two poles at this fc that is halfway between f naught and f2, and it has a q that was omega naught over omega c, or f naught over fc. And if you work out what that is, that turns out to follow the low frequency asymptote here. If you the equation of the low frequency asymptote is f naught over f, and if you plug in f as fc, you get this value q, which is right there. So the actual value of the function, as I've drawn here, lies below the 0 dB asymptote. And in fact, we have the low Q case. You can approximate what the two poles are then using the low Q approximation that we've already talked about, where we'll have one pole at Q times omega c, which turns out to be omega naught, or right here at f naught, and the other pole is at omega c over Q, which turns out to be omega 2, or f2, right there. And the low Q approximation then gives us what we would get by using the approximate construction of the asymptotes as we previously discussed. So this is the low Q case. Let's consider the high Q case. Suppose you move f2 down to a lower frequency, and here we're going to choose f2 to be below fc. So f naught is again the frequency where the low frequency asymptote passes through 0 dB. We have to extend the low frequency asymptote in this case to find f naught. And f2 is the second pole frequency. fc is again halfway between. In this case, the previous arguments still apply. Q is omega naught over omega c, or f naught over fc, which now is a number bigger than 1. We have a Q larger than 1, and the exact function goes up and touches this low frequency asymptote and then comes down. So this is the high Q case, and we have this Q that grows. It's larger and larger as f2 goes to a lower and lower frequency. Well, what is happening as far as phase margin goes? If we move f2 to a lower frequency, you can see that that will move this phase asymptote to a lower frequency, and our phase of t at the crossover gets lower. And as f2 goes to dc, our phase margin goes to 0. And as this happens, we find that the closed loop Q grows. We can work out an expression for the exact phase margin of our original t, and we can plug that into our expression for the Q of the closed loop poles, and with some algebra we can find this expression for the relationship between the Q of the closed loop poles, and the phase margin from T. There's what it turns out to be. Takes some algebra to do that. Or alternatively, you can solve for the phase margin in terms of Q, and here's an expression for what phase margin it takes in order to get a certain closed loop Q for this example. Here's a plot of that result. So this is phase margin of T on the horizontal axis, and Q of the closed loop poles of T over 1 plus T on the vertical axis with Q expressed in decibels. So that's the answer. You can see that if you want a Q of 1, which is 0 dB, right here, it takes this phase margin, which works out to be 52 degrees. Or if you'd like Q of a half for your closed loop poles, which means we have real poles, that takes a phase margin of 76 degrees. And the smaller the phase margin, the higher the Q factor is. So this phase margin of 1 degree would give us a very high Q and a very large resonance in our closed loop transfer functions. And that's a very good reason to require more phase margin. So we need phase margin not just for a yes-no stability test, but we need phase margin to keep the resonance in our closed loop transfer functions at a controlled and low value. Okay, the next question is, how much Q can we allow? Well, that really depends on your application. But let's see what the impact of having a higher Q is. Well, this is really an exercise in constructing inverse Laplace transforms. Let's suppose that we have this closed loop transfer function with these complex poles, and what we want to do is work out, say, the step response. So we'll have some input to our transfer function that will take a step in its Laplace transform. Then we can express as, say, a unit step function can be written in Laplace transform domain as 1 over s. You can multiply that by this second order response and then take the inverse Laplace transform to work out the exact time domain response in the output that we get. So this is also an exercise in algebra and inverse Laplace transforms, but the result in the case where Q is greater than a half, so that we have complex poles, is this. So if our input is a unit step function, then our output is this time domain response. In the case of real poles, we get decaying exponential type responses, and here's what that is. Okay, that's a pretty big expression. Here is a plot, though. So again, our input is a unit step that's doing this. We would like the output to follow that, and it eventually does settle down and follow that, but there is some transient that happens following the step. So for low Q, we have these decaying exponential type responses that vary monotonically and eventually settle down to follow the input. And for high Q, we have these ringing or sinusoidal type responses that have overshoot and ringing, but the ringing decays in amplitude and eventually it settles down. So one has to decide whether overshoot is allowed. One also has to decide how fast we want the response to be. Q of a half is the case where we have two real and repeated roots. This is actually the fastest response that has no overshoot and ringing, and it's this response right here. This is called the critically damped case. Q greater than a half gives us complex poles. This is called the underdamped case. These responses are faster, but they have overshoot and ringing and take some time to settle down to the final value. Whereas Q less than a half gives us what's called the overdamped case, where we have two real roots that are at different values, and we get decaying exponential type responses that are slower but don't overshoot. So often we think that the critically damped case for Q of a half is the best because it's the fastest response with no overshoot. On the other hand, we might allow a little bit of overshoot, so a Q of 1, say, has maybe 15 or 20% overshoot, which we have to decide if that's acceptable or not, but it is a faster response and requires less phase margin. Generally, in power applications, we can't allow overshoots heading towards twice the final value like we get in the lightly damped case with very little phase margin. This type of overshoot and ringing usually will cause higher stresses on our components, where the voltage will go to twice the final value, and usually we can't allow that. Here's a nice little function that is the peak. We can solve this function to find the peak value, and this is what it becomes as a function of Q. So this peak for the underdamped case is the value of the first peak right up here, say right here, as a function of Q. So if we decide how high we can allow the peak to be, then we can solve this to see how much Q that requires, and then we can go back to the previous plot here to see how much phase margin is required. One other thing about this plot is that the horizontal axis here is labeled in units of radians of omega c times time. So if you have a requirement that you want the settling time or the rise time to be so many, say, microseconds or milliseconds, then we can plug that time in here for t and actually work out what the crossover frequency omega c needs to be. For example, if we have Q of a half and we want a settling time of some number of seconds, we may define settling time as the time that it takes the waveform to get within some amount, like say within 10% of the final value, and stay there. So we can draw some boundary that's 1 plus or minus 0.1 or 10%, and then see that, okay, if we have Q of a half, then right there is where we get to within 10% of the final value, and that's maybe 4 radians. So you can plug in omega c equals 4 and then solve for what omega c is required to get the given t, or time that is the specification. You can also see that Q of 1 will rise faster to this value, but then it will overshoot and go out of the box, and it doesn't get back in the box until right there. So it actually has a longer settling time, but a faster rise time. So one can decide exactly what one needs from the application, and then use a plot like this to choose how big the crossover frequency needs to be, and ultimately what is the bandwidth of the feedback loop. So from this kind of plot, then, we can get a requirement on both what omega c should be and what Q should be, and then that in turn tells us what the phase margin should be and what the feedback loop crossover frequency should be. One last thing I need to point out is that I explained this with respect to simply an example. I chose this somewhat arbitrary loop gain, although I did argue that this loop gain is one that can approximate a great many actual loop gains in the vicinity of the crossover frequency. It's possible to choose other loop gains if their closed loop response is well approximated by a second order system in the vicinity of the crossover frequency. Then in fact you get the same answer, which is this. And there's actually a good fundamental reason for that. That as long as you correctly work out the magnitude and phase of t and relate it to Q, you will get the same answer if the system can be approximated by this dominant pole or two-pole second order system in the vicinity of the crossover frequency. Now, of course, you can design more complex feedback loops whose closed loop response has more than 2 poles near the crossover frequency, and in that case you can't characterize the response simply by this parameter Q and omega C. It takes more parameters. So in that case, you have to do more work and use more advanced control techniques to work out what happens. But in fact, the vast majority of our systems, feedback loop systems that we design in power electronics, do end up being second order systems, and we can use these simple arguments then to design them. In the typical design of a control system, we have these kinds of specifications and requirements. First, we may have variations in the load current, which cause variations in the output voltage. And we would generally like to maintain regulation of the output voltage regardless of what the load current does. So there will be a limit on the maximum variations in the output voltage that result from load current variations. And essentially, this is a limit on the maximum allowable output impedance of our closed-loop system. A similar problem is the effect of input voltage variations, or VG hat variations, on the output voltage. And so again, we may have some maximum amount of input voltage variations that we are expected to see, and this requirement then limits the magnitude of the transfer function from the input voltage to the output voltage. So in previous lectures, we've discussed already how to work out the closed-loop transfer functions, and we found that we can construct the closed-loop output impedance as the open-loop output impedance divided by 1 plus the loop gain, and likewise the closed-loop transfer function from VG to the output we can construct as the open-loop GVG divided by 1 plus the loop gain. These are then the closed-loop disturbance transfer functions, and we want to design our feedback loop to make each of these quantities be sufficiently small so that the output voltage is regulated. The other kinds of requirements that we get relate to the last lecture. So we may have some transient response time requirement, which means that we want to respond to a disturbance in a certain amount of time. And so this requires a sufficiently high crossover frequency and bandwidth of the feedback loop. Also, this transient response may have overshoot and ringing. Generally, we want to limit that. And so we need an adequate phase margin in order to achieve that requirement. So these two issues were discussed in the last lecture. The problem of designing a feedback control system then is one of shaping the loop gain so that we have the adequate phase margin, we have an adequate crossover frequency, and we have a large enough magnitude of the loop gain to make these disturbance transfer functions be sufficiently small. So what we'll talk about in this lecture then is how to add poles and zeros and gains to our loop gain to shape it and change it so that we meet all of these kinds of requirements. And this addition of poles and zeros is done through generally what's called a compensator network. It's another block that we add to our feedback loop that often contains things like op-amp circuits in an analog feedback loop. And this is the place then where we can add these poles and zeros to shape the loop gain and get what we need. So we're going to talk about several of the classic kinds of compensator networks. The first one is called a lead compensator traditionally, or a PD, proportional plus derivative control compensator. And the object of this kind of compensator network is to improve the phase margin. So how can we improve the phase margin of a loop gain if we don't have enough? Well, we know that zeros add positive phase, so naturally we can think of adding a zero to our loop gain. Here is then a plot of a loop gain that has a 0 right here, and after that frequency we have a gain that increases, so we get this compensator that has some DC gain, and then it has a 0. Now, one immediate problem or practical problem with this is that this transfer function by itself with a 0 implies that the gain gets larger and larger as the frequency increases, and in fact as you go to infinite frequency this circuit has infinite gain. Now, this is not at all practical. All amplifier circuits must roll off at high frequency, and if you go to a high enough frequency there's no more gain. So there's at least one pole to flatten out our gain, and in fact there's more than that. There's at least one more after that to make the gain roll off. We'll talk more about this when we do an example of designing an op-amp circuit for a practical compensator. So what's shown here is a pole then that makes our compensator gain flatten out at high frequency, and we'll assume that any further poles are at a high enough frequency that they don't affect what happens here in the vicinity of our crossover frequency where we're going to design. The phase asymptotes of this transfer function are constructed below it. The 0 will give us phase asymptotes that extend a decade on either side of the 0 frequency, and likewise the pole will give phase asymptotes that look like this, that go down to -90 and change over a decade on either side of the pole frequency. So here's FP over 10 and 10 FP. The phase asymptotes will have this is FZ over 10 and 10 FZ up here. When you combine those asymptotes, the slopes over the range from this frequency to this frequency will cancel and will flatten out, and then above that frequency we'll eventually come back to a net 0 degrees phase shift. So the composite asymptotes are sketched here. The maximum phase happens right at that frequency. So if we want to improve the phase at the crossover frequency, we should set the crossover frequency to be this frequency where phase is maximum. So we'll set that equal to crossover frequency f sub c. This is a log scale in frequency, and so halfway between these two phase break frequencies on the log scale is the geometric mean, which turns out to be at the square root of the 0 frequency times the pole frequency. So that's what we should set equal to f sub c. Then this phase here we'll call phi or theta max, or perhaps just theta on the next slide. So that's the phase lead that we get out of this network. We can work out the exact phase of this transfer function and calculate what theta is as a function of fz and fp. That's actually done on the next slide. So here is the answer. The frequency where the phase is maximum is at this geometric mean, which we will set equal to the crossover frequency. And the value of that phase, if you work out the exact function, it turns out to be expressible like this. So here's a plot of the maximum phase lead that we get as a function of the ratio of the pole frequency to the 0 frequency, which is on this axis. So for example, if we place the pole at 10 times the 0 frequency, like this, then we'll get this much phase lead out of our network, which looks like it's, about 55 degrees. And so we can actually figure out what ratio of frequencies of the pole and 0 we need to get a certain amount of phase lead. Here is the relationship between the pole over 0 frequency versus this maximum phase theta. So to design a lead compensator then, or a PD compensator, we want to set our crossover frequency to be right there. and our pole and zero frequency will be spaced evenly about it, and we will choose that ratio of frequencies to make this maximum phase give us enough additional phase to get the proper phase margin in our loop. Here then is what we need to do. So FC is the crossover frequency, theta is the amount of additional phase that we need out of this compensator network, and here are the expressions then that we can solve for the zero and pole frequencies of our compensator. One last little point is that this compensator also has a gain that can move our overall loop gain up and down. If you don't want to change the crossover frequency of your loop, you need to make this gain right here be unity gain, so that it doesn't change the gain at the crossover frequency. Well, that means that this gain at low frequency will be less than unity. Here is, in fact, an expression from the gain, which you can derive by writing the equation of the asymptote. If we want to change the gain of the loop at the crossover frequency, then we can set this quantity equal to whatever gain we need and solve for the value of GC0 that it takes then to achieve that gain. So this slide is the bottom line. This is the design equations that we need to design the PD compensator. Here's a brief example, and we'll do some more involved examples in upcoming lectures. But what I've shown here is an uncompensated feedback loop that has two poles with a Q factor, and then it rolls off with a two-pole slope after that. It passes through 0 dB right there, so this is our crossover frequency. And here are the phase asymptotes for the uncompensated loop gain T. In the vicinity of the resonance, the phase changes very quickly from 0 to minus 180 degrees. And by the time we get up here to this high frequency where we have a crossover, the phase of T is basically minus 180 degrees, and we basically have no phase margin. So what we need to do is add a PD compensator network to add a zero and pole that will improve our phase margin. Here I've illustrated one where the zero is below FC and the pole is above FC, as on the previous slide, so that our compensated loop then does this. We maintain the same crossover frequency, but the zero and pole give us some additional phase, so that we now have some positive phase margin here, which is in fact equal to the amount of phase we're adding from our compensator for this example. One of the things it does is reduce the DC gain, and so with this type of compensator we're not concerned with the DC gain or the gain of T at other frequencies. All we're really trying to do is improve the phase margin. Here's a second classical type of compensator network called the lag compensator, or the proportional plus integral controller, or PI controller. The object of this type of compensator is to increase the loop gain at low frequency so that we can regulate better and have more loop gain. Here's a transfer function of the classic PI compensator. I've expressed it here as an inverted zero. So it has a gain that looks like this. This term here is the integrator. In the Laplace domain, an integrator divides by S. And then, so that's the I part of the PI controller. And then this is a proportional part, or proportional gain, that's P. And so we have proportional gain, and we have an integrator at low frequency that increases the low frequency gain. This kind of compensator does not improve our phase margin at all. In fact, at low frequency, it makes the phase more negative, so that's not good. Generally, what we do with a PI compensator is we try to not disrupt the high frequency phase. So the PI compensator has 0 degrees of phase at high frequency, And generally we'll want to have our crossover frequency somewhere up here, where the PI compensator doesn't mess up our phase margin. But what we do is we use the compensator to improve the low frequency gain and get better regulation so that we reduce the disturbance transfer functions at low frequency. Here's a brief example of a lag compensator. In this case, our initial uncompensated loop gain is this one. It has a low value of gain at DC. In fact, it has next to no loop gain. And then it has a single pole with a single pole slope at high frequency. The phase of the uncompensated gain then is 0 degrees at low frequency, and then the pole gives us a minus 45 degree per decade slope, and we end up at minus 90 degrees at high frequency. Our phase margin is not a problem. Looks like here, if we cross over at this high frequency, we'd have 90 degrees of phase margin, and that's not the problem at all. Instead, the problem is that we have next to no gain at low frequency, and our loop doesn't do anything. So we need to boost the gain. Now, the first thing we could do is simply add more DC gain to our entire loop. So we could bring the whole loop up by maybe that much, and just scale the whole curve up so that we have a gain like this. But then we can do even better if we add an inverted zero here and get very large gain at DC. The inverted zero might be chosen to be a decade in frequency below the crossover so that it doesn't change the phase margin, but it simply gives us more low frequency gain. Here is a plot of the quantity 1 over 1 plus t for the compensated loop gain. So recall that this quantity 1 over 1 plus t reduces disturbance transfer functions in the converter, such as the output impedance or the line to output transfer function GVG. As you recall, 1 over 1 plus t is found as being essentially equal to 1 or 0 dB at high frequency and 1 over t at low frequency. So increasing t with this PI compensator will reduce 1 over 1 plus t and therefore reduce the disturbance transfer functions and give us very good rejection of disturbances and very good regulation of the output voltage at low frequencies. Finally, here is a PID compensator, or a combination of the previous lag and lead compensator networks. So what we have here is a PD compensator from those two terms, which gives us this zero and this pole. I've also shown us another pole, a second pole at very high frequency. As I mentioned, this was present in a practical amplifier. And then finally we have the PI compensator, which gives us this inverted zero at low frequency. So this compensator network has all the terms. This is often what we will do if we have a second order system, such as a continuous conduction mode buck type converter, to compensate. The crossover frequency, as in the PD compensator, will be chosen to be halfway between the zero and the pole, so that our crossover frequency will be here, and we'll get some improvement in phase margin from that. And then we'll have our PI compensator inverted zero be at some frequency sufficiently less than the crossover frequency and improve the low frequency gain. The way to design one of these is to do these quantities one at a time. So I would first design the PD compensator part to improve the phase margin, and after that add on an inverted zero or PI compensator to improve the low frequency gain, and get a composite transfer function like this. In upcoming lectures, we're going to discuss first design of some of this type of compensator, and I'll do a practical design example. And we'll also talk about how to realize op-amp compensator circuits to realize a transfer function such as this using the ideas that we've discussed in previous lectures. In this lecture, we'll do a design example where we're going to design the compensator of the feedback loop for a buck converter with output voltage regulation. So the object in this system is to produce an output voltage of 15 volts. So the first thing we should do is decide what the sensor or feedback gain H of S should be. In this example, we have a reference voltage that is a well-regulated and accurate 5 volts. So as we've discussed previously, in a well-designed feedback loop, the error signal will be 0, or at least very, very small. And so the fedback output voltage, H times V, should be equal to the reference when the circuit is working in steady state. So we have 5 volts here, and that means that H, therefore, should be 1/3. So we'll have a gain of 1/3, and our 15 volts will turn into 5. So H equals 1/3. With this choice of values, we can work out the quiescent operating point of the converter, define, for example, the steady-state duty cycle. We're not going to model losses, so the steady-state duty cycle would be 15 volts divided by 28 volts for the buck converter, and we can work out the other quantities such as the control voltage and other things from there. So here is a list of the voltages and duty cycle at this quiescent operating point. Knowing that, we can now plug in the small signal model for our buck converter. And here is the buck converter AC model that we have previously derived. I also have shown a block diagram then for the rest of the feedback loop. We can solve this AC model for the buck converter then to find the important transfer functions. So the control to output transfer function, GVD of S, for this buck converter, we've found previously for the buck is this expression. We'll plug in the numbers from the previous slides to these component values, and what we find is that we have a DC gain in GVD of 28 volts, which corresponds to 29 dB volts. And we have a resonant frequency, F0, that turns out to be 1 kilohertz. So we'll have a 2-pole slope beyond 1 kilohertz. The Q factor works out to be 9.5, which corresponds to 19.5 dB, so you can sketch in the resonance from that. And we can also sketch the phase asymptotes of GVD. By using our phase asymptote formulas, we find that the phase asymptotes have break frequencies at 900 Hz and 1.1 kilohertz, so the phase changes very sharply over that narrow frequency range from 0 degrees down to minus 180 degrees. So there's our control to output transfer function. We can also work out the line to output transfer function and the output impedance of the converter power stage as usual, and here are the expressions for those. So given all of those things, then we have this complete system block diagram with the converter power stage model as we previously discussed, and with the transfer functions of the buck converter included, and we have our feedback loop as well. From this block diagram, we can work out the loop gain. So the loop gain T will be the compensator gain, GC, times the modulator gain, 1 over Vm, times the control to output transfer function, GVD, and then times the H of S. So that's these quantities. And when we plug in our GVD of S with its 2 poles, then we get this. So let's first plot the uncompensated loop gain. This is the loop gain T of S when the compensator gain is 1. So we haven't designed a compensator yet. Let's see what our starting point is. So the uncompensated loop gain then has the two poles from the control to output transfer function, and then it has a DC gain that is the product of these DC gains around the loop. This DC gain works out then to be 2.33 or 7.4 dB, so we have a fairly low DC gain in our uncompensated loop. And then we have our same two poles at 1 kilohertz with a Q of 9.5. So there's the complete loop gain without a compensator. You can see that the crossover frequency looks like it's right there from the drawing, which is 1.8 kilohertz, and the phase at that point is almost minus 180 degrees. There's actually a little deviation from the asymptote, and if you work out the exact phase at that point, we find that it's minus 175 degrees, so our uncompensated loop would have a phase margin of 5 degrees. Well, so this is our starting point. I would say some defects in the uncompensated loop gain are, first of all, we don't have much phase margin. Second of all, we could probably push this crossover frequency up to a higher frequency and get some more bandwidth. And third, we don't have much low frequency loop gain, so our loop won't do much of a job of regulating. First thing we'll do then is design a lead compensator to improve the phase margin. So we've discussed already how to do that. What we're going to do is I'm going to try to design for a crossover frequency of 5 kilohertz, which is here. It's 1/20th of the switching frequency. So we'll need to increase our loop gain by this much to push our gain up at 5 kilohertz so that our crossover frequency ends up being there. We'll also need to add some phase. So we'll need to improve our phase margin, and I'm going to design for a closed loop Q of 1. If you recall our plot of Q of the closed loop transfer function versus phase margin of T, if we want a closed loop Q of 1, this means we need a phase margin of 52 degrees. Looking at this plot for the uncompensated loop gain, at 5 kilohertz there really is basically no phase margin. So we need to design a compensator that will add 52 degrees at 5 kilohertz, and we'll add this much gain at 5 kilohertz. From working out the asymptote of T, the expression for the asymptote of the uncompensated T, one finds that the existing loop gain at 5 kilohertz is minus 20.6 dB. So we need to add 20.6 dB more of gain at 5 kilohertz to get the crossover frequency to be there. Here were the asymptotes of the lead compensator from the previous lecture. We'll then want this frequency here to be the crossover frequency, FC, or 5 kilohertz. And we'll want this phase right at this point, that we were calling theta, to be plus 52 degrees. This slide is also from the previous lecture. These are the formulas for designing the lead compensator. So again, FC is 5 kilohertz, and theta is our 52 degrees. So we can simply plug the numbers in and see what zero and pole frequency we need. Then here are those computations. It turns out our zero needs to be at 1.7 kilohertz, and the pole needs to be at 14.5 kilohertz, and our compensator DC gain needs to be 11.3 dB, or a gain of 3.7. Here is a bode plot of that then. So this is our 5 kilohertz right there. Let's plot the compensated loop gain now with this compensator. Here's the original loop gain with the DC value of the uncompensated loop gain and its two poles. And then these three terms are the added terms that come from our compensator with our zero, pole, and additional DC gain. When we add those into our loop gain, we'll get the zero right here and the pole right there. The phase asymptotes then are increased, so we have our phase margin of 52 degrees at 5 kilohertz. And it turns out now that our DC loop gain is 8.6 or 18.7 dB, which is better than it was before. This loop gain is not bad. We do have a good phase margin, but we could further improve it by increasing the low frequency or DC value of the loop gain. The reason we would want to do that is to reduce the disturbance transfer functions. If you recall from previous lectures, the disturbance transfer functions such as the GVG or transfer function from VG hat to V hat end up having a factor of 1 plus t in them, like this, in the closed loop case. So we can use our loop to reduce this transfer function in magnitude. A typical case for wanting to reduce this transfer function is in a DC voltage regulator that operates off the power line, where VG includes variations at the second harmonic of the AC line frequency. In other words, at 100 Hertz or 120 Hertz. So if we have voltage ripple from rectification that occurs down at frequencies down here, then our feedback loop can reduce those variations if it has more loop gain at 100 or 120 Hertz. So it would be nice if we could reduce 1 over 1 plus t or increase the loop gain to better reject those harmonics. What we can do then is to add a PI type compensator or lag compensator, which is this inverted zero form like this. What this does then is increase the loop gain at frequencies below the inverted zero frequency so that we better reject variations or disturbances. Since the inverted zero term adds phase lag at frequencies below 10 times omega L, it is a good idea to choose this omega L to be perhaps no more than 1/10 of our crossover frequency so that it doesn't reduce our phase margin. Therefore, with a crossover frequency of 5 kilohertz, we might choose this F sub L to be 500 hertz. Now, the lower in frequency we put it, the less benefit there is, say at 100 or 120 hertz. So we might want to put this, in fact, at a higher frequency. But if we do, then we're going to have to redesign our lead compensator to correct the phase margin. So here is a design then where we choose 500 hertz, and then we obtain this loop gain with our additional term at 500 hertz and loop gain being improved at frequencies below that. The 1 over 1 plus t factor then looks like this. Then let's construct the closed loop transfer function from VG to the output. Here's our open loop GVG, and it has the same poles as in GVD, plus it has a DC gain equal to the duty cycle. So I'm going to just sketch them on this plot. We have a duty cycle that is slightly greater than a half or slightly larger than minus 6 dB. So it's down here. And then we have the same two poles at F naught. So this quantity, GVG, then gets multiplied by 1 over 1 plus t. So we have to multiply this asymptote by that asymptote. Well, at high frequency above the crossover, 1 over 1 plus t is 1, and it doesn't change anything. So we get the closed loop GVG is the same as the open loop. And that's the case all the way up to or at frequencies of Fc and higher. When we go below Fc, the 1 over 1 plus t term adds a plus 20 dB per decade slope there. We had a minus 40 slope on GVG, so we go to minus 20. Then we have our compensator 0, which adds a plus 40 dB per decade slope below that, which will make this whole function flatten out below the 0. So that is at f sub z. The next corner frequency we come to is f0. This resonance at f0 is contained in both GVG and in 1 over 1 plus t. 1 over 1 plus t has resonant zeros and GVG has resonant poles, and they come from exactly the same place. So in fact, when you multiply these two quantities together, the resonance cancels out. So it doesn't appear in our closed loop GVG, or closed loop transfer function from VG to output. Finally, we have the compensator inverted 0 at f sub L. And below that, we get this 20 dB per decade slope in 1 over 1 plus t. So our GVG function, or GVG over 1 plus t, will have a plus 20 dB per decade slope below that. So this is GVG over 1 plus t. Some things to note about this. First of all, we can work out what is the gain at 100 Hertz or 120 Hertz, which is this value. We could calculate how much it is, and if we know how big our input variation is in VG hat, then we can multiply by this gain to find the resulting output variation. Another thing we can see from this is that the maximum value of this transfer function happens over this range of frequencies right here between f sub L and f sub z. So this is where this transfer function from the disturbance in VG to the output will be maximum, and we're most susceptible then to variations in VG over this range of frequencies, which is around a kilohertz. If we need to reduce variations more, we can also gain the insight from this kind of construction to see what we need to do. For example, if we want to reduce this transfer function more, perhaps we need to push up the crossover frequency more, which will push down all of these asymptotes at frequencies below the crossover. Here is a nice drawn plot on this slide of the quantity that I just computed. So I've done an example of how to design a PID compensator for a voltage regulator circuit. We came up with this compensator, with this GC of S that has this kind of transfer function. In the next lecture, we're going to design an op-amp compensator circuit that realizes this gain. In this lecture, I'm going to illustrate how to design the feedback compensator op-amp circuit that we specified in the example of the last lecture. I'm going to do this entirely with pen and pencil on paper here, and I don't have slides, but my handwritten lecture notes are appended instead to this lecture. So our compensator and feedback network from the last lecture was this. We had the output voltage fed back through a gain block H, where H was 1/3. That went into a summing node where the fedback signal was subtracted from a reference. And Vref DC component was equal to 5 volts. This made an error signal that went into a compensator network having a transfer function GC, and the output of the compensator is the control voltage VC. The GC that we specified was this. GC0 was what we called the gain. Then there was a compensator 0, and there was an inverse or inverted 0 for the lag or PI compensator. And there was a pole as well. So this has a bode plot that looks like this. And let's see, the corner frequencies, FL we chose to be 500 Hertz, FZ was 1.7 kilohertz, and FP was 14 kilohertz. This midband gain GC0 was 3.7 or 11.3 dB. Our job then is to design some analog circuitry to realize the feedback gain H and the compensator gain GC that has these asymptotes. Design is a creative process that has more than one answer. We rely on our prior knowledge and experience to invent circuits that realize these transfer functions. So what circuits would be appropriate here? What circuits do we know? First of all, for H, as I've mentioned previously, we usually realize H with a simple voltage divider, and we can design a voltage divider circuit that has a gain of 1/3 pretty easily. So for the voltage divider, we'll put V into the divider network. The output will be H times V, and we'll have two divider resistors that are called R1D and R2D in my notes, so that the transfer function H is the divider ratio R2D over R1D plus R2D, and that should be equal to 1/3. So that is a design equation then that we can use to choose the resistors. Okay, that one was easy. What about the rest of this circuit? We need a subtractor circuit with some transfer function GC. Do you know any circuits that can do that? Well, a subtractor circuit, from basic circuits, we have this kind of op-amp circuit is one well-known way to do it. We'll put a voltage I'm going to call V minus into one terminal and V plus into the other terminal, and we build an op-amp circuit that can subtract these voltages. And this is a well-known circuit that can do that. In this circuit, it's Z1 equals Z2, then it turns out that VC is equal to V plus minus V minus. If Z1 is different than Z2, then we get an added gain factor of Z2 over Z1. So one can show from solving this circuit then that the output voltage VC of S is equal to Z2 of S over Z1 of S times the differential input voltage V plus minus V minus. Our job then is to choose Z1 and Z2 to get the compensator gain that we want. And as for V plus and V minus, what we want is to subtract the fedback output from the reference. So we can make V plus equal to the reference, and we can make V minus equal to the fedback output voltage H times V. Okay, and Z2 over Z1 then is chosen so that that transfer function, or magnitude of Z2 over Z1, should have these asymptotes that we wanted for our compensator. Okay, I pulled that circuit just really out of my prior experience, but I hope if you've taken a beginning circuits class, then you've seen circuits like this before. So, what should we choose for these impedances that go into Z1 and Z2? This is a low power signal processing circuit, and generally in such circuits we try to avoid inductors because they cost more than capacitors and they're larger, although nowadays we can get pretty inexpensive inductors. But nonetheless, we're going to try to choose resistor and capacitor networks for Z1 and Z2, and we would like to put resistors and capacitors in series and parallel combinations so that Z2 over Z1 comes out to have this type of asymptote. So let's consider first, suppose we have a resistor and a capacitor that we put into Z2. What does the impedance of Z2 look like then? I'm going to draw resistor and capacitor impedances just on regular paper here, as if this were semi-log graph paper for a bode plot. So, if we had a resistor, we would have a flat asymptote, and with a capacitor we would have a minus 20 dB per decade, 1 over omega c asymptote. And our choices here are, we could use either a series or parallel combination. So if we used a series combination, we take the largest, like this. And if we used a parallel combination, we take the smallest. So we get something like that. And if we realize Z2 using one of these, then we will get Z2 asymptotes that look like one or the other of these. Well, the low frequency asymptotes of G, or of GC, here and here, in fact have the same shape as the series combination. So what we might think of doing then is to use an R in series with C to get the F sub L corner frequency out of Z2. So Z2 then, we can start out with some R in series with C. So I will call this R2 and C2. And we'll choose them so that we get this F sub L corner frequency. And F sub L, which we wanted to be 500 Hertz, is the frequency where these two asymptotes intersect, so that would be equal to 1 over 2 pi R2C2. That's a good start then for our transfer function. So that gives us the beginning of our transfer function, the first two asymptotes. How do we get the 0 at Fz at 1.7 kilohertz? Well, if we did it inside Z2, we would need to add an asymptote that increased with 20 dB per decade slope, which would be an inductor. We don't want to put inductors in this little low-power compensator network, so instead what we should do is perhaps think about what happens if we put resistors and capacitors into Z1. If we put resistors and capacitors into Z1, then its effect on the overall transfer function, which goes like 1 over Z1, will have asymptotes that go like 1 over those impedances. So I can draw the asymptote for 1 over R, and the asymptote for 1 over the capacitor impedance, which is 1 over omega C, or just omega C. And our asymptotes for 1 over Z1 then will be what? Well, if we put the resistor in parallel with the capacitor and then take the smallest asymptote for the parallel combination, 1 over Z will have the largest, and we'll do this. So this is the parallel combination. And likewise, if we put R and C in series, we'll take the largest, and then when the effect on 1 over Z will be to follow the smaller of these inverse asymptotes. So this is what we'll get in 1 over Z1 when we put R and C in series. Well, we can see that this parallel combination asymptote can give us the kind of asymptotes that we need to realize the zero. A flat asymptote at low frequency, and then we have a zero here at this frequency, and we'll increase after that. So if we make Z1 be R1 in parallel with C1, and then we make Z2 be R2 in series with C2, so that our Z2 asymptote looks like this, and our 1 over Z1 asymptote looks like this. Then to multiply Z2 by 1 over Z1, we simply add the asymptotes, or multiply. We add the asymptotes on a dB scale or multiply them on a linear scale, and what we'll get, I'll draw it down here at the bottom, at low frequency will be this asymptote, 1 over C2, times this asymptote, 1 over R1, which gives us something with a minus 20 dB per decade slope overall. Or 1 over omega C2 R1. At mid-frequency, we'll get this asymptote R2 divided by this asymptote R1, so we get R2 over R1. And we follow that until we get to the next break frequency, right here at FZ. After that, we'll follow the R2 asymptote times the omega C1 asymptote, and we'll get this. So that would be R2 times omega C1. Looks like we're almost done. We have our F sub L and our F sub Z corners. We simply need to add one more, which is a high frequency FP corner. What can we do to make our gain flatten out at high frequency? Well, there's more than one way to do it. One way would be to add a capacitor in parallel with Z2 to make this quantity go down and cancel out the C1 asymptote that is going up. Another way would just be to make the Z1 asymptote flatten out. So we could make 1 over Z1 flatten out if we added another resistor into Z1. For example, if we simply put a resistor here, which I'm going to call R3, then at high frequency, after capacitor C1 has shorted out or become much smaller in magnitude than R3, the overall series combination of Z1 will become R3, and 1 over Z1 will go to 1 over R3. For this to work, you can see that 1 over R3 has to be bigger than 1 over R1. In other words, R3 is smaller than R1. If we do that, our overall gain at high frequency will go to R2 here, multiplied by the 1 over R3. So our high frequency gain will be R2 over R3. These corner frequencies then in Z1 are found as usual. The FZ corner is where the resistor R1 is equal in magnitude to omega C1. So this is at 1 over 2 pi R1 C1. And the FP corner is where the R3 asymptote is equal to the C1 asymptote. So that would be at 1 over 2 pi C1 R3. Then here's our complete design. So we put H times V which is our V minus, into one terminal, and we put a Z1 there, which was R1 in parallel with the C1, and then both of those are in series with R3. And we put Vref into the other terminal, and we put a Z1 there also. Then our feedback impedance is Z2, which was R2 in series with C2. And we have a Z2 in the other leg as well. The output of the circuit is the compensator output voltage V sub C that goes to the pulse width modulator. And then here are all of our design equations. So from our previous slide, this gain, midband gain that we call GC0 is R2 over R1. So GC0 equals R2 over R1, and we wanted GC0 to be 3.7. Then our corner frequency F sub L was from the Z2, and that was 1 over 2 pi R2C2, which we wanted to be 500 Hertz. The corner frequency FZ was from the R1 and C1, so it was 1 over 2 pi R1C1, and we wanted that to be, that was 1.7 kilohertz. And then finally, the high frequency pole came from R3 and C1. It was at 1 over 2 pi R3C1, and that was 14 kilohertz. So then here are the design equations for our circuit, and we can now solve these for all of the element values. One thing I would point out here is that we have 5 different element values, right? 1, 2, 3, 4, 5, but we only have 4 equations. How do we get the 5th equation to solve for the 5th element value? Well, this is typically what happens. We don't have a 5th equation, and we can choose one of the element values arbitrarily. In fact, what we normally do for the last equation is we pick an element value to make the impedance levels come out to have reasonable power dissipations in this circuit. We'll have voltages in a circuit on the order of 1 or 2 volts. If we chose resistor values of, say, 1 ohm, then we would have 1 or 2 amps in our resistors, which is not a reasonable number. Typically, our op-amp can produce several milliamps, or maybe 10 or 20 milliamps at most. And in fact, what we would like to do is choose the element values so that the power dissipation in these elements is small. If you choose 1K type resistor values, then with 1 or 2 volts, we'll have 1 or 2 milliamps. If you choose a megohm, then we'll have 1 or 2 microamps. With milliamps, then we'll get milliwatts of power dissipation, and with microamps, we'll get microwatts. On the other hand, if we choose the impedance levels to be too high, then our circuit is susceptible to noise, and it will, with very high impedance levels, we have antennas that are just the wiring and the components that can pick up noise. And in a power converter, we're in an environment where there generally is a lot of noise from the switching of the power stage. The susceptibility depends on the layout of the circuit, which we don't know yet. But typically, if you have megohms, then the impedances are getting pretty high and they are susceptible to picking up noise. And so a typical choice might be resistor values of tens of k ohms or hundreds of k, but not megohms. What is chosen in this design is to use R2 equals 100k as our last equation, and then from there we can solve for the other element values. Okay, I won't write down the element values, but they are in the accompanying lecture notes. There are several other considerations here to think about. First of all, if Vref truly is just a DC voltage that never changes, then we don't really need all these R's and C's. If you put a DC value for Vref, then you can see that the voltage at this node will also be Vref. And we don't really need the R2C2, or for that matter, we don't need the Z1 there. We can simply just connect Vref up to the plus terminal of the op-amp. Often you see this done in power supply designs that have a fixed output voltage. On the other hand, if Vref is something that can change, then removing all these R's and C's will change the transfer function from Vref to the output, and in that case I think we probably want to put these element values here. A second consideration is that we're going to connect the voltage divider to this HV point. And so we ought to think about how the interaction happens between the voltage divider and our op-amp circuit. So the full circuit will have our divider coming from the output voltage, and then we'll have our Z1 and Z2. In this case, the Z1 can actually load down this voltage divider and change its transfer function. So we need to account for this in our design. One way to do it is to choose the divider resistors to be small in value relative to Z1. But that might mean that there's substantial power dissipation in these resistors. Another way to account for it is to make a Thevenin equivalent model of the divider. And the Thevenin equivalent, looking back into the divider from this node, will have a voltage source equal to the open circuit voltage, which is the desired transfer function. It's V times the divider ratio. And then it has a Thevenin equivalent resistance that is the resistance seen from this node when you short the voltage source or short V to ground, and you get the parallel combination of the two resistors. So that's our Thevenin equivalent, and we put that then in series or connected to the Z1. Well, what this suggests is that why don't we use the parallel combination R1D and R2D to be equal to R3? Then we don't need to add another R3, and we can simply choose R1 and put R1 and C1 there in the actual circuit, along with the rest of our op-amp circuit. And I'm not drawing what's connected to the plus terminal. So then this gives another constraint that the value of R3 that we solved before on the previous slide should be in fact equal to R1 and D in parallel with R2D, and we also want the divider ratio to come out to give us our H. And we again have a set of equations that we can then solve for all of the element values. One last practical point regarding this design. What we're asking our op-amp to do is to make a transfer function that looks like this. And one feature of this transfer function is that the high frequency gain is flat and doesn't roll off. In fact, the value of the high frequency gain would be this midband gain GC0 multiplied by the ratio of the pole and zero frequencies, and that works out to be 30.5, which is approximately 30 dB. The FP corner frequency was 14 kilohertz. So we're asking our op-amp to produce this gain of 30 dB at all frequencies above 14 kilohertz. Well, real op-amps can't do that. They can't produce gain out to infinite frequency. They have what's called a gain bandwidth product. The internal gain of an op-amp that's compensated so that it can operate at unity gain is typically some single pole slope that passes through 0 dB or unity gain. An average op-amp might have a unity gain frequency of 1 megahertz or so, which is a decent op-amp but not a fancy high-frequency op-amp. And it will have a very large low-frequency gain, but at some point it rolls off like this. So let's suppose we used a standard 1 megahertz op-amp, and let's compare the gain that the op-amp has to what we're asking it to do. Well, where does this op-amp gain pass through this gain of 30 and a half? It's basically at 1 megahertz divided by 30 and a half. So we're at 30 dB at 1 megahertz over 30 and a half, which is about 33 kilohertz. Okay, that's higher than 14 kilohertz. That's not bad. What it's going to do is introduce another pole into our overall transfer function. You can build a circuit and ask for whatever gain you want, but you aren't going to get that gain if the op-amp can't produce it. So we would expect to see some pole, a second pole up here at some higher frequency. It'll be in the vicinity of 33 kilohertz, although you have to do some more work to analyze the op-amp feedback loop, including its actual gain, to see exactly where that corner frequency happens. But let's say it's on the order of 30 kilohertz. Now, our crossover frequency for this example was 5 kilohertz. And you can see that this 30 kilohertz is less than a decade higher than 5 kilohertz. That means that the added pole that we get is going to be significant, and it's going to reduce the phase margin of our compensator in our feedback loop. If we want to fix that, we would have to either redesign the compensator to get more phase margin, or perhaps use an op-amp with a wider bandwidth. If we used, for example, a 2 megahertz op-amp, then this corner might happen up above around 60 kilohertz, which then would be a decade higher than our crossover frequency. So perhaps we need a 2 megahertz or faster op-amp here. So we can use our graphical construction of bode plots to gain the insight that we need to design an op-amp compensator circuit to complete our design of the feedback loop. In this lecture, I'm going to summarize another example that is similar in many ways to the example of the last two lectures, except it has a more recent and practical application, along with some simulations to show the actual performance. This is a point-of-load regulator made with a synchronous buck converter. So we have a synchronous rectifier in our buck converter. The output voltage is 1.8 volts to supply digital chips. And the input voltage is 5 volts. Our output current can vary anywhere from 0 to 5 amps. In this kind of converter, it is important that the loop be able to respond quickly to variations in load current. And in fact, the processor may change its load current much, much faster than the bandwidth of the feedback loop, and so we invariably have to put many capacitors around the processor chip in order to maintain adequate voltage regulation at high frequency and have a sufficiently low output impedance driving this chip. Still, the faster we can make our converter, the less capacitor we need, and the capacitors that can work in this application can add up and be fairly expensive. So we see a lot of applications such as this nowadays with buck converters that operate at a low duty cycle. And in fact, we may have parallel connected buck converters to supply the full current. These parallel connected converters are generally phase shifted so that their ripples, the inductor current ripples, will cancel approximately, and so that we can have a faster transient response using small value inductors. So in this example, we're going to model the capacitor. This is 200 microfarads of capacitor with an effective equivalent series resistance of 0.8 milliohms. We'll have a 1 megahertz switching frequency, which is a pretty typical number for this kind of converter nowadays. And our inductor for this converter is 1 microhenry, which should give us a pretty fast transient response in our output current. Here's our equivalent circuit model for the buck converter. Here I have dependent sources where the transformer goes, and the equivalent circuit model of the inductor with its loss resistance and the capacitor with its ESR. This circuit has 3 resistive elements, so it's a little bit of work to calculate the Q factor. I'm not going to go into it here, but there's another approximation we haven't discussed called the high Q approximation, where when we have both series loading and parallel loaded damping resistors for series resonant and parallel resonant circuits, if they're both present in this circuit, then the high Q approximation says that the overall Q is approximately the parallel combination or inverse addition of the 2 individual Qs. This is a good approximation when the product of the Qs is substantially greater than 1. So we work out our corner frequencies. This LC circuit has a corner frequency of 11 kilohertz. The overall Q with all 3 resistive elements works out to be no more than 2.3 or 7.2 dB. And the ESR causes a 0 in the transfer function at the corner frequency of the ESR and capacitor, given by 1 over 2 pi ESR times C, or 1 megahertz. Let's work out the uncompensated loop gain then and design a compensator. This goes very similar to the previous example. With no compensator then, our overall loop gain will be the control to output transfer function GVD multiplied by the pulse width modulator gain multiplied by the compensator gain of 1. And in this low voltage output of 1.8 volts output, we don't need to divide the voltage down, so our H is 1. Here are the bode plot asymptotes then of the uncompensated loop. Our DC gain is 5, which is not very high. We have our poles at 11 kilohertz, and then we have a 40 dB per decade slope after that until we get to the ESR 0 at 1 megahertz. And here are the phase asymptotes. With a 1 megahertz switching frequency and with the need for wide bandwidth of this feedback loop, we're going to attempt to obtain a crossover frequency of 100 kilohertz, or 1/10 of the switching frequency. This is an aggressive choice. So at that frequency of 100 kilohertz, here is our uncompensated loop gain. It's something below minus 20 dB at that frequency, so we will need some extra gain in our compensator to bring this gain up to 0 dB. For verification, here's a MATLAB plot of the exact magnitude and phase response, and you can see indeed that it does follow the theory. And our phase at 100 kilohertz is basically minus 180 degrees, and we have next to no phase margin. We'll proceed in a design just as in the previous example with a crossover frequency of 100 kilohertz and a desired phase margin of 53 degrees. We need our lead compensator then to look like this, where this is 100 kilohertz, and we're going to want 53 degrees of phase lead out of our compensator so that we get that phase margin. When we plug into our compensator formulas from the earlier lectures, we find that we need a 0 frequency here at 33 kilohertz and the pole frequency at 300 kilohertz. This gain at this point will need to be 20-something dB, and when we work it out, we find that the DC gain of our compensator needs to be 15 dB at this point. So then here's the summary of the compensator gain. Another thing I would point out here is that this lead compensator works out to need a high frequency gain of 49 or 34 dB. And a practical implementation then would mean that we have a added high frequency pole at, say, 10 times the crossover frequency, or at 1 megahertz, with a gain of 49 at 1 megahertz. So we need an op-amp then with a gain bandwidth product of at least 49 megahertz in order to realize this compensator. This is getting to be a pretty high frequency and more expensive op-amp. It's a non-trivial op-amp, and we're going to need very good layout to get this compensator to work. Here then is a plot of the compensated loop gain. The orange asymptotes here are the compensator phase, and when we add those to the blue asymptotes, which was the uncompensated loop, then we get the green asymptotes, which is the compensated loop phase response. And here at 100 kilohertz, or the crossover frequency, we get our required phase margin. This compensator also increases the loop gain so that we cross over at 100 kilohertz. Once we've done this, it's now time to add the PI part of the compensator. The DC gain of 28.7 is not bad, but we could do more by simply adding an inverted 0 to get the PI compensation as well and improve the low frequency regulation. So as before, we will add an integrator at low frequency. We're going to choose this corner of our inverted 0 to occur at less than 1/10 of the crossover frequency, and here the choice was made to make it 8 kilohertz. So with that addition of the PI compensator, then here is our overall loop gain response, including this 8 kilohertz inverted 0. And here is verification with a MATLAB plot of the overall loop gain magnitude and phase. MATLAB, including deviations from the asymptotes, predicts a crossover frequency of 105 kilohertz with a phase margin of 51.6 degrees. Now, given that design, what I want to discuss now that is new in this example is to verify the closed loop responses and plot some transient responses. So first we'll talk about the reference to output transfer function, 1 over h, t over 1 plus t, and recall for this example h is 1. So here in blue were the asymptotes of the loop gain t, and in green then is the transfer function from reference to output, which is t over 1 plus t. So we have a low frequency asymptote of 0 dB, the crossover frequency here at 100 kilohertz, and then we follow t after that. Here is a MATLAB plot of that function. You can see that it indeed looks as advertised. There's a little bit of peaking in the vicinity of 100 kilohertz, which comes from the phase margin of 51.6 degrees, so Q is close to 1. And there's a little bit of resonance there. Here's a simulated plot of the step response. So what we're doing here is applying a 10 millivolt step in the reference voltage, Vref, from 1.79 volts to 1.8 volts and back. So the output voltage steps from 1.79 up to 1.8, and then here it steps back to 1.79. This is the resulting inductor current variation, and this is the duty cycle variation. One thing you can see here is that the duty cycle must take a jump, and there's a little spike in duty cycle in order to get the voltage to change this quickly. And in fact, we can zoom in on the response here, and what we can say is that the duty cycle doesn't actually saturate. If we applied a larger step change in voltage, the duty cycle would hit the maximum value that the pulse width modulator can make, maximum of D of 1, or perhaps something less than that. And if it did saturate, then our transient response would not look like we expect. But since this step is small enough, the duty cycle doesn't saturate, and actually we see a step response with an overshoot that is commensurate with the Q of 1 that we get from our phase margin of 51.6 degrees. So this overshoot plus the ripple, switching ripple, are exactly what our small signal models would predict. Next, let's plot the output impedance and then plot the response to a step change in load current. If we set our independent sources in our converter model to 0, then the model reduces to this equivalent circuit, and we can work out the open loop output impedance from this. Basically, we have the parallel combination of the two branches, and we can construct the asymptotes for that parallel impedance. Here are all the asymptotes: the inductor, capacitor, the load resistance, and the ESR down here. So first we find the series combination of the inductor resistance and the inductor, which will follow this. And then we put that in parallel with the ESR and the capacitor. Here's the ESR and the capacitor. We take the smaller of the two for the parallel combination, and we get the red asymptotes with some Q factor there. At DC, then, the output impedance is dominated by the inductor resistance for these numbers, and at high frequency, the output impedance is dominated by the ESR of the capacitor. Next, let's construct the closed loop output impedance. So here is our T. Here is 1 over 1 plus T, which you recall is 1 above the crossover frequency, and it follows 1 over T below the crossover frequency. Then we need to multiply this 1 over 1 plus T function by the open loop output impedance to get the closed loop output impedance. Here is that computation. So this is our 1 over 1 plus T, and this one is our open loop output impedance. And what we need to do then is multiply the orange asymptotes by the blue asymptotes. They're shown in green. So here we follow the open loop output impedance above the crossover frequency, and below the crossover frequency, this open loop output impedance gets multiplied by the 1 over 1 plus T function, and we get asymptotes then that do this. So you can see that the maximum value of the output impedance happens at the crossover frequency right there, and at some frequencies below that. In fact, from working out the asymptote, it works out that we're at 8 milliohms right there at the crossover frequency, which is in fact the value of the capacitor impedance at the crossover frequency. It's just below minus 40 dB ohms. And at lower frequencies and higher frequencies, we have lower impedance than that. What would you expect then would be the voltage deviation that would be caused by a step change in load current? Well, perhaps it's hard to do the inverse Laplace transform in your head, but one thing I can say, just as a first order approximation, the step change in load current has a wide spectrum of frequency components, and the ones at these frequencies where the output impedance is maximum will have the most effect on the voltage deviation. For verification, here is a MATLAB plot of the closed loop output impedance, and you can see that it does indeed look like the asymptotes that I constructed on the last slide, with a similar kind of maximum that's just under minus 40 dB ohms, and with a little bit of peaking right here at the crossover frequency in the vicinity of 100 kilohertz. And here is a MATLAB plot of the response to a step change in load current. So here we're making the load current change from 2.5 to 5 amps and back. So it does this. In response to that, here is the transient that we get in the output voltage, in the inductor current, and in the duty cycle. And the output voltage transient is magnified right here. First of all, you can see that the settling time is about 10 microseconds. So that's the time from here to here. and that time is commensurate with our loop bandwidth of 100 kilohertz. In addition, the magnitude of the voltage deviation is about 15 millivolts. From 1.8 volts it dips down to 1.785 volts. So if we take a 2.5 amp change in current and multiply that by this maximum output impedance of 8 milliohms, that works out to be 20 millivolts. So that's this rule of thumb approximate estimate of how large the voltage variation will be. Okay, we actually have 15 millivolts instead of 20 according to the simulation. But if we wanted to reduce this step change, we would need a yet higher crossover frequency, or we would need more capacitance on our output, one or the other, in order to reduce the maximum output impedance of our converter. So I've illustrated another example. This is a fairly up-to-date point-of-load power converter. It is a challenging design and requires good engineering. You need to know what you're doing as far as working out the closed-loop responses and closed-loop output impedances in order to meet the kind of demanding specs that we have nowadays for these kinds of power systems.